lezioni di algebra lineare numerica applicazioni in presenza, anche se c'è qualche remoto. E adesso parlo in italiano perché tradizionalmente la lingua della 2 giorni è sempre stata l'italiano, però dato che abbiamo uno speaker che non è italiano e vari ragazzi ci hanno anche chiesto se si poteva parlare inglese e ci hanno scritto in inglese, noi ovviamente diamo loro la libertà di parlare in inglese o in italiano nel modo in cui loro preferiscono. Io voglio semplicemente dirvi che noi siamo giunti alla 17ª edizione di questo appuntamento e non vi dirò molto sull'appuntamento perché poi c'è Dario e la memoria storica di questo convegno e quindi sarà Dario poi a dirci l'evoluzione del convegno, dove eravamo quando siamo partiti e dove siamo oggi, vero Dario? E semplicemente mi limito a dire che chiaramente questo convegno di algebra lineare numerica, gli argomenti trattati sono moltissimi, dalla risoluzione di sistemi lineari di grandi dimensioni con metodi diretti iterativi, precondizionatori, ma anche funzioni di matrici, anche metodi osservazionali, insomma autovalori, autovettori, tensori, algebra lineare. Naturalmente tutte le applicazioni anche di queste tematiche sono più che benvenute, ce ne sono tante. Quello che vorrei dire è che il convegno è stato, è il frutto del lavoro di un comitato scientifico di cui storicamente fanno parte Dario Giorni, che voi tutti conoscete molto bene, quest'anno ne faccio parte anch'io. E poi siamo stati fondamentali nell'organizzazione i membri del comitato locale. Io ne faccio parte, ma non posso ringraziare me stessa ovviamente, ma devo ringraziare Giuseppe Izzo dell'Università di Studi di Napoli, Valentina De Simone e Marco Viola dell'Università della Campania di San. Sono stati fondamentali, hanno gestito tutto. Poi devo ringraziare anche le sponsor, perché noi siamo stati patrocinati dai 2 atenei che ho citato e anche dall'Inland e in particolare dal Gruppo Nazionale del Calcolo Scientifico, quindi che ci hanno fornito un supporto molto valido per organizzare questo evento. Abbiamo un sacco di eventi. Quest'anno ci sono ben 35 contributi e poi ci sono 2 team nell'unità dell'algebra lineare numerica, che sono Michele Beni, che appunto recentemente è entrato dagli Stati Uniti da un po' da qualche anno oramai, e poi Mirek Prima all'Università di Praga. Quindi loro avranno un tempo maggiore e per questo motivo purtroppo abbiamo il tempo di contributi che sono soltanto 20 minuti. Quindi io prego gli speaker e prego anche il chair di far rispettare i tempi. Nel caso che volete discutere di cose in particolare, al piano terra c'è una sala, la sala A, che è dedicata a questo, quindi potete venire lì, potete discutere, potete parlare, perdonate, noi dovremo rispettare i tempi del programma. E prima di passare la parola di dire qualcosa in inglese, io vi vorrei dire che oltre a quella la sala di una sala di storia nella quale sarà una colazione di lavoro molto leggera. Ancora una nota per non dimenticare niente, anche qui ci sono i cartelli per la wifi cellula, speciale con una password di cui voi troverete cartelli da questo. Una cosa che vi voglio dire è che purtroppo non siamo riusciti a organizzare la tradizionale cena sociale. Questo è dovuto al fatto che oggi fa Valentino. Quindi i ristoranti non erano affatto propensi ad accettare prenotazioni senza sapere esattamente il numero di persone che sarebbero venute. Inoltre offrono pacchetti particolari per le coppie e così via, quindi considerano non molto conveniente fare una cena sociale un po' al buio, oltre al fatto che altro non possono mettere un tavolo con 10 persone. quindi questo ci ha impedito di fare il allora, vi chiedo una cortesia di indossare il badge, perché dato che questo è un esame storico, a volte entrano dei curiosi, quindi noi vorremmo poter distinguere tra chi è veramente argomento e gli eventuali curiosi che entrano, perché poi le guardie giurate, insomma, vogliono controllare piano piano. Provo, scusatemi un po' per la fama, ma la mascherina è... Allora, provo a dire le stesse cose inglese per le eventuali persone che non parlano bene italiano. I wish to welcome you all. Thank you for being here. And for me, it's a great pleasure and an honor to have you here. And this is the 17th edition of these 2 days of Numerical Linear Algebra and Application workshop series. And everybody knows what the goal of this conference is, the topics that are all topics of numerical linear algebra and their applications in science and engineering. And this organization is the result of the efforts of the scientific committee, which consists of Dario Bini, Fabio Di Benedetto, and myself, and also of the local organizing committee, which includes myself, of course, but is composed by Giuseppe Izzo from the University of Naples Federico II, by Alessandro and Marco Viola from my former university, which is the University of Campania di Giorni. And we had many submissions, many requests to registration, and we have about 60 participants present, 25 a little bit more remotely. And also we have 37 talks, 35 contributed talks and 2 keynote talks given by the scholars in science in the field of numerical linear algebra. Now at the Scuola Scuola Superiore in Pisa and by Miracina from the Charles University in Prague. And before leaving the stage, who will say something about the history of this conference series, I want to give you some details about the organization. As you all know, of course, all the talks will be given here in this lecture room. And on the same floor, we also have a room which is dedicated for coffee breaks and light lunch. And also, we have a room for the discussion on the ground floor. You can go there and discuss with your friends, work, etc. We have, of course, a Wi-Fi connection. You can find the signs on the walls at this floor and on the ground floor. And it is a dedicated Wi-Fi connection. And of course, we also have everyone and the Wi-Fi from the University. Let me remember. Okay, no more things to say. Just a note about the length of the talks. Since we received many abstracts, we didn't want to exclude anybody. We decided to reduce the time of the talks. So the time slot for the contributed talks is only 20 minutes. I kindly ask the speakers to respect this time limit, and I kindly ask the chairs to help me to keep the conference in time, because we have some time constraints. Unfortunately, we weren't able to organize a social dinner, because today is St. Valentine's Day. All the restaurants are full, and they are not inclined to accept reservation without knowing the exact number of people sitting at the table. And I strongly suggest you, if you have some time, during the coffee break or at lunchtime, since we have 1 hour and a half for the lunchtime, to go outside, for example, and to try to reserve the table for tonight, because we expect that all the restaurants, all the bars are full. I recommend this. Of course, you can also check the restaurants using your smartphone, your PC, etc., and make a phone call. And our sponsors are the University of Naples Federico II, the University of Campania Luigi Vanvitelli, and the Istituto Nazionale di Alta Matematica, specifically the National Group for Scientific Computing that supported us in this organization. And I must acknowledge their help. Please wear your badge, because there are people entering this building just for curiosity, because this is considered a historical building, not very old, but a nice building to be visited. And the guards on the ground floor would like to distinguish among the people that are here for the conference and people that are just giving a look around. And to conclude,
io spendo 30 secondi, in modo da rimanere in orario. Grazie a un'iniziativa di Valeria Simoncini, e si è ripetuta quasi con cadenza annuale in varie sedi, infatti è una conferenza itinerante. Se volete vedere la storia la trovate sulle pagine web. E inizialmente partecipavano, diciamo, le prime 2 giorni 20-30 persone, poi il numero è cresciuto nel tempo e siamo arrivati alle ultime 2 giorni 50, 60, 65 persone, quindi abbiamo 85. Io ringrazio Daniela per questa organizzazione, per aver realizzato questa 2 giorni qui a Napoli. Devo dire con grande soddisfazione e orgoglio che l'algebra lineare numerica in Italia è cresciuta non solamente in numero, ma in qualità negli ultimi anni. Abbiamo tantissimi giovani e grazie anche alle tecnologie post-Covid o durante il Covid di comunicazione sulla rete, abbiamo la possibilità anche di far partecipare giovani che si trovano all'estero e stanno svolgendo in modo brillante la loro carriera fuori d'Italia. Buon lavoro a tutti, e io passerei la parola subito a Fabio Di Benedetto che presiede questa prima sessione.
Grazie Dario. Ho l'onore di dare la partenza a questo convegno in questo giorno di San Valentino che dedicherei agli innamorati dell'algebra lineare. E do la parola al primo speaker che, come quasi tutti quelli di questa prima sessione, si focalizzeranno prevalentemente su funzioni di matrice. Il primo speaker è Igor Simonek, Scuola Normale Superiore di Pisa, e ci parlerà appunto di funzioni di matrici generalizzate e metodi di Krylov razionali. Prego.
Okay, can you hear me? I don't know, online, I'm not sure if it's working everything. Più vicino, okay. Okay. Okay, this one, yes. Okay, I will try to point without facing away from the microphone, which is not very easy. Okay, so I will maybe remove this if I can. Okay. Okay, so thank you for the introduction, and in general thanks to everyone who organized this conference. I will tell you about computation of generalized matrix functions using irrational Krylov methods. This is a joint work with Angelo Casulli, who is another PhD student at Scuola Normale Superiore. So this is the outline of the presentation. I will first start with an introduction on generalized matrix functions and rational Krylov subspaces. And then I will go into the main part, which is how to compute these generalized matrix functions using existing methods. And then I present our method and some of its properties. And finally, I have some numerical experiments to show you. Okay, so a matrix function is defined for a diagonalizable matrix in terms of the eigendecomposition. So I will use the mouse, which is, I think, easier for me. So also, so the people online also see it. Okay, so take a diagonalization of the matrix. A function is defined on the spectrum. If a function is defined on the spectrum, you can define f of a by applying f to the eigenvalues. A generalized matrix function is defined in terms of the SVD. And so can also be defined for rectangular matrices. So if you have an SVD, you can define a generalized matrix function, which we denote by f diamond of A, by applying f diamond to the matrix of singular values in this way. So you apply f to the positive singular values and you leave at 0 the others. So you need the function to be defined on the positive real numbers. And you don't care about anything else. So you can assume that f is odd and that f of 0 is equal to 0. This is not restrictive. Just to give some examples, in case you haven't seen them before, if you take the identity, you get A. If you take an odd power, you get this kind of alternating product between A and A transpose. If you take the inverse, you get the transpose of the Moore-Penrose pseudo-inverse. And if you take, in general, any odd function, and you consider this matrix here, which is, for instance, the adjacency matrix of a bipartite graph, then you can f of this big matrix can be defined in terms of f diamond of the small matrix. Okay, I will also recall what Krylov subspaces are. So a standard polynomial Krylov subspace is this one defined below. So just take a matrix and a vector, and it's the space spanned by B and the matrix A applied to B a few times. And the rational space can be defined from this space by applying the inverse of a polynomial in A, which is defined using these poles Cj that have to be outside of the spectrum of the matrix. So in practice, when you work with these spaces, what you want to do is compute usually an orthonormal basis, which you can do using the rational Arnoldi algorithm that requires at each iteration to solve one linear system, shifted linear system with the matrix, and then some orthogonalization. Okay, so now I will start with the main part. Our objective is to compute, f diamond of A times B. So here I show some methods that have been developed in the literature. So for instance, in this paper from 2016 by Arrigo, Benzi, and Fenu, they propose this method, which is based on the Golub-Khan bidiagonalization of the matrix. So they propose to perform k steps of this process. So this produces a matrix k by k, which is bidiagonal, and two projection matrices with orthonormal columns, pk and qk, such that bk is the projection of A using these two matrices. And they propose to approximate f diamond of A times B using these two projection matrices, and so you have to compute the f diamond on the projected matrix here. Another method, which is proposed in a later paper, is based on Chebyshev interpolation. And both these methods have very good performance for functions that are analytic or entire, such as the sine function of the hyperbolic sine. So in general, both these methods have underlying them polynomial approximation, because you can recall that if you do a certain number of steps of the Golub-Khan bidiagonalization, you're actually constructing bases of these two Krylov subspaces associated to A transpose A and A transpose. So what we propose to do in our work is to replace these subspaces with rational Krylov subspaces. So now we have the same notation. So qk and pk will now be bases of these spaces. So here hidden there is a pole sequence, which is the same for these two spaces. So you choose some poles and you can define these rational subspaces. And as before, we can define the projected matrix like this. And then the approximation has, again, the same form. You project using these two bases. Only that now we have rational Krylov bases. So we have a higher cost, but also different properties. So let me just give you some remarks on the computation of this. Maybe I can do this. So now, okay, first, say we want to compute one of these bases, let's say qk. This has to be computed by solving shifted linear systems. So we have to solve k-1 shifted linear system with A transpose A. Then the other basis can be computed without solving any linear system, because we have this property between the Krylov subspaces. So if you multiply by A one of them, you get the other one. And so we can obtain the other basis using just a QR decomposition of this tall matrix here. So we don't need to solve any other linear systems. Okay. Sorry. Okay. So in the Golub-Khan bidiagonalization, we had a nice property that the projected matrix was bidiagonal. So we could compute the new columns using a short-term recurrence. Now we no longer have this property. We just have an upper triangular matrix in general. But we can use another structure, which is the quasi-separable structure, to still obtain a short recurrence for the columns of these matrices. So quasi-separable means that every block in the strictly upper triangular part of BK has rank 1. So I will just give you a very short idea on how this is done. So let this be the projected matrix. The actual thing that we use is that this block here, so the last 2 columns minus the last 2 rows, this here, this one has rank 1. So the last column can be written as a multiple of the previous one. Maybe I can. I'm not sure if I'm the only one who's seeing this, but no, okay. Okay, so I will ignore it next time. Okay, so what we do, you use these 2 columns, and now I will not give any details about this, but using this, you can write a short recurrence that relates the new vectors with the old ones. And this is the algorithm that we obtain. So giving in input a matrix, a vector, the function, and some poles that we chose previously, we get a vector which approximates f diamond of A times B from a rational Krylov subspace. So we have the initial steps which don't use the short recurrence, and then for each step, what we have to do is that we have to solve a shifted linear system with A transpose A. Then we can compute a new vector by orthogonalizing against the previous ones. And I should say this can also be done using a short recurrence, using, for instance, the rational Langches method, since we have a symmetric matrix. And then we can use another short recurrence, which is the one that I showed you before, to compute the vector of the other matrix and the projected matrix. And then we do, as I showed you before, so you compute the projected matrix, and you get the approximation to f diamond of A times B. Okay, so we also have an error bound for this method. So here we will use the notation sigma j for the singular values of the matrix, and we also use the notation sigma n for the nth singular value, where I mean if n is larger than m, I mean sigma n equal to 0. And so we have this result here. This is very similar to the results that are known for the convergence of rational Krylov methods for standard matrix functions. So the error after k steps is bounded by this minimum on this approximation problem, where you're approximating the function f with this rational function, which is an odd rational function, defined using the poles. So the denominator is fixed, defined on, depending on the poles that you chose, and the polynomial here is minimized, only it's odd. And you have this interval of singular values here. And you can also reformulate this bound by changing your variables, basically, and here you get an approximation problem which no longer has odd functions, but this is more familiar, perhaps. Okay, so as I said, we can have, here we have sigma n, okay? So if n is larger than m, this is always 0. And this is 0 also if sigma m is larger than 0. So if you have a matrix which is full rank but rectangular, you can have sigma n equal to 0. And this can give problems for convergence. It's not just an artifact of the proof that we use. So this is a small example that shows that the projected matrix can actually have singular values that are arbitrarily close to 0 if you consider a rectangular matrix. However, this difficulty can be overcome by using this identity. So instead of computing f diamond of A times B directly, you can compute this using f diamond of A transpose, which has the different shape, so you no longer have this problem here. So what you can do is you compute W like this, and then, so here you use a rational method or polynomial method on A transpose, and then you can recover the other function that you were interested in by solving this least squares problem here. So now you have a projected matrix with singular values in this interval, which is not always, but many times can give better convergence. Okay, finally I have some numerical experiments. So our experiments are mainly done to investigate how sharp the bounds are. So we compare different methods on matrices with prescribed singular values. So we compare polynomial method, the extended Krylov method, which has alternating poles between 0 and infinity, the shift and invert method, which has a single repeated pole. And here we chose a pole that optimizes one of the bounds that I actually didn't show you. And finally, a rational method with poles chosen in an asymptotically optimal way from this paper here. Okay, so this is convergence for the polynomial Krylov method. You see on the right, convergence for functions that are entire. So convergence is very fast. And on the other hand, the same method can be very slow. So look at the scales on the axis. For functions that have problems near zero, so for instance, very high derivative or a singularity of the function. And this black line is a bound that is not dependent on the function. So it only depends on where the function is analytic and on the singular values of the matrix. So this is a sort of worst case behavior, and you see that it actually captures the behavior in this circumstance where the function is not entire. On the other hand, on this side, you would have basically a flat line here, which is not very useful. Here are our rational methods. You see the optimal, okay, so this function here is written down here. The method with quasi-optimal poles is the best one, and also the bound that this line here is the bound that I showed you earlier. It's very precise in describing the convergence. And then we have the shift and invert and the extended method, which are somewhat slower, but again, we have a bound that correctly captures the asymptotic behavior of the shift and invert method. Here's what I told you before about rectangular matrices. So if you consider a function like square root of z, which has a very high derivative near zero, if you use the transposition trick, you get much better convergence. On the other hand, if you consider a function like this, so z log z, which doesn't have too many problems in zero, you basically don't get anything. But still, in some cases, it's useful. And here we also investigate the loss of orthogonality when you use the short recurrence. So you see that if you use a short recurrence, you actually do lose orthogonality. But this does not seem to affect too much the convergence, as long as the convergence is fast. So we don't have any theoretical results, but at least the experiments show that in yellow you see here the difference between the short recurrence and the full orthogonalization, and you see it's quite close to machine precision. Okay, this is it. So we'll just briefly conclude. So our methods are an extension to existing method for the computation of f diamond of A times B. We can still use a short recurrence like in the previous methods. We have proved error bounds for these methods, and these can also be applied to the previous methods. And in that case, we have polynomial approximation instead of rational approximation. And finally, as you might expect, the numerical experiments show that rational methods are superior in approximating functions that have singularities in zero or anywhere near the spectrum. Okay. Thank you for the attention. If you want, here's a preprint on archive and some references that I cited.
Bene, grazie allo speaker anche per la velocità, perfettamente nei tempi, tanto più che c'è tempo anche per qualche domanda. Chi vuole fare domande magari meglio che le formula in inglese, ti passo il microfono.
Cosa è successo? Sono partite le slide. Ok.
Nicola Guglielmi inaugura le domande.
Thank you for the talk. So, do this generalized function have application to, I don't know, differential equation or integral equations?
So, I don't know
I'm
about
curious.
that. The main application that I know about is the one that I hinted at here. So, I don't know what's happening. So if you consider a function from a matrix, if you want to compute a matrix function of this form, then you get generalized. I don't know, I'm not sure if it's this computer or something, but anyway, you saw the slide before. So if you have to compute a matrix function of the form which has a block, okay, it works now. I don't know, it's as if it's pressing automatically the button to go ahead. Anyway, this form here. Okay. So I think you understand what I'm saying, right? So if you have to compute a matrix function of that form, you can use a generalized matrix function instead. I don't really know about other applications. I'm sorry.
Okay, it would be interesting. Thank you very much.
Grazie, se ci sono altre domande. Se non ci sono altre domande, direi di ringraziare ancora lo speaker. E passiamo al prossimo, che rimaniamo al centro Italia, sempre Scuola Normale Superiore, Michele Rinelli. E Michele Rinelli ci parlerà invece di limitazioni sul decadimento per proiettori spettrali. Prego.
Ok. Maybe like this. Okay. Okay. So, thank to the organizers for this opportunity. And today I will show you some refined decay bounds on the entries of spectral projectors developed in a joint work with Professor Michele Benzi. So we start recalling some concepts about decay matrices, in particular matrix functions, and then spectral projectors along with some previous results. Then I will show you some refined decay bounds obtained exploiting an integral representation of the sine function, which lead to an asymptotically optimal bound and a bound related with the eigenvalue distribution. Okay, so let us start with the exponential of diagonal decay. A sequence of matrices has this property if the entries decay geometrically, moving away from the main diagonal, and the constant factor C, the geometric rate, must be independent of the sides. So such sequences can be truncated to m-banded matrices, and the bandwidth can be chosen independent of n. Observe that a banded matrix has ON non-zero entries, so it is a sparse matrix. So such sequences are approximatively sparse. So matrix functions are defined this way in the Hermitian case, and the main ingredient for obtaining decay bounds is the error of the best polynomial approximation of a set. In fact, we have that if a matrix A is m-banded Hermitian and the spectrum is contained in S, then if the error of the best polynomial approximation decays geometrically, then also the matrix function f of A decay as the exponential of diagonal decay. Since the bound depends on the set S and on the bandwidth and not on the dimension, if we consider a sequence of matrices with all these properties, so spectral property and bandwidth property, then the sequence f of an has the exponential of diagonal decay. And a similar property holds, I don't know how to show. Okay, a similar property holds for general matrices, and in this case we have decay related with the sparsity pattern of the starting matrix A, and under suitable hypothesis we have that f of A is still approximatively bounded. Okay. So the main function we have studied is the spectral projector, which is defined for an Hermitian matrix with spectrum contained in the union of two disjoint intervals. Then the spectral projector associated with the left interval is given by this matrix function here. So the important fact is that this function takes the value 1 on the eigenvalues on the left interval and takes the value 0 on the other eigenvalues. So the value mu can be chosen arbitrarily between A1 and A2. So some properties, this function, h, is not continuous over the whole spectral interval. Okay. So we cannot use directly polynomial approximation, but we have this invariance for linear transformations, which allows us to assume that the spectrum of H is contained in the union of two symmetric intervals. Then we have another important relation between the function H and the sign function, which tells us that the entries coincides up to a factor 2, except for the main diagonal. Okay, so there was already a result about decay of spectral projector, which uses this idea. So the sign function is equal to this product. So the idea is to consider a polynomial approximation of the inverse square root, and then to consider x qk of x squared, which will approximate the sign function. And using this idea, there is this result, which gives a family of bounds parameterized by a parameter chi. So for I and j fixed, we can minimize in the variable chi, and the optimized bound numerically behaves as b minus a over b plus a to this exponent here. Okay, so let us move to the refined decay bounds. The idea is to use this integral representation of the sign function and then to bound the ij entry of the sign this way. This is a similar idea to the one used in this paper. And then we can bound the ij entry of this function depending on the parameter t and then integrate. So we have used also the previous idea, so to approximate this function and then to consider x qk of x squared, which will approximate the whole function. And the fact is that now the polynomial approximation of the inverse gives us a single bound and not a family of bounds like before. So we obtained this result, which has the same asymptotic behavior and a moderate constant factor. We also improved this result because the last bound was not the best from an asymptotic point of view. In fact, it's shown that Ek behaves asymptotically this way. So this translates in terms of decay properties to this bound here. And in the previous bound, we miss this factor which improves the speed, the asymptotic speed. However, the constant factor is still unknown. So what we have done is to obtain an equivalent bound from an asymptotical point of view. And this is a family of bounds parameterized by tau. But in this case, all the bounds have the same behavior. But we can also optimize to get the best possible bound. So these are some experiments. in this example, we have this three-diagonal matrix with this spectral property. And let me explain this plot. The solid line represents the maximum modulus attained in the kth diagonal of P. And the other lines represent the bounds for I minus j equal to k. And we see that the new bounds improve the previous one, and we see that the dashed bounds takes over because of the more asymptotic speed. So let me stress that the bounds are independent of the sides. So if we would choose a matrix with size like 10,000 or a billion, the bound would be the same. So the bounds don't depend on the side. In this other case, we have a 20-banded matrix with a similar spectral property, and we have a slower bound. See that here we have 2,000, and previously we had 150. So we obtained also bounds related with the eigenvalue distribution, and the idea comes from the fact that this property holds for the inverse function. And we asked ourselves if this property holds for spectral projector. The answer is yes. In fact, we obtained these results. The values bi here are the distinct moduli of the eigenvalues of h in a decreasing order. So you must see this parameter L as the number of moduli of eigenvalues we are removing from the spectral information we are considering. Moreover, for fixed ij and when L increase, if the value BL is much less than BL minus 1, then the geometric rate QL decreases substantially. But we also have this minus L here, so the fact that the exponent is smaller makes we have a trade-off between the smaller geometric rate and the smaller exponent. So what we can say is that if we have one or few isolated eigenvalues, they do not contribute to the decay behavior of the matrix, and that certain eigenvalue distributions lead to super-exponential decay. So we have the first experiment where we have a matrix with one isolated extremal eigenvalue, minus 1. Here, minus 1 is also multiplicity 10. And we see that the bound with L equals 0 does not catch the behavior as the bound with L equal to 1. Then, in this example here, we have a matrix H, three-diagonal, with the eigenvalues described in this figure. So you see that we have several isolated eigenvalues at the extremes. They become more clustered near the spectral gap. And in the right figure, we have the exact decay compared to the bounds for several values of L. And we have that the optimized bound is this dashed blue line, which describes well the super-exponential decay of the projector. In this case, here the eigenvalues are perfectly symmetric with respect to the origin. In this other example, the eigenvalues are not symmetric, and you see that the result is worse, but still catches the fact that we have an exponential, a super exponential decay instead of an exponential, a simple exponential decay. So to conclude, we developed 3 decay bounds for the spectral projectors. The first is a single bound that describes the decay in case of uniformly distributed eigenvalues. The second is optimal in the sense of polynomial approximation. And the third catches super exponential behaviors. We have still some open problems, like to find appropriate bounds for the non-symmetric intervals case, and find the smaller constant factor. In practice, the smaller factors are smaller than the one that we found, and to establish connections with more complicating the eigenvalue distribution. So, thank you for the attention.
Bene, grazie al nostro secondo speaker. Si vede che i giovani sono abituati a tenere i tempi molto più di noi datati. C'è una domanda di Stefano Serra Capizzano. Meglio che vieni qua perché così riusciamo a entrare nell'inquadratura. Non è lui che deve... Sì, perché sennò...
I would like to ask just if the isolated eigenvalue is close to 0, because you have shown one isolated eigenvalue far away from the interval.
No, we have several isolated eigenvalue, extremal eigenvalues.
Ah, extremal. Yes. So, not in the middle.
The eigenvalues of largest moduli.
Okay. But when you have approximation of the differential equation, in general, there is an eigenvalue distribution, and this eigenvalue distribution is a cluster around 0. Yes. In which kind of application you find this kind of two separated intervals?
So you're asking the application where we found this project? These are found in electronic structure computations, where we have discrete Hamiltonians describing systems. So in systems modeling like semiconductors, we have that the Hamiltonians have this spectral gap property, which allows to say that the projector has a decay, and often is encountered a special eigenvalue distribution. And I think this is a step in order to describe better super exponential phenomena. So there is some open problems, of course, even if there are several isolated eigenvalues near the gap. So we have like a gap and an eigenvalue inside. That eigenvalue does not count in practice for the bound, but we have not explained it with a rigorous bound.
I see another application, preconditioning. If you have preconditioning, then you have this kind of application.
Yeah, maybe we should investigate more.
Bene, se ci sono altre domande, altrimenti ringraziamo ancora Michele Rinelli. Se passiamo alla terza speaker del mattino, rimaniamo in centro Italia e ci spostiamo leggermente in questo viaggio geografico che abbraccerà un bel po' di sedi. Andiamo verso il Gran Sasso Institute dell'Aquila. Miriam Ignazzo ci parlerà di polinomi di matrici quadratici.
Allora. Dove? Mi sto trovando. Allora, chiudo qui? No? Ah, ok. Qui.
No, però stanno dietro allora.
Ah, ok, allora stavo... E poi... infatti... Secondo me è quella a fianco, però infatti non so. Ok.
Questa?
Sì.
Allora, questa dà fastidio però.
La metto dall'inizio.
Quanto bello, un attimo. Quanto bello. Sì.
Ok, quindi questo qua davanti e indietro. Okay, so good morning everyone, and today I would like to talk about an idea for the computation of the distance to singularity for matrix polynomials. So in this particular talk, we will refer to quadratic matrix polynomial, but the same idea, the same method can be also generalized easily for polynomials of a higher degree. So let's start with some definitions. And a quadratic matrix polynomial is a polynomial in this form here, where the coefficients a, b, and c are matrices of size n by n. And in particular, we will call a polynomial regular if its determinant is not identically 0. Otherwise, we will call it singular. And sometimes we have a regular polynomial, and we would like to know how far or how near this polynomial is from a singular one. And this idea is distance to singularity, and can be defined in this way. So we are computing the minimum of the norm di perturbation delta A, delta B, and delta C that we have to add to the coefficients of our matrix polynomial in order to make it singular. So why this definition is so important? Let me give you some motivation. So first of all, in the control system theory, we may have a second order control system. So a control system in this form here, and we would like to design a controller such that the closed loop here has some desired properties. And the fact is that the behavior of this control system is mostly governed by the eigenstructure of this quadratic matrix polynomial. So if this polynomial is singular or near to a singular one, then we have problems in controllability and solvability of the problem, and we have to apply different methods, depending if the polynomial is regular or singular. Another application may be in the conditioning of eigenvalues. Let me give you an illustrative example. We have here a polynomial, and if we perform the first choice of the parameters, alpha, beta, and gamma, then we have that the eigenvalues are all distinct from each other and all finite. Instead, if we perform a different computation, a different choice of the parameters, we have that, for example, the second eigenvalue may vary discontinuously. So as beta goes to 0 and alpha is fixed, then second eigenvalues goes to infinity. And so the eigenvalues in this particular case are not well conditioned. And the problem is that in a small neighborhood of the polynomial, there is a singular matrix polynomial. So we would like to understand what's the radius of this neighborhood in order to apply a proper eigensolver. So these are a few references in literature. The first three papers relies and study a method for the computation of the nearest singular pencil. And the first two papers have the drawback that they do not respect the structure. So if we have a matrix polynomial with additional structure on it, such as symmetry of the coefficients, these two papers do not respect the structure. The third one instead will be the one that we will follow in the most, with the difference that in our method, we will use singular values, since they are well conditioned. And the last paper instead is a first attempt to extend the method for quadratic and matrix polynomial of higher degree. So in order to start, we first reformulate the problem. So as I told you before, we are looking for a polynomial in this form here, a perturbed polynomial singular. So it's singular if and only if its determinant is identically 0. And using the fundamental theorem of algebra, we know that since the determinant is a scalar polynomial of degree at most 2n, then if it has more than 2n plus 1 roots, then the polynomial itself will be equally 0. So our idea is to choose a set of distinct complex points, mu I, then evaluate the determinant at this particular point and impose it to be equal to 0. So we can rephrase the problem as an optimization problem in this form here, where we are looking for the argmin of this matrix norm here, where we choose the Frobenius norm, subject to the condition that all the determinant evaluated at this particular point must be equal to 0. Now we need a functional that can give us the idea of how close this determinant is to 0. So we decide to compute the singular value decomposition of each of these matrices here, then consider the smallest singular values, and the singular values to 0. So the function will be this one here, and for simplicity, we choose perturbation in the form epsilon delta theta gamma, where this perturbation matrix is of unit Frobenius norm. The function will involve all the smallest singular values of the matrices that I showed you before. And so if this functional is going to 0, the matrix polynomial will be singular. So our method is a two-step method. And the first step, we fix the norm of the perturbation and compute the minimum of this functional here. And then we look for the smallest root of the functional g epsilon. Let me show you here. So we are looking for the smallest root, which will be something in this form here. The smallest root here, epsilon star. And as I told you, our method is a two-level approximation, two-level method. So in the first part, we fix the norm, the norm of the perturbation, and solve the minimization problem. The second part is that we tune the value of epsilon in order to get the minimal roots. And we will call it inner iteration and then outer iteration, these two methods. So I'll explain in detail both the inner iteration and the outer one, starting from the inner iteration. There are several ways to solve this minimization problem, and we prefer to use a steepest descent method. So in order to employ this method, we have to compute the derivative of the functional. And we can indeed compute the derivative, since the function is differentiable, since all the singular values are differentiable. And the derivative will be something in this form here, involving not only the singular values, but also the singular vector associated to it. So we have to minimize this inner product. And with several computational calculations, we can prove that, indeed, along the solution of this ODE system, we have two properties. The first one is that the norm of the perturbation is conserved and is constantly equal to 1. The second one instead is that along the solution of this ODE system, the functional decreases monotonically. So this is indeed a gradient system, and in particular, the value eta is a Lagrange multiplier that respects the norm conservation. So we are looking for the stationary points of this functional here, g epsilon. But we have that these stationary points indeed are the stationary point of the gradient system. So the iteration will be solve this gradient system, finding all the stationary points. Then we have completed this first part. Once we have all the stationary points, we go on with the outer iteration. That will be changing the value of epsilon in order to find these minimum roots here. And we plan to do it using a Newton-like method. The advantage of using a Newton-like method is that In particular, this functional here has a derivative which is basically costless because it just depends on m2, m1, and 0 that we have computed before. So we perform this Newtonian iteration, and sometimes we have to correct the step using a bisection method. So it will be a hybrid Newton bisection method. Now let me give you an example, a small one. We have this polynomial here, and we may recognize that if we do not perturb the first and the third coefficients, and we just add the perturbation on the second one, where the first row is all 0, and then 0.50, the perturbed problem will be singular. And indeed, applying our method, we have that the distance to singularity is in the order of 0.28. And the interesting fact is that all the coefficients are perturbed. And in this particular example, we also have that the sparsity pattern is preserved. And this is basically a surprising fact. So another advantage of our method, our approach, is that it can be easily extended with two polynomials which have, for example, additional structure on it. And the structure may involve not only the coefficients, such as symmetry, for example, but also the whole matrix polynomial, such as palindromy. So a palindromic polynomial is a polynomial in this form here. And in this context, we prefer to use perturbation that respect the structure of the problem. Why is that? Because we can have eigensolver, such as palindromic linearization, that respect the property of the problem. So in this context here, it's more useful not only to compute the nearest singular polynomial, but the nearest palindromic singular one. So we introduce this new idea of distance to singularity. And we just have to change a step of the method. And a step is that we compute the projection to the manifold of palindromic polynomial in this form here, and then we change the ODE system, basically, in this form here. And this ODE system can be solved as before. A small example. And here we have a palindromic polynomial, and in the end, applying our method, the outcome is still palindromic. But here we don't have that. The sparsity pattern is preserved. So just in order to conclude, as I told you, the method has the advantage that it can be extended easily to polynomial of a higher degree, and also that it can be used for polynomial with different structures, using a different projection. And we still have some open issues, for example, in the choice of the points mu I. Because as I told you, we need at least 2n plus 1 points. But do we need just 2n plus 1 or more than that? Like 3n, for example. Is there an optimal choice of mu I? For example, if we start with a real problem, do we have to still choose a complex point or just real one? And how the choice of the points influences the numerical result? Another idea can be performing the method onto a set of complex points and then adding an additional set of points, mu I tilde, in order to prove if the determinant is still 0 there. Another delicate point is the efficient integration of the gradient system, which can be expensive, and how to include additional structure computing the projections. And the last step is computational challenges of polynomial of higher degree. Since as we increase the degree of the problem, we also increase the complexity of the problem. So this is a delicate point that this needs to be investigated. So that's all for now, and thank you for your attention.
Bene, ringraziamo la speaker. Ci sono domande? Anche remoto? I have a question. The problem of finding the nearest singular polynomial is more difficult than computing just the minimal distance.
The minimal distance between the...
Without knowing which is the nearest polynomial, just the distance. Is an easier problem or is equivalent?
I think it's an easier one because we have to, if we have to compute the nearest polynomial, we have to compute also the perturbation that we have to add to our polynomial. Instead of computing the nearest, just the distance, it's an easier problem. Because in this case, we have to see exactly what are the perturbations that we need to add to our polynomial, so also the argmin. So it's a more delicate problem. So yes.
Anyway, knowing the nearest polynomial gives some computational advantage.
Yes, yes, of course. Yes. It's more useful to know exactly what's the nearest polynomial. Yes.
Ok, thank you. Altre domande? Bene, ringraziamo ancora Mira Miazzo. Se in diretta televisiva non c'è problema. Il prossimo speaker, torniamo a Pisa, ma sdoppiamo la sede di Pisa perché abbiamo sentito rappresentanti della scuola normale, invece Leonardo Robol dell'Università di Pisa, e ci sdoppiamo anche come variabili perché ci parlerà di funzioni di matrici in due variabili.
No, o se no si può spostare, se le può nascondere forse è meglio, però se no... Nascondi i controlli mobili forse. Ok.
Okay, thank you, Fabio, for the introduction. So this talk is based on a joint work that I've been doing with Stefano Massei, and as the title says, we will be dealing with computing bivariate functions of matrices. In a moment, I will define what I mean by bivariate functions of matrices, and this will be a talk considering essentially the dense linear algebra aspect of this problem. So there will be no low-rank matrices and no Krylov subspaces. But in practice, we ended up looking at this stuff because we were in need of computing these objects after a projection to a small subspace in a Krylov setting. So there's a lot of ways that one could use to define what a univariate matrix function is. Let's say a classical matrix function. One could use Taylor series, for instance. One could use contour integrals along a path that encloses a spectrum of the matrix, like you see here. We may use the eigendecomposition, as you've seen in the previous slides. And philosophically, what we are doing is saying, okay, we have a matrix, a linear operator A. When we compute f of A, we're just computing another linear operator which has the same eigenvector, the same eigenspaces, but different eigenvalues. We're just mapping the eigenvalues through the function f. And this idea, let's say, can be generalized to two variables. So by considering a function f zw, here written with Taylor expansion. And we just for instance, evaluate Taylor expansion on our right-hand side on this matrix C by multiplying matrices powers of A on the left and powers of B on the right. And the same thing can be also described by a contour integral along paths gamma A, gamma B that enclose a spectrum of A and B respectively. So it's relatively easy to see that what we are building is a linear operator acting on matrices instead of vectors. And this linear operator has as eigenvalues the function f applied to the eigenvalues of A and B. It has a lot of nice properties that essentially generalize the properties of univariate matrix functions. For instance, and this will be important, we can do similarities on A and B and take the similarity out of the two matrices. So this relation that you see here holds. And it has some interesting well, I don't know if I should say applications or at least connections with equations that we all know. For instance, if you think about a Sylvester equation, ax plus xb equals c, this is, can be written as the evaluation of a bivariate matrix function f, x plus y, to the matrix x here. And the interesting part is that if you want to express the solution of the Sylvester equation, then you can write x as a bivariate matrix function g applied to the right-hand side. And this time, g is just 1 over x plus y. Now, this idea can be generalized to other classes of matrix functions. So if you had, for instance, a polynomial instead of just x plus y, and you want to solve this guy over here, which is the summation of powers in A and B acting left and right on the matrix, then you can just evaluate the bivariate matrix function 1 over p. And there's a lot of other applications that we'll just briefly mention, but you can express Frechet derivatives of univariate matrix functions as bivariate ones. And actually the most interesting for us was that all the time you have a function of a Kronecker sum, then you can express it as a bivariate matrix function of this form, gxy equal to fx plus y. And that was actually what we were doing at the time. We were trying to compute fractional powers of objects of this form, and this is one way to express them. So, okay, they have a lot of nice theoretical properties, but how do we compute such a function in practice? There is one case where this is very easy, and this is the case where A and B are diagonalizable. So I'm keeping the same notation as before, so I'm assuming that f is given as a Taylor series. If A and B are diagonalizable and we have an eigendecomposition, we can use the property I was mentioning before that you just do similarities on A and B and take them out of the expression. And you get f A B transpose applied to C as this guy here, which apart from the similarities on the outer part of the equation, is just a bivariate matrix function applied to diagonal matrices, the A and the B, which have the eigenvalues of A and B. If you do a few computations, you can notice that this is expressed in a compact form where you just have VA and VB minus 1 here, and then a matrix with the evaluation of the function at all the eigenvalues of A and B, Hadamard product, so element-wise product with the right-hand side with the chosen change of basis. So in all the cases where A and B are, for instance, normal matrices, this is definitely the way you want to go. So if you want to compute a generic, let's say, bivariate matrix function, you can just diagonalize them and compute this matrix with all the evaluations, take this Hadamard product, and do the transformation back. This will be perfectly fine because the eigenvector matrices will be well conditioned, but obviously not all matrices are normal matrices, maybe unfortunately. And so we need to take into account the case where we cannot really diagonalize A and B, or it's not a good idea because of stability reasons. So what can we do in that case? And we tried to mimic, let's say, what Schur-Perlet would do for univariate matrix functions in the bivariate case. Now the idea is useful to keep in mind, but it's not exactly the same problem because we're now looking at applying a matrix function to a vector, and that's one case where you cannot really use Schur-Perlet also in the univariate case, but it's still a good idea to keep in mind. And so this is the evaluation scheme that we propose. So the first observation that we can make is that it's not really restrictive to assume that A and B are at least upper triangular, because we can also take Schur forms, and it's easy to take the transformation matrices which are unitary or orthogonal out of the evaluation of the function. And then we proceed by partitioning the matrices A and B, the diagonal blocks, in a way that their spectra will be separated. I will give more details on this later on. And then we will derive a formula for understanding how to relate bivariate matrix function of block triangular matrices like these ones with bivariate matrix functions of the smaller blocks, so of A11, B11, A11, B22, and so on and so forth. Once we put all these pieces together, we will be able to design a divide and conquer scheme that will allow to evaluate these bivariate matrix functions in the generic case. So, okay, let's keep the idea that A and B are upper triangular. Then we can solve a couple of Sylvester equations, A1, 1V minus A2, 2V equal A1, 2, and the analogous one for B, and construct block diagonalization, basically, of these two matrices. We will be able to do this because we are assuming that the spectra of the two blocks are separated. In practice, we will see it. We will need to assume that they're far enough, because otherwise these Sylvester equation might have large solutions, and these guys might be ill-conditioned. But if you put all of these in the equation you had before, then basically you can rephrase your original evaluation of the bivariate matrix function as these block diagonal ones, which splits into 4 smaller evaluations, where you have all the AII, BJJ combinations, essentially. And then just need to reassemble the whole thing by multiplying by the inverses of these two guys. So putting all of this together in a pseudocode, this is what you get. So you have a procedure that starts by computing sure forms of the matrices A and B, and then calls a recursive procedure on the triangular matrices, in which there are essentially 2 parts which are important. So there is one case where the matrices are small, and then you just compute this guy directly. I will give more details on how to do this later on. And the other case is where these A and B are still large enough, so you can partition them into triangular blocks by ensuring that the spectra are sufficiently separated. And you solve the Sylvester equation to block diagonalize them, and go on recursively until you get to the minimal dimension. So as I was saying, in practice, we don't want really to have ill-conditioned eigenvector matrices, so we'll need to make sure that these Sylvester equations have small enough solutions. And to do that, we will apply the same strategy that Schur-Perlet uses for the evaluation of unit variate matrix function. So we will choose a certain delta, which is a parameter that should be tuned in order to for the algorithm to behave properly. And then we will subdivide all the blocks so that the spectra inside each block is concentrated in a small disk of radius delta. And 2 blocks have eigenvalues which are farther than delta. Now, this criterion helps with controlling the norm of the solution of the Sylvester equations, but it's not really a guarantee. It would be in case the matrices would be normal, essentially. But they're not. They're actually triangular, so we can only hope that this works. But we also check a posteriori that the thing did not break down. So there are some cases where this solution could be of larger norms than we were hoping. And in that case, we just remerge the blocks and treat them as a unique block. So the remaining part that needs to be discussed is the evaluation of the small bivariate matrix function. So at the end of the recursion, we have a small, like, 4x4, 8x8, or something like that, bivariate matrix function that we need to evaluate. And we've experimented actually with 2 different ideas. One was using Taylor series. So if you end up with a matrices A and B which have clustered spectrum, and this should happen because we are using the Schur-Perlet blocking. Then, in principle, you can approximate F around the eigenvalues of A and B with a bivariate Taylor series, which converges quickly. And so that's an idea that works most of the time. But it's somehow not so robust because, as I was saying before, we also need to remerge blocks from time to time. And in that case, it can happen that the spectrum is not so clustered and you end up using Taylor expansions that are a little bit longer and a little bit harder to compute accurately. So we ended up with doing something that sounds a little bit strange and usually what they tell you shouldn't do. So we have matrices A and B, which are not diagonalizable in general. So we just add a very small perturbation of the order of the machine precision, random, and this will make them diagonalizable almost certainly. And then we just diagonalize them and compute the matrix function by direct diagonalization. Obviously, in this way, it's not stable, so we need to ensure that we do it with a sufficient working precision to guarantee the results in double precision, basically. So what we do is we start lowering the unit roundoff to u squared, where u is the unit roundoff in double precision, add these small perturbations in a way that we can represent them accurately enough. And then we estimate a working precision in a way that we can work with the eigenvector matrices that will be ill conditioned in a way that the result is accurate to double precision. We compute the matrix function, and then we go back to the working original unit round. So there is one can show that if UH is sufficiently small, then you can guarantee the result in double precision. But this sufficiently small is essentially related to the condition number of the eigenvector matrices, which we haven't computed yet. So that's a little bit of a problem. And we need to estimate these condition numbers before actually computing them, because we will need to use the higher precision to compute VA and VB. Now, this can be done, some estimates can be derived by looking just at the entries of the matrices. So remember, we're talking about triangular matrices here. Okay, so computing eigenvectors is just essentially solving a linear system. So this, all this analysis is basically down to analysis of condition number for linear systems. So one can derive bounds of this form where this M that you see here is the size of the matrices. So these are fairly accurate if the matrix is small enough. If the size of the matrix starts to grow a little bit, then this can be quite an overestimate. So in practice, we redo another blocking of these smaller matrices if they're a little bit larger, with a smaller delta, and use this result on the small blocks, which just have a very clustered eigenvalues. This turns out to be quite a good heuristic in practice. Then we compute the eigenvectors, and again, we check a posteriori that we were right, so the precision was enough to actually guarantee the result. And once we have that, we compute the evaluation of the bivariate matrix function and go up with all the recursion procedure. So I just want to show you a couple of experiments. These ones that you see here are small matrices, like 64 by 64. And the function is the inverse square root of x plus y. So we've tested the proposed scheme on different matrices. I will briefly describe at least a few of them. And that's fun 2m that you see here. Then we've tested also a straightforward diagonalization with nothing special, which we expect to not be stable in most of the time. And then we've also tested just diagonalizing at higher precision, which would be an natural competitor to what we're doing. So in the last column here, you see the condition number times the double precision, and that's the accuracy that we should be aiming for, essentially. Okay, so if the method is backward stable, it should deliver a result within this accuracy here. And as you see, our proposed scheme is essentially we're giving an error of the same order, and the same holds for YAG HP, which is the one using higher precision. The same cannot be said for straightforward diagonalization, but on the other hand, straightforward diagonalization is very fast. As you see, the method here is very competitive also with straightforward diagonalization all the time, that you can split the matrices in many blocks, because then you just have small matrices that you need to diagonalize in higher precisions. Some of the matrices are actually have eigenvalues which are really badly conditioned. Some of them are from the gallery of MATLAB. George block has a Jordan block of size 8 by 8, and the rest is fine. That's the reason we can actually work nicely on this one. And then we've tested also the performance on a good example to see that at least when the things are going in a nice way, we can still be competitive with straightforward diagonalization, let's say. That would be the difficult to beat method. And so we've tested with random complex matrices which have nicely conditioned eigenvalues on average. And as you see from this result, this is the time that the proposed algorithm takes, and it's just a little bit higher than the times that just diagonalizing and computing the function takes. So, for instance, at size 1000, we are 5.5 seconds instead of 4, so it's not too bad of an overhead. Obviously, this works because in these examples, we are able to actually go down with the recursion and split in really small blocks. So if you want to try this out, we have a Julia package, so you feel free to experiment with that. The reason we went with Julia for this is that it embeds higher precisions in a native way, which is not something you find most of, for instance, in MATLAB. Well, in MATLAB you have it, but it's really slow. So this is just implemented there. And we only have complex arithmetic, essentially because we were a little bit lazy, and it's really not so nice to swap blocks on real sure forms. But that's essentially it. As soon as we will have let's say the swapping of the blocks implemented on real sure forms, that will be available as well. To conclude, well, I think this showed that perturb and diagonalize can be an effective strategy, even if it sounds a little bit strange because you're not used to diagonalizing matrices where they should be not diagonalizable. But on the other hand, if you do it with the appropriate care, it can work, and you just need to make sure you're working with the right precision. And most of the time, you need to have a good blocking strategy for this to actually work out, because you want to end up working with small matrices when you do this. And this is all. Thank you for your attention. I'm happy to take questions.
Bene, grazie a Leonardo Robol. Ci sono domande? Valeria Simoncini, se puoi venire qua così entriamo in inquadratura, grazie.
Allora, chiaramente l'intera procedura è nota nel caso dell'operatore Sylvester, con un sacco di lavoro dietro, i blocchi, eccetera. L'uso di mixed precision rispetto agli algoritmi di Bock, Armstrong e Co., come funziona, come si confronta, perché la diagonalizzazione ovviamente non è qualcosa con cui confronti solitamente.
Per le Sylvester, stai dicendo?
Per l'operatore Sylvester, che è uno dei due che hai presentato, l'altro probabilmente si ricollega, però la cosa principale che hai fatto vedere è Sylvester, e per quello tutta l'operazione è nota, anche la ricorsività, certo, mi sembra.
Sì, rispondo. Maybe I will answer in English. So the question by Valeria was how would this be compared for the Sylvester operator with the similar approaches which are well known essentially. And so maybe I need to be clear on this. So if you have a Sylvester equation to solve, don't use this method. There's better ways, better things you can do. And the main point here is you have a generic function that is not 1 over x plus y. So for the Sylvester operator, there are few special things that happen that can make this idea a little bit more efficient. So in practice, this reduces to the recursive algorithm for Sylvester equations if you work with 1 over x plus y. The main point, up to a very small differences that make this slightly less efficient. And that's because a Sylvester equation is basically solving a linear system. Okay. That's what you can use to make it a little bit more efficient. But for instance, if you want to compute an inverse square root of the Sylvester operator or something like that, this is a nice way to go. So this was the main idea that we had in developing this. So not that you can solve a Sylvester equation, that's, let's say, one of the possible applications, but this algorithm is not really tailored to do that specifically. Okay? So that's more useful for more complex and difficult to evaluate functions. I hope I have answered the question.
Bene. Ringraziamo ancora Leonardo. E con l'ultima speaker di questa iniziale sessione ci spostiamo un pochino più a sud, Politecnico di Bari, Marina Popolizio. Ci parlerà di una funzione abbastanza famosa, soprattutto ultimamente, la funzione di Mittag-Leffler.
Thank you for the presentation. This is a joint work with Roberto Garrappa and Tiziano Politi, and actually we are still working on it. So let's start with the definition of the Mittag-Leffler function. It is known at the moment, but okay, just to give you the basic facts about this function. We have here a family of entire functions which depends on two parameters, alpha and beta, which are in general complex with the real part of alpha greater than 0. Okay, it's a series expansion with the Euler gamma function at the denominator. It is easy to see that for alpha and beta equal to 1, we just have the exponential. But as soon as we move from these two parameters, alpha and beta equal to 1, we actually lose a lot of important and nice features that the exponential has. As for example, the semigroup property. And actually we miss a lot this property when we numerically deal with this function, because for example, we cannot use the scaling and the squaring procedure that works very well for the exponential, for the scalar, and the matrix case. These functions were introduced in the context of the analysis of divergent series, but nowadays they are very important in the context of fractional calculus. And actually in this context, they have the same key role that the exponential has in the ODE context. But okay, my talk is about Mittag-Leffler functions with matrix arguments, and so this is just a list of some examples in which these objects are required. Okay. And for example, in the solution of systems of fractional differential equations, or in the solution of PDEs where the time derivative has a fractional order, or in the control theory when we analyze the controllability and observability of these systems, and in the solution of multi-term fractional differential equations, that is to say, equations in which we have the simultaneous presence of different real orders. And so just to give you an idea of the context in which we work, and so the peculiarities that we have to deal with, I describe here a method that me and Roberto Garrappa propose in the context of FDEs. So actually we have a system of FDEs to solve. The term f of t here is linear, but just to simplify the presentation, but in general you may think to more complex situations. And d alpha of 0 denotes the fractional derivative with the definition due to Caputo, but you may also generalize to other definitions. And the key fact here is that to solve this problem, we have applied the variation of constant formula. And so you may appreciate here that the role of the exponential in the usual expression is now occupied by these Mittag-Leffler functions. And so we introduced these exponential integrators that we defined generalized because we do not have the exponential but these Mittag-Leffler functions. And if we just approximate the term f by means of polynomial, we have a method which has excellent stability properties, high order convergence, and it overcomes memory issues. The problem is here that you have here an integral, and actually also in the definition of the fractional derivative, we have an integral, meaning that we have to take into account all the memory of this problem. But if we give this matrix a compact formulation for the solution, actually we overcome memory issues because we go directly into the point, say Tn, in which we want to compute the solution. And so here we have just to compute the Mittag-Leffler, we have to compute this Mittag-Leffler function here, E alpha 1 of Tn to the alpha times A, and these coefficients Wn minus J, which actually require the computation of several terms of the form E alpha beta of A times a scalar BL, which actually changes. Sorry. I wanted just to, okay. And this is a challenge in this situation because we have to compute these terms, and so actually we need a reliable and fast way to compute these matrices. But Mittag-Leffler functions are nowadays common also in the network theory. Precisely, we talk about matrix Mittag-Leffler functions also in this context. Probably Michele Benzi and Estrada were the first to introduce these functions in this context. And recently, Fabio Durassante and Francesca Enrico have proposed these Mittag-Leffler network indices defined for a general alpha between 0 and 1. So the idea is to compute these Mittag-Leffler functions in the matrix A, which is the adjacency matrix of a graph, so it is in general large and sparse. And it is interesting to note that in this case, the power of the Mittag-Leffler functions is the possibility to interpolate between resolvent-based and exponential-based indices. Okay, so we need a way to compute this Mittag-Leffler function with matrix argument. And so when we started to think about this problem, we tried to simply generalize the fnance code, MATLAB code, to this function. And Leonardo Robol already introduced the Davis and IAM algorithm. And so I just recall here the main features because they will be important also for our numerical tests. So we start from a sure decomposition of the matrix A in such a way that we just reduce the computation to the Mittag-Leffler function of this triangular block. In the improvement given by Davis and IAM, the matrix T is reordered in blocks in such a way that each block has clustered eigenvalues and the distinct blocks have far enough eigenvalues. And this will be a very important point in the procedure. Then the procedure computes the Mittag-Leffler function for the diagonal blocks by considering the truncation here of the series expansion, where the Mittag-Leffler function and its derivatives are computed in this value sigma, which is the mean of the eigenvalues. For the extra diagonal blocks, the Parlett recurrence holds, and so we compute them one extra diagonal at a time. And then we just go back to the Mittag-Leffler of the original matrix A. The challenge here is that we need to compute these derivatives of the Mittag-Leffler functions. And this is a problem because there were no codes available for this purpose. And so we dealt with this. And actually, we applied the method that we had to define to compute the Mittag-Leffler function for scalar arguments, because there were no codes available for this topic. And we tried several strategies, but this one, based on the Laplace transform, is very effective. So it is based on this formula for the inversion of the Laplace transform, and so we use this integral representation. This idea was proposed by Weidman and Trefetten, but then we extended it to any couple of parameters, alpha and beta, and any complex argument Z. We extended this approach also to the derivatives of the Mittag-Leffler functions because the similar property holds, and so these derivatives are the inverse Laplace transform of these functions, and here we have just a different strength of the singularities, actually. Okay, then I do not give the details. You may find them here, but the idea is very similar for the scalar case and the derivative case, even if more technicalities have to be taken into account. Okay, so to work with this object, we proceed by deforming the Bromwich line. And so this line sigma minus I infinite, sigma plus I infinite becomes a contour, and then we just apply a quadrature rule on this contour. Okay, so for simplicity, we choose the parabolic contour because it simply depends on, on one parameter mu. Then the trapezoidal rule was used, truncated at a term big N. So this procedure actually requires the computation of 3 parameters, mi, h, and n. And to compute them, we have just a routine that takes here as input the precision epsilon that we want to reach and gives the parameters by imposing that the error is proportional to the accuracy we want. Actually, we impose that all the 3 components of the error are proportional to epsilon, that is to say the discretization error, the truncation error, and the round-off error. I do not go into the details, but it's important to stress, for example, the role of the round-off error, because it strongly depends on these parameters mu here that defines the parabola that we are considering. If the parabola is small, actually small in the sense it is close, let us say, we have a small round-off error, but it becomes large if this parabola becomes more open. How do we choose the parabola? They depend on the singularity of the Laplace transform. But in the scalar case, we may also consider parabola that do not include all the singularities by applying the residue theorem, because then we take into account their contributions by computing the residues here, and actually we also have the expression for these residues. Okay, so once we have the procedure to compute the parameters h, mu, the weights, and the nodes, we may think to apply this procedure directly to the matrix argument A. And actually, I will show you some numerical tests with this parabolic contour integration. The problem here is that, in this case, we cannot apply the residue theorem. So the parabola must enclose all the eigenvalues of the matrix A. And so this approach becomes problematic when eigenvalues are far from the negative real axis because the parabola must be large. So this is an approach, but the other approach is based on the Schur-Parlet method, where now we have this method to compute the Mittag-Leffler scalar function and its derivatives. The problem here is that for general functions f, Davis and Iam propose this criterion to this bound to decide the term m to stop the Taylor series expansion. And the problem is that this bound here depends on the derivatives of the function f up to the order m plus ni minus 1, where ni is the dimension of the block TII we are considering. So when the spectrum of the matrix, when the eigenvalues of the original matrix A are clustered, this approach becomes prohibitively expensive and highly inaccurate because we have to compute a lot of derivatives, and this process may be inaccurate also because especially if we consider f that are not as simple as the exponential or the trigonometric functions. And so for the Mittag-Leffler functions, this is an issue, and we will see the consequences on the numerical tests. Okay, so now to test these procedures, I consider these matrix arguments of large dimension with small rank or fast decaying singular values and sparse, which are very common in the applications. The starting point is were actually these 2 matrices. This is just an academic exercise, but for us it was very interesting because these matrices capture the more important features of the problem. So we have B1 and B2, which are 600 times 600 matrices. They have the eigenvalue 0 with multiplicity 566, 30 eigenvalues in the interval -1, 0, 8, and then the matrix B1 has these 4 complex conjugate eigenvalues, which are close to the negative real axis, while B2 here, as it is a term 25, which means that actually these 4 eigenvalues are quite far from the negative real axis. And this will be a key feature because here, okay, we compute the Mittag-Leffler function for these 2 matrices, B1 and B2, by considering the complex contour integration applied directly to these matrix arguments and the Schur-Parlet algorithm. Okay, we tested several values of alpha and beta. What we may see here is that the Schur-Parlet method has always a good accuracy but large computation time. While here, for the complex contour integration, this approach works well for B1 but not for B2. The reason is that the matrix B2 requires a very large parabola. And so actually we have these parameters mu, which influences the round of error, and so the errors are large. So to reduce the dimension of the problem, we have considered this method proposed by Stewart, which approximates the matrix A by these 3 factors, x, t, and y transpose. The idea is to take x as a subset of columns of A, y as a subset of rows of A, in such a way that we preserve the sparsity of the matrix argument A. And then we have this square block T, and these factors are chosen in such a way that this Frobenius norm is minimized. The interesting factor here is that this matrix T now is a square and has dimension R times R, where R is at most the numerical rank of the matrix A. And so if the rank is small, actually we have a reduction from N to R, which is much smaller than N. Another important fact is that actually we may choose the accuracy we want because this procedure is able to find the value for R and the matrix T such that this bound holds. An important theorem that we have found in this context allows us to reduce the difficulty of the problem because we may approximate the Mittag-Leffler of the matrix A by means of the Mittag-Leffler function evaluated in this matrix Z, which has just dimension R times R. So this is an important result because actually we reduce the dimension of the problem. We see here that the second parameter is different, but it's not a problem for us because our procedure works for any alpha and beta. And this is also interesting in all of those situations, for example, in the context of generalized exponential integrators, in which we need to compute several factors of this time. In this case, we just compute the SCRA once, and then we repeat this computation, but just for a very small argument, tau z. Okay, so just some numerical examples to give you an idea of the results that we obtain. We see that by using the complex contour integration for the matrices B1 and B2 I described before, we see that the SCRA approximation has always the smaller CPU time. And the reduction is important, especially if you think that computations of this form are required several times, while you just compute the SCRA once. Another important, interesting feature is the fact that we maintain the accuracy. So actually this SCRA, even here, that we have a reduction from a problem of 600 times 600 to a problem of dimension 34, the errors are of the same order here. For the complex contour integration applied to the matrix B2, obviously we cannot improve the accuracy because the matrix, the SCRA approximation has the same eigenvalue distribution of the matrix itself, but in any case, the time is much faster. And if we consider Schur-Parlet, in this case, we maintain the same small errors with a noticeable gain in terms of CPU time. The last example is a matrix from a multigraph for a multigraph. It has dimension 953 with numerical rank 155. We have computed the Mittag-Leffler function for this matrix with the parabolic contour and the Schur-Parlette. And what we see that the time of the scra is always much smaller than the other case. In particular here, for this special, for alpha equals 0.5 and beta equal 1.5, with the full matrix, we had to stop the procedure because the time was too large and nothing happened, while here in much smaller time, we have the result with a very good accuracy with respect to a reference solution computed in Maple. Okay, thank you.
Bene, grazie a Marina Popolizio. C'è tempo per una domanda prima del break, dove ognuno avrà modo anche di fare più domande a quelli che hanno parlato. Domande? Just a little question. You made the assumption of a matrix with at least a numerical smaller rank. Any idea on how to extend the approach to rank structures? Maybe it is a difficult
yeah,
question.
We can think about this case. No, we don't have worked on it.
What happens if the rank is too high in your approach?
You cannot reduce the dimension of the problem. You have to take a matrix which has a similar dimension to the original matrix, so probably you don't have nothing. You don't have a gain, saving in time and approximation.
Okay, thank you. Thank you again to Marina Popolizio e ringraziamo tutti gli speaker di questa prima sessione. Riprendiamo alle 11 in punto, giusto?
Allora c'è un coffee break su questo piano, trovate il cartello per la sala e poi appunto come ha detto Fabio riprendiamo alle 11, ci sarà il keynote talk di Michele Benzi. Va bene? Grazie. Come? Scusa? Sì, penso per lasciare noi accostiamo le porte. Magari giusto non succede niente, se qualcuno ha effetti personali, borsa, eccetera, leggeri, li può portare. Va benissimo. Sopra i 10.000, noi accettiamo offerte, va bene?
Va bene, penso. Ciao Stefano. Ciao. Tutto bene? Allora, in realtà noi... Tu sei oggi pomeriggio, giusto?
Sì.
Te le apriamo già tutte in,
Okay, sì.
tutte in Acrobat, quindi devi solo mandarle in play.
Sì. Okay.
Come quelle di stamattina.
Va bene.
C'è il pointer e purtroppo c'è la condivisione Zoom sempre attiva perché infatti anche in questo momento siamo in riunione. Io metto... Sì. Il problema è che noi non abbiamo sempre il feedback lì perché mettono la regia e quindi non abbiamo notato questa cosa. In questo momento... Allora, intanto volevo mettere il programma, poi Benzi...
Eccolo qua. E vuoi condividere questo?
Allora, proviamo. Ok. Faccio. Solo che là dobbiamo avere feedback. Ciao Sandro, ciao, come va? Tutto bene. Sei tornato o già stavi qua? Sei tornato per il convegno, quindi praticamente. Hai colto l'occasione, hai fatto.
Esatto. Questo è.
Dovrebbe dare fastidio. Capito.
Questa qua ancora rompe le scatole, ma questa non so come devo. In teoria sparisce sempre da sola, però non si è capito. Pure l'altra volta ci ha fatto lo stesso. Sì.
Ma dà poco fastidio perché tanto in alto.
Sopra in genere si testazioni, cose.
Sì, però cioè in basso a volte c'è anche la numerazione delle slide che aiuta insomma a seguire.
Sì, no, esatto.
A che punto è.
Uno si fa un attimo un'idea.
Pausa perché tu l'hai messo da parte?
Non lo so perché
in
pausa.
Forse quando abbassi la finestra va in pausa, vedi?
Sì, ok. Vabbè.
Anche se io così da lontano però non vedo, cioè nella riunione Zoom non vedo se c'è un.
Vabbè, qua non vediamo, quindi. Ma è solo per tanto i partecipanti online. Madonna. Allora. Mo faccio la condivisione di tutto lo schermo, dai. Tanto la barra di Windows ho tolta di mezzo. No, ma faccio schermo, guarda. Così stiamo tranquilli e non scompare. Tanto la barra l'abbiamo rimossa. Questo
La barra non compare più, va bene così.
Allora, in questo momento io vedo tutto senza la barra.
Il problema è solo questa, che
Quella
continua a disturbare. Questa qua in teoria si può
Nascondere controlli di
nascondere.
riunioni mobili, però l'abbiamo fatto prima. E poi vai su col qua per farlo ricomparire?
In teoria basta premere Alt, però ovviamente.
Si è accavallato il basso con Zoom e gli alt non funzionano bene più, gli alt delle scorciatoie. Cioè possiamo, sì,
Ah, premendo
puoi
ESC.
scaricare da Zoom.
Premendo
No, perché
ESC.
la riunione sta qua.
No, però ho capito, se tu la nascondi con ESC più o meno. Ctrl Alt Shift H, madonna.
No, però premere ESC per non entrare nei comandi. Quindi quando tu la nascondi e la lasci nascosta, ogni volta si deve fare quello. Dovrebbe essere da solo. Prima se ne andava da solo, quindi fai una cosa, chiudi Zoom. Perché io tanto la riunione la tengo attiva sul. Ok, usciamo dalla riunione e lo riavviamo. Grazie.
Ah, grazie. Giovanni.
Lui,
se
vuoi fare cose
Sì, no, infatti, no, lo ringrazio. No, però una bottiglia d'acqua.
No, però allora quello è un box separato, quindi comunica con uno di gli altri e portarsi fuori.
Ma tutti i giorni faccio questo. A pranzo siamo prima. A pranzo ci sta.
Proprio il box lunch, cioè quello di fare.
Ti prendo quello del pranzo, vi ringrazio, troppo gentile.
A pranzo ci facciamo pure male, quindi se sei a dieta. Allora, dov'è? Lo devo trovare il link però.
Allora, qua già ci sta.
No?
Quello è solo Zoom, no?
Aspetta.
Puoi andare giù. No, in realtà no, qua c'è proprio un link, c'è messo un link. Ma se n'è andato da solo là? Hanno cambiato l'istruzione, perché io la stampante la tenevo sulle pietre per non farla vedere. Quindi la devo spostare.
Beh, mi fai. Mentre mangio cioccolato in un locale. L'ho visto. Madonna.
Infatti uno mi ha chiesto oggi dall'Africa come si fa la pista, io l'ho detto che non è lingua di tutto, senza
Noi chiediamo.
poi ho fatto collegare due cose nella casa, io ho collegato, dovevo montare come la rete, quindi tutto sempre. Ma quello è il fatto che dopo rimane là forse registrato, quindi contano anche esercizi totali dopo, cioè nel senso che è un link che fa un po' di tutto, io l'avevo sulla base del servizio. Allora, non te ne vado solo? No. No, l'altro giorno se ne vado su.
Ci dobbiamo andare a
E noi
prendere...
l'abbiamo spostato e poi l'abbiamo rimesso.
Dobbiamo prendere un paio di box. Io non ho preso niente, quindi devo mangiare qualcosa se non svengo quando parlo.
Tu devi pure parlare. Quindi se andiamo a prendere il box, ce lo portiamo, ce lo dobbiamo capire sempre poi. Andiamo sempre a mangiare qualcosa. Però facciamo una cosa, mettiamo un Benzi, vai, avviati. Io vengo con Benzi anche tra gli altri aperti. Tutti aperti, tutte le edizioni. Sì, l'ho visto.
Fabrizio si buttava il bristolo apposta. Fabrizio, io alzo le mani, Fabrizio sapeva esattamente ogni aula, a seconda del periodo dell'anno e dell'orario del giorno, quanti Kelvin aveva essere.
Vai Valentina. No, non lo so, glielo dobbiamo dire forse mentre... Quando...
No, no. Sì, prova. Sì, ok. Sì, va bene. Quello è il puntatore, ok. No, era perché se guardo un po' là, era solo...
Anche la regia oggi ogni tanto cambia, quindi qua c'hai sempre le tue slide, là ogni tanto invece vedi la sala.
Sì, si vede un'altra roba.
Lo fanno, lo controlla qualcun altro questo. Okay.
Perché oggi siamo in diretta sul canale di YouTube dell'Ateneo e quindi c'è una regia esterna.
Sì, ho capito. Questo per farlo sparire basta cliccare sul primo.
Io non sono pratico di Zoom, sul primo nasconde.
Io ho un problema, un mezzo cieco, ho bisogno di occhiali sia per vedere da vicino che vado a prendere.
Beh, puoi guardare lo schermo.
Sono le 11 esatte. Benvenuti alla sessione dove ho da introdurre il keynote speaker. È per me un grande piacere, un grande onore introdurre Michele Benzi, e se volessi fare un'introduzione adeguata avrei bisogno di 40-45 minuti, quindi toglierei tutto il tempo a Michele per parlare, quindi devo essere molto sintetico. Michele è professore, full professor alla Scuola Normale Superiore di Pisa, è stato, non so se è ancora la posizione alla Emory University, no, l'è abbandonata, Samuel Candler Todds Professor. In passato ha ricoperto posizioni all'Università di Bologna, al Fairfax di Tolosa e poi al Los Alamos National Laboratories. Michele ha un ruolo importante nell'editoria come editor di moltissime riviste internazionali e ricopre il ruolo di editor in chief di SciMax, la rivista più prestigiosa dell'analisi di matrici e delle applicazioni. È fellow dell'American Mathematical Society e del SciAM. È membro dell'Accademia Europea. Michele ha avuto tanti studenti e vi siete resi conto già stamani che ha ancora tanti studenti e quindi alla comunità darà tantissimo negli anni a venire, crescendo nuove generazioni di giovani brillanti. Che dire, Michele è un punto di riferimento per tutta l'analisi numerica italiana e internazionale. Mi fa molto piacere che sia qua a raccontarci cose molto interessanti e importanti. Una cosa che non ho detto, perché naturalmente tutti noi conosciamo i lavori di Michele nel settore dell'algebra lineare numerica e dell'analisi numerica in generale, però Michele ha prodotto importanti lavori di ricerca storica sull'analisi numerica, sull'algebra lineare numerica, specialmente in Italia, che sono molto molto interessanti. E Michele, ti passo la parola. Naturalmente ora il titolo del talk l'avete visto lo vedete adesso nelle slide.
Well, thank you, Dario, for the very kind introduction. Thanks to the whole scientific committee for inviting me to give this keynote address. And also many thanks to the organizing committee for the excellent organizational work. So today I want to talk about solution of a class of linear systems that present some difficulties, some challenges, and that I keep running into. If anyone has a suggestion for a name, I had to write a formula in the title, which I never do usually, but somebody has a suggestion for this type of linear systems, I'll be happy to hear it. So first I will give motivation. Like I said, this type of linear systems arise in many different areas of the numerical analysis and optimization. Then I will describe the preconditioning technique to be used for solving these linear systems that we're investigating. This is still work in progress, so I should say. Some possible variant of this preconditioning idea. A little bit of theory, mostly some eigenvalue bounds for the preconditioned matrices. And then I'll show you some numerical experiments and conclusions. This is joint work with my student Chiara Faccio of Scuola Normale, who will also give a presentation in this meeting on a completely different topic, by the way. All right, so we're interested in solving large linear systems of this form. We have matrix A, which has some nice structure. It's sparse or block diagonal or topless or circular, something like that, something that we know how to solve. But then we augment this matrix with typically a rank K matrix, which I write as U transpose multiplied by a parameter gamma, positive. And this matrix U has, again, typically rank K, which is neither too small. It's not like a rank 1 perturbation or rank 2 perturbation, but typically it's something more than that. But it is considerably less than N. In some cases, K may depend on N. In other cases, will be independent of N, depending on the application. A could be singular, but we assume that the sum of A and gamma U transpose is non-singular. Obviously, U transpose is singular. Like I said, there's some desirable property which would be destroyed if we were to form A plus gamma U transpose explicitly. So we want to keep the factors A, U, and U transpose separate. We don't want to multiply U by U transpose, and certainly we do not want to add the result of that to A. So math of X with this matrix can be computed efficiently by doing math of X with U transpose, U, and A. So clearly, if K is not very large, multiplied by U and U transpose is not very expensive, and A will typically be sparse or data sparse or structured in some way such that matrix vector products with A are efficient. So we can use this in an iterative method like conjugate gradients or GMRS. Moreover, in typical applications, these linear systems have to be solved repeatedly. A and U may be both constant. More often, one of the two will change and the other will remain constant. It really depends on the application. I'll see more about this. So this is the setup. Okay, it's not responding. How do I change slide? Fine with the arrow? Okay. So linear systems of this form arise in many settings, like I said. My main motivation initially was the use of augmented Lagrangian type of methods for subtle point problems, in particular for solving the, say, Navier-Stokes equations, the Ozeen problem for the Navier-Stokes equations. But then I realized that the same structure arises in other settings like KKT systems in constraint optimization, interior point methods. I also realized that sparse dense least squares problems fall under this category, and of course tomorrow we will hear much more on this from an expert. Certain types of integral differential equations, solution of PDEs from slightly compressible elasticity, for instance. So there's a variety of situations. Numerical solution of PDEs with, say, an integral boundary condition and so on. So let me say a few words about the augmented Lagrangian method. So we're interested in solving a saddle point problem, for instance, of the kind arising from finite element discretizations of certain systems of PDEs, like the Stokes or Oseen problem, or the couple Stokes-Darcy problem, and so on. So in the last 15 years or so, one methodology that has shown to be very effective for treating this kind of problems is the one based on augmented Lagrangian approach. And it's also, of course, the augmented Lagrangian approach is widely used also in constrained optimization problems, which are not necessarily tied to PDEs. So here's a reference to a paper of mine with Olshansky, where we showed that this approach can work very well for the Oseen system in fluid mechanics. So the idea is to replace the original saddle point problem with a new saddle point problem where the 1-1 block is augmented by adding a certain matrix, which is written there, gamma B transpose W inverse B, where W is a diagonal, positive diagonal matrix, which is typically the diagonal of the pressure mass matrix. This may seem, so of course we need to modify the right-hand side slightly, and then this system has the same solution as the original system. This seems like an odd idea because this looks more complicated than the original saddle point problem. But the advantage of this is that we can precondition this block linear system with a block triangular preconditioner, P sub gamma, which is denoted, which is shown below, where the 2-2 block is just a diagonal scaling operation, and the 1-1 block is the same as the 1-1 block of the augmented system. We will solve this typically with a Krylov subspace method, like flexible GMRAS. And when we apply the inverse of the preconditioner, we need to solve linear systems with this matrix A plus gamma B transpose WB. And this will be done by an iterative method, so inexactly. And this is why we may want to use flexible GMRAS as the outer iteration. So this preconditioner converges very fast, and it's very much robust with respect to parameters like the mesh size and the viscosity, particularly if gamma is taken large. One can show that all the eigenvalues of the precondition matrix tend to 1 for large gamma. However, the prices that we need to pay to solve these linear systems with matrix A plus gamma B transpose W inverse B. This can be done by a multigrid method for certain special choices of discretization and mesh types and so on. But it would be interesting to explore methods that do not rely on properties of the discretization and are more general, and they can be used more algebraically, let's say. So we recognize that the system is of the form A plus gamma U transpose, where U now is this scaled discrete gradient operator, B transpose W to the minus 1/2. For the Stokes problem, A is block diagonal and symmetric positively definite. For the Oseen problem, the matrix is still block diagonal, and it is positive definite in the sense that the symmetric part, A plus A transpose, is. However, if we form explicitly this matrix A plus gamma B transpose W inverse B, we typically pay a price in terms of loss of sparsity and structure. So this matrix is no longer block diagonal, and it tends to be considerably denser than the original matrix. Also, the system can be ill-conditioned. For large gamma, the rank K part dominates, and that is highly singular. So we should expect an ill-conditioned system. So this is the main challenge associated with the augmented Lagrangian approach. How do we solve this ill-conditioned linear system, the condition number of which grows like K, essentially, like gamma, sorry. So we like to have a precondition which is, for the system, which is robust with respect to gamma, or a solver. Here's another example, KKT systems in constrained optimization. when we apply the KKT condition to a function that has been modified, like with a logarithmic barrier term, and we impose the KKT condition, then we solve the nonlinear system with Newton's method, or inexact Newton method to be precise. Then we have to solve a sequence of linear systems with this 3x3 block structure, where H is the Hessian of the objective function, which is typically it's a symmetric matrix, of course. The Jacobian of the constraints is denoted by C. And then we have these diagonal matrices Z and lambda, which are associated with the current values, current in the sense of the current Newton step of the Lagrange multipliers and the slack variables. So these matrices Z and lambda are diagonal, and the entries in them can vary by orders of magnitude. So we can reduce the system first by eliminating the variable, the third variable, the increment to the variable Z, and substituting in the second block of equation. This gives us a 2x2 block linear system, sort of a subtle point problem, this non-symmetric in this case, written in non-symmetric form. Now we can do one more step and eliminate delta lambda and reach the fully reduced system, which is just a Schur complement of this 2x2 block matrix, with matrix H plus C transpose, then a diagonal matrix, the inverse lambda, C. Of course, there's a right-hand side that goes with that. So we can solve for delta x here, and then from that we can readily recover the values of the other variables, lambda and z. So this is also a linear system of the form A plus gamma U transpose, where now A is the Hessian, U is the scaled Jacobian of the gradient of the constraints, essentially, and gamma can be taken to be 1 here. The Hessian is usually positive semi-definite, quite often it's singular. It is typically sparse and may have some structure. Again, if we form explicitly the Schur complement, we typically get a full matrix, or we lose structure anyway. So again, we propose to use this with PCG, or maybe another Krylov method with an algebraic preconditioner that doesn't require forming this matrix explicitly. Sparse dense least squares. Here we have a least squares problem where most of the rows of the rectangular matrix B are sparse, and we permute it so that any dense rows are at the bottom. Okay, so B2 is dense, B1 is sparse. If we write the normal equations, we get the system of the form B1 transpose B1 plus B2 transpose B2. Again, B1 transpose B1 typically sparse, and we don't even have to form the product explicitly if we use this as an iterative method, of course. And B2 transpose B2 will be full and will destroy any sparsity. So we do not want to form this explicitly. We keep it separate. Again, gamma will be 1 here. One more example. There are problems that lead to integral differential equations. So we have a differential operator, for instance, a Laplacian or a convection diffusion operator, plus an integral term, possibly multiplied by some scalar, gamma in this case, which controls the importance of the non-local term versus the local term. And if the kernel of the integral operator, which we assume symmetric here, is sufficiently smooth, then we can approximate it with a degenerate kernel. So a separable kernel approximation with a finite number of terms. So the number of terms in this approximation of the kernel, this could be, say, a Fourier expansion, right? A bivariate Fourier expansion. How many terms we keep depends on the smoothness of the kernel. So how quickly the eigenvalues of the integral operator decay to 0, which again depends on the regularity of the kernel. If we discretize the differential operator with some finite difference or finite element method, and the integral term with some quadrature rule or Galerkin method, and with this approximation, this degenerate kernel approximation, again we get a linear system of this form. A is sparse, is the differential part. U transpose represents the integral term. And again, we would like to be able to solve this efficiently. In this case, the rank K is independent of N. All right, so how do we propose to solve this? So typically we assume again that A is positive semi-definite at least, or its symmetric part, A plus A transpose is positive semi-definite. We assume that the whole system is non-singular, which means that A and U transpose have null spaces, kernels that intersect only at the zero vector. This guarantees that the system is non-singular. If A is non-singular, a tempting thing would be to try using the Sherman-Morrison-Woodbury formula to solve the system, but you cannot apply this to very large-scale problems. The Sherman-Morrison-Woodbury formula tells us that the inverse of A plus gamma U transpose is given by this expression. So this requires 4 applications of A inverse. If the system is very large, we could replace these exact inverses of A with approximate inverses or preconditioner of some kind. So we tried this, and actually the results were not satisfactory, or not as good as the ones we obtained with the method that we'll talk to you later. And also there is the problem that in many applications A is singular, so it's not entirely clear how to apply this. So if K is small, say 10 or less, then any good preconditioner for A, or maybe a slightly shifted version of A, if A is singular, should give good results, right? And for instance, in the symmetric positive definite case, if I precondition the conjugate gradient method with the exact inverse of A, would give a convergence in at most K plus 1 steps because of the rank of the term, U transpose. But if K is in the hundreds or thousands, this is not appealing, of course. So in the preconditioner, we really need to take into account both A and U transpose. We cannot ignore either one of these 2 terms, typically. So the idea is to perform 2 splittings. The first time, so we introduce a positive alpha and split A plus gamma U transpose as the difference of these 2 terms, the shifted A and the rest. But we also perform the reverse splitting in a sense where we shift gamma U transpose and then we put the rest there. So the nice thing is that now both A plus alpha I and alpha I plus gamma U transpose will be invertible. And when, so we could combine this and do an alternating iteration where we alternate with these 2 splittings. And this is similar to some classical methods like the alternating direction implicit method, the Hermitian skew-Hermitian splitting method, the modified HSS method, the relaxed dimensional factorization, the relaxed physical factorization, and other methods that are based on the same principle. So this is not a particularly new idea. But it is new in this context. Okay. So it's easy to show that if the symmetric part of A is positive definite, then this alternating iteration is unconditionally convergent. That is, it converges to the unique solution of the system for any positive alpha and any choice of the initial guess. In practice, however, we probably want to apply this as a preconditioner for a Krylov method rather than as a stationary iterative method, because it will converge much faster and the cost will be only marginally higher. And also, this will allow us to solve those 2 linear systems that we need to solve at each step inexactly instead of exactly, which would be too expensive for many applications. All right, so to derive the preconditioner, we need to eliminate the intermediate variable, x to the xk plus 1/2, and write it as a single step, fixed point iteration. So we have xk plus 1 equal an iteration matrix, the alpha plus some right-hand side. And then we want to write the alpha as the identity minus the precondition matrix, P alpha inverse A. So P alpha inverse is the preconditioner, and it's easy to show, and it follows from general results on alternating method, that the preconditioner is the product of these 2 terms, okay? And then we divide by 1/2 alpha, although this factor is immaterial for preconditioning because it cancels out and it can be ignored. But we will use it in the eigenvalue estimates. So Again, applying this preconditioner will require two solves, one with A plus alpha I and the other with a shifted gamma U transpose matrix. And the hope is that solving these two systems separately is a lot easier than solving the original system with the whole matrix. Let's look at the first piece, A plus alpha I. So if A is sparse or has a nice structure like block diagonal or tuplets, then shifting it by a multiple of the identity does not disturb the structure, preserves it. Some cases, A plus alpha I is simple enough that can be solved inverted exactly. In most cases, we will replace it with a good preconditioner. Notice that shifting A by alpha I makes the matrix more diagonally dominant, so better condition. Not more diagonally dominant, but it shifted the spectrum away from zero, so it's better condition. So we could solve this with maybe a few steps of an inner iteration, like conjugate gradients or multi-grid methods, or we could use simply an incomplete factorization, which is what we do for the most part here. There is a trade-off. Large values of alpha would make solving this scale shifted system easy, but of course the overall performance of the preconditioner could be degraded for large values of alpha. So choice of alpha will be an important factor. Now, experimenting with this method, we observed that whereas we can be fairly inexact with A plus alpha I, we have to be pretty accurate with the second term, alpha I plus gamma U transpose. This matrix will be always symmetric and positive definite, but ill-conditioned for small alpha or for very large gamma. So this one we solve with the Sherman-Morrison-Woodbury formula. So we write the inverse of this matrix, and we find that now, in order to apply the inverse to a vector, we have to multiply with U transpose, not a problem. We have to solve a linear system with matrix alpha ik plus gamma U transpose U, and this is k by k, it's much smaller than n. Multiply by U, then some scalar stuff, and the rest is easy. So the main cost, therefore, of applying this part of the preconditioner is solution of a k by k linear system. And we do this with a Cholesky factorization, possibly with some reordering in the sparse case. And this can be computed once and for all, of course, at the outset. Or maybe we could try an inner iteration, but we haven't tried that yet. For an incompressible flow problem like the Stokes and Nosine problem, this is just a discrete pressure Laplacian that has been shifted. So it's not a difficult linear system to solve. There are many excellent methods to solve this. Oops. The other nice thing is that if we're solving the Navier-Stokes equation, say by Picard iteration, so a fixed point iteration, the matrix A changes because the convection coefficient changes from step to step of Newton's method, Picard's method, but this matrix here remains constant because the matrix B that expresses the divergence constraint is constant. So this factorization will have to, any preprocessing needed to solve this k by k system will be reusable. And this is also true in the context of KKT system, for instance, if the constraints are linear, so that the Jacobian is constant throughout the Newton method, and also in other cases. All right, one can envision several variances of this. If A is already non-singular and linear systems with A are not too difficult to solve, for instance, because they're well-conditioned, then maybe it's not necessary to shift A. We may get slightly better results, perhaps, by simply having this product preconditioner. However, the underlying stationary iteration will no longer be convergent in general. This may or may not be a problem. In general, we found that shifting is beneficial, so we prefer to shift A. If A is symmetric and positive semi-definite, then the whole problem is symmetric positive definite, and we would like to use CG, not GMRES, say. So in this case, we could try and symmetrize the preconditioner. For example, we could take a Cholesky factorization or an incomplete Cholesky factorization of either A or A plus alpha I, and then symmetrize the preconditioner by writing it in the symmetric form. Now the preconditioner is positive definite and can be used with CG. We tried this, and in general, in some cases it works fine, but we actually found that often it is better not to symmetrize and use GMRS instead, even for symmetric problems. Occasionally, we found that diagonal scaling greatly enhances the quality of the preconditioner. Notice that it's easy to do a diagonal scaling of the matrix because we can easily compute the diagonal entries of this matrix. They're just given by the diagonals of A plus gamma times the norm of the columns of the rows of U squared, essentially. And we can also do this implicitly by slightly modifying the preconditioner and putting the diagonal instead of the identity in the preconditioner. It doesn't matter. It's equivalent. All right. What can we say about eigenvalues of the preconditioned matrix? So for this result, we rescale. We assume that A and U are both scaled so that they have a unit 2 norm. We also assume that the whole matrix is non-singular, as always. And then we can prove the following bound. So, of course, if we assume that A and U are scaled so they have norm 1, then gamma controls the relative size of of the two parts of the matrix. So we can prove that if we have an eigenvalue lambda corresponding to an eigenvector x of the preconditioned matrix, then the real part of this eigenvalue will be between a positive number mu and less than 2. The imaginary part is always less than 1. That's not too important. And so the important thing is this lower bound mu, which is expressed here in terms of alpha, gamma, and the smallest eigenvalue of the symmetric part of A. Clearly, if A is symmetric, this is just 2 alpha lambda min of A. Moreover, if the eigenvector x happens to be in the kernel of U transpose, then the corresponding eigenvalue is given by the expression here at the bottom, and it does not depend on gamma anymore. So we see from this bound that if alpha goes to 0 or gamma grows very large, then the lower bound is close to 0, and the same happens, of course, if the smallest eigenvalue of A plus A transpose goes to 0. So this bound is not terribly satisfactory, but the performance of the method perhaps is better than one would expect. We also note that if A is singular, or A plus A transpose is singular, then the bound doesn't give us any information. It just tells us that the real part is positive, but it could be arbitrarily small, so it's not useful. We can maximize the lower bound very easily. Simple calculus show that taking alpha equals square root of gamma maximizes the upper bound. It would be tempting to use this as the choice of alpha in the preconditioner, but numerical experiments show that we can do much better than that. So it's only a lower bound, right? So, like I said, the lower bound approaches 0 if gamma tends to infinity. So maybe the case of large gamma is challenging. We kind of expect that. And also this result is limited in that it assumes that the preconditioner is applied exactly, which in practice is almost never the case. And of course the usual caveat that this is just an eigenvalue bound, and the convergence of GMRS is not typically, cannot be fully described by the eigenvalues. Well, let's check the accuracy of the bound. So we, in boldface, I put the value square root of gamma for 3 values of gamma, 0.1, 1, and 50, so small, medium, large. And you can ignore the maximum real part, just to make sure that it's less than 2. The minimum real part is the one that should be compared with the lower bound. And we see that the lower bound captures the, can be an order of magnitude off, but it does, it is a lower bound, and that maximizing the lower bound does give somewhat better bound. So this is for a Stokes problem on a 64 by 64 mesh. We do the same thing with the Oseen problem with viscosity 10 to the minus 2. We see that this value is closer to 0 now. It's a harder problem, fact. But we see that the lower bound is quite accurate, for instance, for large gamma. For gamma equal 50, we're quite close. And this is for a sparse, dense least squares problem. The problem is LP fit 2P. And here we see that the lower bound captures quite well the minimum eigenvalue for different values of alpha. Here gamma is 1. And these are not as close to 0. So maybe this problem is not as hard as the Stokes and Oseen problem. And here's another one for a KKT system in optimization. Again, we see that the lower bound captures the behavior of this real part of the eigenvalues of the matrix. All right, let's see some applications in numerical experiments. So I'm going to start with problems from incompressible fluid flow using the IFIS package. So these are two-dimensional Stokes and Oseen problem. The underlying problem is the leaky lid driven cavity problem, which is a standard benchmark in fluid mechanics. We use inexact variance of the proposed preconditioner. The first factor is implemented by an incomplete Cholesky factorization with no fill, so very cheap to compute, very easy, or ILU 0 for a non-symmetric case. The second one we solve exactly, so the inverse of alpha I plus gamma U transpose is done exactly with the Sherman-Morrison Woodbury formula using a Cholesky factorization of the K by K matrix. Here A is block diagonal, and we also found, we're very glad about this, a nice heuristic for the choice of alpha. So this is one of my favorite plots. So this shows the results for a steady 2D Oseen problem. We have alpha on the horizontal axis and the number of GMRS iterations on the vertical axis. And we did a sequence of grids from 32 by 32 to 256 by 256. What we did is we tried to find a good value of alpha for the 32 by 32 grids. We did this experimentally by trying different values of alpha. Now here there is some behavior that I don't quite, there's some instability for very small alpha. This is probably due to the nature of the problem. This is a coarse grid, and it is probably an unstable discretization. But anyway, if we ignore what happens for tiny alpha, we find that a good value of alpha is this minimum here. And then we look at the behavior for finer and finer grids, and the number of iterations decreases with problem size, which is wonderful. And as the mesh is refined, it seems to settle on an asymptotic behavior. And so we looked at how alpha is reduced at the refining of the mesh, and we discovered that it is reduced by a constant factor, which is a square root of 2, magic number. So here's the optimal alpha found experimentally, and this is the corresponding number of iterations. And this is the estimated optimal alpha obtained by dividing by square root of 2 each time we refine the mesh, starting from the 32 by 32 mesh, and this is the number of iterations. So you can see that this rule of thumb, this heuristic, is extremely accurate. So we don't really have a good explanation for this, but it must have to do probably with the behavior of the smallest eigenvalue of the symmetric part of the Oseen operator. So we're very happy for these results. So number of iterations decreases as the problem size increases. It's a dream. This is the number of iterations for different values of gamma for the Oseen problem for different meshes, and we see that there is some variability, but again, as gamma gets larger, the number of iterations seems to become smaller, and this is for two different grids, 64 by 64 and 128 by 128. All right, then we did the 2D Stokes problem, and here we found that it's no longer true that the number of iterations decreases with problem size. For the Stokes problem, the number of iterations does increase with problem size, but the variability with gamma is very much reduced, so it's very robust with respect to gamma. I should also say that with Stokes, we don't use the augmented Lagrangian approach. We use it with the Ozine problem, so this is not such a big deal. All right, let's look at a sparse densely squares problem. So this matrix has 13,000 rows plus 25 dense rows at the bottom. The condition number of the normal equations is pretty high, 10 to the 9th. Yeah, I'm almost finished. We look at the iterations without preconditioning, 174. Then we do the number of iterations preconditioning only with a plus alpha I. And you see that the number of iteration is quite high still. Whereas if we precondition with the product preconditioner, we can get it down to 7 iterations. I have a bunch more of these, but I see that Dario is standing. So this is another sparse dense problem, larger. Again, we can get maybe not as good results here, but still quite good. And also you can see that the symmetrized version is a little bit worse than the unsymmetrized one, because this is with GMRS, this is with CG, so it's 2 different methods. This is a KKT system. No preconditioning does not converge in 2,000 iterations. Preconditioning only with the shifted Hessian, which is singular in this case. Not good. Very fast convergence with the scaling, with the product preconditioner. And this is another KKT system. Unsymmetrized and symmetrized versions. We can get very fast convergence here, like 6 iterations versus, or 14 for the symmetrized one. So it seems to work quite well on these 2 KKT systems. This is an integral differential operator with the Laplacian plus a rank 100 term, dense term. You can see that here the number of iterations with increasing gamma and no preconditioning tends to decrease, which we don't quite understand. But again, we can get good results with the product preconditioner. All right, let me conclude. So we have a new solver for a class of tough linear systems. Seems to work well in practice. We can be very inexact with part of the preconditioner, but then we have to be exact, quite exact with the other. Only K by K solves needed, and much of this work can be done only once and then reused in the course of a calculation. We have a good heuristic for choosing alpha for some important type of PDE problems, and we have a little bit of theory available in the ideal case of exact solves. We need to do some further investigation of the spectrum of the preconditioned matrices. We see clustering in some cases. Can we show anything about that? What about the case of singular A? We don't have any useful bound as of now. Understand better the choice of alpha. Can we solve this shifted rank K matrix by iterative method, for instance? Better ways to precondition the system with CG. And of course, we need to write a paper. So thank you very much.
Thank you, Michele, for your nice talk. Questions?
Michele, thanks a lot for this very nice, very interesting talk. I have many curiosities. We can speak about them later.
Sure.
But just a couple of them here. First, okay, you said that you have usually to solve a sequence of a system like this, as you showed, of course, in your slides. I'm curious to know if you attempted to use any form of update of the preconditioner. I'm thinking about those shifted preconditioners and also the KKT ones, right, because there are techniques that think in terms of update, even if in this case I understood that the term gamma you transpose may be dominating. Okay?
Right, exactly.
So this may be a problem. This is the first question, just a curiosity. The second one is that if you attempted to make any comparison with the preconditioners like constraint preconditioners, right, that are widely used for KKT systems. And of course, the situation is a little bit different if you use systems coming from optimization problems or from PDEs. In my experience, they work much better for optimization. Right. And for PDEs, for example, for the lead-driven cavity flow, my experience is that inside IFIS, there are some specialized preconditioners for that problem, because I made many attempts.
Yeah, I worked for many years on those problems.
So many questions.
So let me start from the end. The augmented Lagrangian preconditioner is much, much faster than any of the preconditioners in IFIS, especially for the difficult problems with small viscosity. This is what we demonstrated already in 2006 with Olshansky. Yes. So in many cases, those preconditions don't converge even. So if the problem is sufficiently convection dominated. So whereas the augmented Lagrangian preconditioner is very robust with respect to viscosity, as we showed. So that's one reason. The problem with our method, of course, is that with the augmented Lagrangian approach is that we have to solve this A plus gamma, B transpose B type of problems, and that's why this problem. With KKT systems, I don't have as much experience. I just wanted to show that even in that context, we can get, you solve very fast convergence, like 6 iterations, 2 iterations, which is promising. Of course, we need to do more experiments. Yeah. The reduced Hessian approach, the null space approach, of course, I know it's popular in optimization, but it's not so easy to construct preconditioners for the reduced Hessian. Yeah. So this is a way that uses the Schur complement reduction and then preconditions the Schur complement, which is alternative to the null space approach.
But you didn't make many attempts to, okay. Okay, we can discuss later.
Yes. Okay.
Thanks a lot.
Thank you again, Michele. And let's go to the speaker again.
Okay, thanks, Michele. And we continue with Marco Viola. Here he is. And he's going to talk about, we continue with the structured linear systems, I guess.
Yes.
The whole session will be on this. Linear algebra and interior point methods for solving L1 regularized optimization problems.
Okay, thanks a lot for the, let me check if this works. Nope. Okay, I will use the computer instead. Thanks a lot for the introduction, and thanks a lot to my fellow organizer for allowing me to present this work today. This is a joint work with two of them, Daniela Serafino and Valentina De Simone, and with Jacek Gonzo and Spiridon Pugakiotis from the University of Edinburgh. So, very fastly, what's the problem we would like to solve? We aim at solving problems of this form in which you look for a sparse or structured solution. And in general, we consider to have a function f which is smooth and convex, and these two regularization terms which may impose some sparsity either on the solution or on some dictionary or some property in the solution. And we will see an example later. And we assume we can have also some linear constraints. And there are many applications for this kind of problems. And for example, portfolio optimization, image processing, classification, image restoration, etc. And in general, in literature, you can find many smart first-order methods which are used to solve these kind of problems, thanks for their very low iteration cost and their ease of implementation. However, we decided to write some sort of apology, defense for second-order methods because it deserves it. Why so? Well, there are some attempts to solve these kind of problems with second-order methods. Of course, as an example, you can have proximal projected Newton methods or semi-smooth Newton methods applied, so combined with augmented Lagrangian approaches. And, but here we are interested in interior point methods. And in particular, we will not do anything strange. And we will do what is done in first-order methods. We will just exploit the sparsity in the solution, and we will try to use a smart linear algebra inside the systems which arise in the interior point methods. So an outline of this talk, I will very fastly introduce interior point methods, then I will show you the interior point proximal method of multipliers. And in our paper, which was recently accepted for publication on SciEM Review, we presented 4 different applications 2 of them have quadratic problems, 2 of them have general convex problems. We don't have time today, so I will just focus on one application. So I will showcase our result by focusing on the image restoration problem. And then I will try to draw some conclusions. So before introducing the interior point methods, just the very, let's say, trivial trick we use in our problems. So whenever you have the absolute value of something, you can write it down as the sum of its positive and its negative parts. So the idea is that if you start from a problem formulated like this and you introduce a new variable imposing a constraint d equal to Lx, then you will have 2 1 norms here, and you can replace them by doubling the number of variables, which is not a problem for an interior point method, and obtaining thus a smooth convex optimization problem, which is now easier to solve. Very fastly, an introduction to interior point methods. We also have seen some of these in the previous interesting keynote talk by Professor Benzi, so we'll try to be fast and concise, more or less. So we suppose that we are in the standard form of a problem, so we have to minimize fx subject to these constraints, so ax equal to b and non-negativity constraints. What interior point methods do, they handle the non-negativity by imposing some logarithmic barriers, and we will see them in a short while. And then we solve a series of barrier problems with Newton method, for example. So more in detail, at each iteration, what we do is we fix a given barrier parameter mu, and then we consider this problem in which we moved the non-negativity constraints to the objective function with the logarithmic barriers, and we apply a Newton step. Now, we made, with some computation you can do, and if you have that yk are the Lagrange multipliers related to the equality constraints, and zeta k the Lagrange multipliers related to the non-negativity constraints, you end up at each iteration with a system, a KKT system, which you need to solve. And solving this KKT system in the most efficient way is the key for the functioning of the interior point methods. So you will see also in that in the one-word block you have this theta minus 1, which we will analyze in a short while, and which depends on the value of xk and the related Lagrange multiplier zeta k. So the augmented system, you can either attach directly the augmented system, or maybe you can resort to some normal equation systems. You can solve with direct methods, you can solve it with iterative methods. The key is that every time you have to be smart and exploit the structure of the problem under analysis. Otherwise, your method will not be as good as or better than first order methods. Some details, well, as mu k goes to 0, nice thing is that the solution of the barrier problems converge to the solution of the original problem, and you can also prove in some cases that you have polynomial convergence with respect to the number of variables. However, as mu tends to 0, the problem becomes ill-conditioned more and more, because in that matrix theta minus 1, you can have either very small or very large elements, and this may lead your condition number to increase. So you need to regularize. How can we regularize the system in interior point methods? Well, of course, the idea is that either we have two chances, or in general, we can apply both of them together. We can apply a dual regularization, just adding a multiple of the identity to the 2-2 block. This allows to avoid singularity in the system. Or we can use primary regularization, so adding a diagonal term in the 1-1 block, which allows us to have eigenvalues bounded from 0. And there is, likely enough, a very natural way to introduce primal and dual regularization in an interior point methods, and it's via the combination of with proximal point methods. So again, suppose that we are in the standard formulation. We just here split variables which were bounded from below, and variables which are free from bounds. And what is the idea? Well, at each iteration k, the proximal method of multipliers considers the proximal penalty function you can see here. You suppose that you have at each iteration zeta k as an approximation of the optimal solution x star and eta k as an approximation of the optimal Lagrange multiplier y star. So you have to solve this kind of problem. The idea behind interior point proximal method of multiplier is to add to this penalty function logarithmic barriers as an interior point, and so solve this, minimize this function with possibly one or more Newton iteration. So if you write down again the optimality condition, applying 1 Newton step, and with some computation you end up with a system which is resemblant to the previous one, and of course here you already find that you have regularized the 1-1 block and the 2-2 block of the system. And the nice thing of this iterative algorithmic regularization is that you recover the solution of the original problem as you go towards convergence, which is quite nice. So, as I said, now I will focus now on a specific application. In particular, just a short introduction, we are interested in the problem of restoring an image corrupted by some blur, and in this case, Poisson noise. A quick overview, you have to recover the W, and you have some measurement G, which are realization of independent random variables with Poisson distribution. And your blur, in general, can be represented by a linear operator, which models your imaging system. And one important assumption we would like to do on this operator is that we assume periodic boundary condition on the operator, which means that D has a BCCB structure, which will be very useful later. And if you apply the maximum likelihood approach, you end up to a formulation in which you have to minimize the so-called Kullback-Leibler divergence, and which has this very nice form here, which, however, leads to a nilpost problem. So you need to add some regularization, and in this case, we consider the anisotropic total variation regularization, which can be represented like this, where L represents finite first-order differences. And then, as a constraint, of course, you have non-negativity constraints because an image is just, each pixel is just counting of photons, and you cannot count negative photons. And you can add also a linear constraint, which is some sort of conservation law, which is just one single linear constraint, but it can be important in some applications. Now, if we apply the nice trick we introduced before, we can double the variables, and we obtain this nice, smooth, convex optimization problem, which now we can address by IPPMM method. So at each step, we end up with a KKT system of this form, which we have to solve. This system may be quite large. For very small images, you can end up with hundreds of thousands of unknowns. And so you have to be smart in its solution. In particular, in this specific case, we address directly the augmented system with a preconditioned minimum residual method. And in particular, as preconditioner, we consider a block diagonal preconditioner of this form, in which you take H tilde K as a diagonal approximation of your 1-1 block. And by exploiting the results in this paper from Bergamaschi and co-authors, you can see that you can also derive for this kind of block diagonal preconditioner some bounds on the eigenvalues of the preconditioned matrix. Now, how can we actually find an approximation in this specific case of the image restoration problem? Well, if we write down again the form of the function of our system, the matrix HK has this form. We observe that the Hessian, in this case of the Kullback-Leibler divergence, can be written like this, where D is the linear operator representing the blur, and UW it's a scaling matrix. And we have a nice thing here. So the system can be very large, but luckily enough, since we suppose BCCB structure, we can use fast Fourier transform to compute matrix vector products. So we don't need to build the full system, and we can work in a Hessian-free manner. And in this case, how can we approximate the term H? Well, you could think about actually computing the diagonal elements of each K, but you should do this at each step, and it means to compute hundreds of thousands of elements at each step, and it may be too costly. Luckily enough, we were lucky enough in finding out these different approximations. So we completely ignore the effect of D, and we just put as a diagonal approximation of the Hessian matrix the scaling matrix, and we of course keep the other parts. And we saw that this in practice performs better than just taking the diagonal elements of the Hessian. Some examples, we consider three 256 by 256 grayscale images. In this specific case, the KKT system you have to solve has 400,000 variables, so quite large. And we decided to compare our IP-PMM implementation with a very famous first-order method, which is the PDAL, primal dual algorithm with line search, which is considered the state-of-the-art for this kind of problems. And you can find more details in the related paper. We compared the two approaches in terms of root mean square error, peak signal to noise ratio, and the MSSIM, which is a structural similarity measure. So here is a plot. Okay, just I forgot a detail. We considered for each of these three different possible blurs: a Gaussian blur, a motion blur, and an out-of-focus blur. So we obtained 9 problems. Here you can see a plot, various plots which compare the performance of IP-PMM with the first-order method in terms of time versus the root mean square error. And it's clear that you can see the blue line corresponds to IP-PMM, and you see that IPMM looks better than the first-order method and faster in some cases in finding a good solution. And not only these solutions are better in terms of root mean square error, but they are also better in terms of the other metrics. And if we take this nice table with all the values, we see that in all the cases we obtain better values with IP-PMM than PDAL. Of course, it does not mean that it will be always better in all the cases, but we were lucky enough to find this, to have these nice results on this problem we selected. And just to give you a visual comparison between the two solutions, the quality of you can see the difference in the quality also by looking at the background, for example, in this cameraman and house image. Here you can find that the solution of the PDAL still has some artifacts here in the sky, so it still needs time to reach a better solution, while the IP-PMM obtained a very smooth background in the images. So this is it. I tried to be as fast as possible for the time constraints we had. We see that, even if not extensively, that if we take interior point methods and we specialize the linear algebra inside these methods, for problems in which we seek sparse solution, we can obtain better solution and more robust algorithms with respect to the standard first-order methods which are used in literature. And of course, there is still work to do. This is just a starting point in this work. We would like to carry on, trying to discover more problems, and of course, trying to improve more and more our methods. For example, we've seen in the previous keynote lecture that when we have KKT system, we can find different ways of solving and address the system with other preconditioner, etc. So there is still, of course, work to do, but the takeout message is second-order methods can be a very good solution if you are able to implement them correctly. And this is it. Thanks a lot. Enjoy your stay in Naples. Thank you.
Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you So once again, this experimental evidence that younger presenters are more on time than experienced presenters. So questions, comments?
Hai sottolineato molto il fatto che ti viene una struttura circolante a blocchi, con blocchi circolanti, utilizzando le condizioni al contorno periodiche. Però ci sono altre condizioni al contorno, come le riflettenti o le antiriflettenti, che portano a strutture matriciali in cui il prodotto matrice-vettore ha lo stesso identico costo, se non forse meno, perché sono reali, della FFT, cioè che usare la FFT. A mio avviso forse, come un suggerimento, magari l'avete già provato, si potrebbero utilizzare queste altre condizioni al contorno che sono più precise all'interno degli schemi di ottimizzazione che avete, perché l'interazione che fate è veramente molto interessante.
Yes, I will reply in English for the others. Yeah, of course. Okay, when you have to define the operator, you have to somehow choose the boundary condition. This was just an example we wanted to give. Of course, with other boundary conditions, you can also find very smart ways to compute the matrix vector product. And of course, the periodic boundary condition can create some troubles on the boundary of the image, because if, for example, the intensity of the image is very different from the bottom to the above part, you can see some strange lines and artifacts on the above part. But of course, when you will have to solve the specific problem, you can use more smarter ways of or different periodic boundary condition and obtain better solution. But this was quite nice still.
We have one more quick question.
So you mentioned using the block diagonal preconditioner with min res.
Yes.
For the KKT, for the saddle point system. Did you show results with that, or did I miss it?
Yeah, we just no. Okay,
can you tell me?
Yeah, we just had a small result on the. You can bound the eigenvalues of the preconditioned matrix.
No, I talk about numeric. I mean, how many iterations does it take? Because you're using a diagonal approximation of the Hessian, which may or may not be good, right?
Well, okay, so you're asking if we more or less compared it with different preconditioners just to, well, actually the number of iterations of the mean res were very low in our experiments. I don't remember now the actual numbers, but less than 10, 20 iterations at each step. Also because in imaging problems, you never have to push too much toward the solution, so this is an advantage also in that case. But more or less, the results we got were quite satisfactory and better than using the standard diagonal approximation.
Okay, I suggest that we stop here and postpone further questions. So we continue with thanks. So we continue with Santolo. Is the accent correct?
Yeah, well, you use that actually to speak in English.
Okay. So stock parameter robust preconditioning for structure, Gaussian iteration applied to Navier-Stokes control. Thank you.
Okay, thank you for the nice introduction, and thank you for giving me the opportunity to be here discussing about this work, and thanks for the organizer for organizing the workshop. So this is a project with my supervisor, John Pearson at the University of Edinburgh, and I will be discussing about parameter robust preconditioning for Gaussian iteration applied to Navier-Stokes control problems. Here there is an overview of what will be the talk. I will be introducing the problem, then I will show you how to derive an approximation of a critical point for the problem, showing optimality condition, the nonlinear iteration and the numerical discretization, and then introducing a little bit of preconditioning for saddle point system, because the system that we are going to solve will be of saddle point structure, and then I will be moving towards the main part of the talk, which is like the proper Navier-Stokes control problems with the Crank-Nicolson in time, showing the discretization, the preconditioning technique, some numerical experiment, and finally I will give you the conclusions. So let's start with the introduction of the problem. Navier-Stokes control problems belongs to the class of optimal control problems with PDE as a constraint. And this can be formulated as a minimization of a cost functional whose constraints are the PDE. From the physical point of view, you have a physical system that you describe with the differential operator D, and you want that the observation, which is called the state V, is close enough to some desired state VD. Of course, you have to add some control U to the system in order to modify it, and since those problems are ill-conditioned, you need also some regularization, and therefore we add a Tikhonov regularization in the functional. Here, the parameter beta is a positive parameter, which is called the regularization parameter, and it is a sort of trade-off between how close you want the solution and the cost that you want to afford in order to achieve it. Indeed, this integral here can be seen as a sort of an energy that you're giving to the system in order to modify it. Those type of problems arise quite often in industrial application. For instance, you want to, let's say, control the phase field separation of two immiscible fluid, or you want to control, you want to optimize the shape of an object, or you want to control a viscous fluid flow, which will be the topic of today. So when you talk about viscous fluid flow, when you're thinking about Navier-Stokes equation. So Navier-Stokes control problem can be defined as a minimization of the cost functional with Navier-Stokes equation as constraints. In this case, we consider time-dependent incompressible Navier-Stokes control. We have the time-space domain is omega times a time interval 0tf. Omega is a subset of Rd, where D is 2 and 3. Then we have the final time tf, and then we have the viscosity mu, which is always positive. And since the problem is clearly nonlinear for the conventional term here, when mu is going to 0, the problem is becoming quite complex to solve. In the following, I will be assumed that initial condition V0 is solenoidal, meaning that it is incompressible. So now what I have to show you is how to obtain a sort of an approximation of the solution. We employed what is called an optimized and discretized strategy. So we write the Lagrangian, we introduce a joint variables zeta and mu, we write the Lagrangian, and then we derive the KKT condition by using the Frechet derivative, which are given by the gradient equation given here, and then we have state equation, and then the adjoint equation. You can see that the system is nonlinear because we have nonlinear term here and nonlinear term here. So in order to find a solution of this problem, we need to linearize it. And we have employed a Nosina iteration, which is given as follows. You suppose that you have approximation of the two velocities and the two pressures. Then you add the decade step of your nonlinear iteration. Then the next approximation is given by the previous one plus a Nosin correction, which is in practice given by the solution of this problem here. Before moving on, I would like you to notice that this is can be seen as a first-order optimality condition of time-dependent, incompressible convection diffusion control problem with the wind defined by our approximation of Decay. Whereas the right-hand side is the nonlinear residual, and it takes, in practice, it's evaluated, the first-order optimality condition evaluated at the current approximation of the solutions. So we have to solve iteratively these type of problems, and when you try to discretize, you have to discretize it, of course. And what we have employed was, in time, was a Crank-Nicholson with a staggered grid for the pressures. And you can see that this is a second-order method in time. So you have the discretization error is of order tau squared plus h squared. And we have also to discretize in space, which is more complex because we have a lot of matrices. We employ Q2, Q1 finite elements discretization, and then we will be working with mass matrices, stiffness matrices, convection matrices, and whenever I have a convection matrix, I will always consider a stabilization matrix. In our test, we use local projection stabilizations. And all those matrices are constructed either on Q1 or Q2 finite elements. And then finally, we have also a negative divergence beam. So now, whenever you discretize the problem, what you obtain is a saddle point problem, a saddle point system. So since we want a fast solution for a fast solver for this type of problem, we have to discuss a little bit about preconditioning for saddle point. Suppose that you have a system of this type here with a 2x2 block given in the slide. Then if we preconditioner this matrix by the block triangular preconditioner P, given here, where S is the so-called Schur complement, then you have that the preconditioned matrix PA minus 1A will have only 1 as an eigenvalue. This is a good starting point because it means that your solver may converge fast. However, I have to mention that the problem that we are going to consider here are not symmetric, and therefore a cluster of eigenvalues is not enough for having fast convergence. Indeed, if you're using min res, for instance, the convergence is also driven by, let's say, the non-normality of the matrix. However, the problem of the preconditioner P is that you have to, at each step of your linear solver, you have to solve with P, which is in practice not practical, and therefore you are trying to, let's say, change the precondition. You are trying to look for a preconditioner P tilde, which is an approximation of this, and you approximate the 1-1 block and the Schur complement by 2 blocks phi tilde and S tilde. In the following, what I will be using is a generalization of what is called a commutator argument. Indeed, I will be working with the block commutator argument for the Schur complement, and it is defined in this way. So suppose that you have what I call a vector gradient grad m, which is defined in this way with the identity matrix in Rm, and then you suppose that you have 2 differential operators D and dP, which have a m by m block structure. Each block on D is defined on the velocity space, and then you have the corresponding Dij P, which is the differential operator on the pressure space, supposing, of course, that each of those is well defined. Then you start supposing that the commutator argument Xi, defined here, is small in some sense. You discretize this expression with your finite element discretization, and working a little bit with linear algebra, you find that if you have something like a vector divergence, something matrix minus 1, a vector divergent transpose, this can be approximated by the following matrix: a block diagonal fnance matrix, the corresponding matrix on the pressure space, and a block diagonal mass matrix. As I said, D and dP are the discretization of the differential operator on the pressure and the velocity space. Now, this is a generalization of the commutator argument presented in this work here. Okay, now let's go to the main part of the talk, which is the preconditioning for Navier-Stokes control problem with Crank-Nicolson in time. Discretizing in time with Crank-Nicolson and eliminating the initial and final time condition on the 2 velocities, what you end up is a saddle point system of this structure with B bar defined as in this way here, and so you can start seeing where I will be using the commutator argument, whereas the 1-1 block is given by the following matrix, and it is not symmetric. The 1-1 block and the 2-2 block is not symmetric indeed, but we will try to make it as close to symmetric as possible, because as I mentioned, the convergence of the iterative method is also it's also driven by the non-normality of the matrix. However, for how far we can try to do that, that will be not possible to have a symmetric matrix, because we have some mismatch on the convection term here and here. So we will have a symmetric matrix only in the Stokes control problem. But in any case, how to symmetrize this matrix is quite easy. We consider a linear transformation T, which is a block diagonal, given by T1, T2, T3, and T4. Each of them is very easy to apply and also to invert, because they are block bidiagonal, and each block is an identity matrix on the velocity or the pressure space. In addition, T1 and T2 and T3 and T4 are one the transpose of the other. So pretty easy to apply, pretty easy to invert. You apply this transformation to the previous system, and what you obtain is, again, a saddle point type of structure. With the 1-1 block, yeah, as I say that it is not symmetric for each k unless you are solving the Stokes control problem. So B2 and B2 are given in slide, and now we have to solve a system with this type of matrix at each Osine iteration. we want to construct a preconditioner that is robust with respect to all the parameters involved, and we will employ a block triangular preconditioner of this form here, where we have the 1-1 block is an approximation of the inverse of the 1-1 block, and then we have a Schur complement approximation S tilde, where the Schur complement is given in this form here, and you can see there is something that it is easy to invert, and then something that looks like the commutator argument that I've introduced before. So before doing that, I would like to show you how to find an approximation of the 1-1 block. We again invert the 1-1 block employing a preconditioner of a lower triangular form. And the 1-1 block of this block is approximated by this phi tilde here, because you can, let's say, work a little bit linear algebra and see that the 1-1 block can be written as T1 diagonal block with mass matrices on each diagonal, and then T1 transpose. And then the Schur complement is approximated in this form here. I don't want to go too much in the detail, but we have employed what is called the matching strategy, and this is a generalization of the preconditioner that we derived in this paper here. And the M hat, the matrix M hat, is again a block bidiagonal matrix given here. The main problem in this preconditioner is in practice how to invert the matrices C2 plus M hat and C1 plus M hat. And I will tell you later about how to do that. So now we want to just discuss how to approximate the Schur complement. As I mentioned, we want to apply a block commutator argument. And indeed, the first part is, which is the easiest part, we leave it as it is. And then the one that had block, let's say, vectorial divergence, we approximated it with the commutator argument. So we have block diagonal stiffness matrix, the corresponding discretization on the pressure space, and then block diagonal mass matrix. So it is quite easy to apply, quite easy to invert. And just before moving on to the numerical experiment, I would like to tell you how to apply the preconditioner, because I've mentioned that we invert 1-1 block with the block triangular preconditioner for convection diffusion control, and we employ that in preconditioner GMRES. The only problem of that 1-1 block was the Schur complement, because we had to invert the C1 and C2 plus the M hat. We do that using block forward and block backward substitution, and we approximate each block on the diagonal with the action of a multigrid, for instance. Then we have also to invert mass matrices, and we do that employing Chebyshev's iteration on the Q2 or Q1 mass matrices, and then all the other blocks are inverted using the action of a multigrid. The problem of this precondition is that you have the 1-1 block which is inverted by a GMRES, and you cannot employ within another GMRES because you are in some sense changing the preconditioner at each iteration, and for this reason we employ the flexible version of the GMRES for solving the whole system. Okay, so with that said, we can go to the numerical experiment. We tested with some level of refinement L and different values of beta, and this is for viscosity 1/100. With the level of refinement L, we divided each interval into 2 to the power of L subinterval. We fixed tau, we fixed tau equal h, and we run the solver. We have the average number of iteration and the average CPU time. You can see that they are quite robust, and the time scales quite linearly. And also we run it for smaller viscosity, again, number of iteration quite constant, and the time scales quite linearly. I have also some plots for the solution at time for the state velocity, the adjoint velocity, and the pressure. And before moving on to the conclusion, I would just like to show an interesting result, which is in practice, when we derived this preconditioner, we were not able to prove any bounds, but when we plotted the eigenvalues, we realized that they are sort of clustered between 0.2 and 1, and they were at the same bounds for the forward Stokes problem. And that was quite interesting. And so, yeah, just a little bit of mentioning that. But now let's go to the conclusion. And let's say that I showed you that we are able to solve optimal control of Navier-Stokes control with Crank-Nicolson in time efficiently. I showed you a potent and flexible commutator argument. Indeed, we were able to solve stationary Navier-Stokes control and in stationary Navier-Stokes control with Bethe-Quad-Euler. We have also a lot of ongoing work and the next thing to do, but let's say that that's all for me, and thank you for your attention.
Okay, we have 1 or 2 minutes for questions. I have a question if no one else has one. So since you're solving in time also, so the columns of your solution vector has blocks that are associated with different time instances.
Well,
so,
to be honest, they can be, let's say, structured as block, but it's only a full vector, let's say, for what I've implemented it.
So you have never checked whether you could save in taking into account that these blocks come from different time instances, so they could be related somehow?
Not really, to be honest. What I was doing is just like taking the whole matrix and then doing matrix vector multiplication and then employing the preconditioner. Nothing like, I don't know, probably you have something like a Kronecker product in your mind, and I haven't tried that.
Okay.
So everything is done, let's say, exactly, nothing with approximations, at least so far.
Okay. Oh, there is some literature on this. Okay. More questions? Okay, we thank the speaker once again. We conclude this session with Andrea Franceschini. Oh, right. So, if someone, do I have to? No, I'm not supposed to. So there is a technician who can do this. Okay, so they're supposed to do it. Here is the expert. Okay, is Andrea Franceschini, class. A reverse constraint preconditioner for saddle point matrices in contact mechanics. Thanks, please.
Thank you everyone for the organization. I'm Andrea Franceschini, and I will present you a joint work with Matteo Frigo, Carlo Ianna, and Massimiliano Ferronato. This is a brief outline of the presentation. After the introduction and the problem statement, I will introduce the block Jacobian that we are going to tackle, the proposed preconditioner, some analysis and comparison with other approaches, and I will draw few conclusions. So, just a let's say overview of the reason behind the choice of our problem. In nature, flow structures are very important in several subsurface systems, and they are responsible of microseismicity, fluid leakage, fault reactivation, and other phenomena. And it's very important to be able to handle large simulation with fault and fracture to model these phenomena. Our approach, our model, is to discretize a 3D body and a series of fractures as internal boundaries, where we impose the constraint using Lagrangian multipliers. This is just the contact problem that we want to solve. The set of the equations that we are going to solve are the classical linear momentum balance, subject to the contact constraints that are essentially the impenetrability and the friction Coulomb criterion. And here I reported also the weak form. We can immediately recognize that this will will create a saddle point problem because we have a mediation, if you want, with a constraint. Indeed, if we write the discretized version of the residual and the Jacobian matrix, we can immediately recognize that this is a saddle problem. The matrix is as a two-block structure with A, the classical stiffness matrix, if you want, in the structural mechanics. That is usually this is an SPD matrix, and here in this study it is assumed as a metric positive definite matrix. B1 and B2 are two coupling blocks between the primary variable displacement and traction. That is the physical representation of the Lagrange multipliers. And finally, we have a null block, the 2x2 null block. Our objective is to present an effective preconditioner for this kind of problem, so a saddle point problem with this 2x2 structure. In general, the Jacobian matrix is non-symmetric for this problem, but we observe that the coupling blocks can be written as, let's say, a small variation of the, where the small variation is quite small and for the preconditioning purposes can be neglected. So we can efficiently preconditioner the symmetrized version and apply this preconditioner to the original version of the matrix. The convergence properties will not change. There are several possibilities as choices for the finite element space for this problem. For example, we can use a Q1 finite element discretization for the displacement field, and the Lagrange multipliers that represent the tractions can be represented as a P0 node-based field. And in this case, the Jacobian matrix is actually what we saw, so with a 0 2x2 block. Instead, if we use a self-centered P0 field, we need to add a stabilization because this approach is not inf-sub stable. So instead of the 0 block, we will have something, a sort of, you can imagine, a sort of diagonal matrix. Okay, the usual way to build a preconditioner is to write a block LDU factorization, where we can recognize the classical L, D, and U factors. And the main issues are that the Schur complement matrix appearing here has to be computed using the inverse of A, the stiffness matrix, and usually the inverse of A is dense. Assuming that a sparse S is available so that we can somehow compute a sparse approximation of the Schur complement, there is no trivial tools to precondition this matrix. And moreover, A has to be a regular matrix because you can see that in places A minus 1 appears. So we need to be able to compute A minus 1. Instead, in several problems, you can imagine that we have two blocks, two bodies, and just one of them is constrained by Dirichlet conditions. The other is constrained just by contact conditions. So it is associated with a singular leading block. So the idea is to reverse the factorization. So instead of computing the Schur complement with respect to the traction, if you want, to the second variable, we compute it with respect to the first variable. So to do this, we need a non-zero 2x2 block. So this is available when the stabilization is added, so when the original discretization is not stable, but in general is not available. So to be able to provide a general way to build this C matrix that is introduced here in the first A hat, we have C matrix. This C matrix is a sort of, can be seen as a sort of augmentation matrix that allows us to write this UD factorization. So we can write the inverse, if you want, a reverse factorization, and that's why the name of reverse in the title of the book, the reverse factorization. where SU now is the so-called primary Schur complement, so computed against the first variable. And this is quite similar to what Michele Benzi already presented us a few talks ago. And we can prove that if A and A tilde are the above saddle point matrices defined above, so A, the original without, let's say, the 2x2 block, with a 2x2 block. Instead, A hat is the matrix with the minus C. And C is chosen as B transpose A minus 1, so the original Schur complement associated to that matrix. The eigenvalues of the preconditioned matrix A at minus 1A are either 1, 0.5. And this is very interesting because, of course, this is an ideal case, but we have a very optimal result in the sense that at most iteration we are able to solve any matrix of this form. And now it's enough to build a cheap approximation for this C matrix. The result holds for C that is defined as B transpose A minus 1, sorry, B. But we say that A minus 1 we cannot complete, so we need to find a cheap approximation. The idea is to start from the classical augmentation matrix that is a scalar factor with the identity, where the scalar factor is a proper ratio between norms of coupling and leading block. Here we propose a local definition of the scalar factor that is, let's say, it's not anymore a scalar, it's the outcome is a diagonal matrix where any entry is computed as the square of the 2 norm of the row of the column of the matrix B, and the 2 norm of the, let's say, the gathered small matrix A associated to the non-zeros of our column B. It turns out that the eigenvalues of the stabilization matrix, when it's present, are very close to those of the optimal C. So we can use the matrix that we provide in this way, so the local augmentation matrix, or the stabilization arising from the discretization itself. Because it can be proved that, at least in the cases that we analyzed, they are quite close in a spectral sense. So now we can complete our definition in the sense that we can build our preconditioner where we have the triangular factors that can be applied exactly and the diagonal matrix in between them that has to be approximated. Now C to minus 1 can be completely 3 because it's a diagonal matrix, we choose it, we build it, so it's very easy to invert it. And SU minus 1 is a Schur complement, it's a primary Schur complement, and it can be proved that for this kind of problem, it's very similar to the original stiffness matrix. So any effective method already available to solve structural problems can be used to approximate this Schur complement. In particular, algebraic multigrid, for example, GMG from Pezzi or Kronos from a work from Janna and co-authors. We also proved some theorems to, let's say, to the eigenvalues, and here we have a set of definitions, but they are not so interesting right now. The more interesting are the applications. If we apply these bounds to a very simple problem, when we use the exact in of the Schur complement, we obtain the eigenvalues plotted on the left. We have only real eigenvalues and they are quite compact to 1, let's say from 0.3 to 1. On the other side, we have an approximate version of the inverse. So we use an AMG, inverse of the primary Schur complement, and we see that a small imaginary part arise, and essentially the real eigenvalues are more or less the same as in the original case. Just few results. to show how the proposed argumentation affect the conditioning. We analyze three cases. We present three cases. In the first one, we have a singular leading block, in the sense that only one of the two portions is the constraint, the boundary condition, and the other one is, if you want, floating, constrained only by the fracture surface, the contact surface. In the other one, we use, instead of a classical node-to-node, we use a node-to-surface contact model. And in the last one, we go back to the node-to-node surface, but we increase as much as we can the number of contact surfaces. So the ratio between, if you want, the second variable and the first one, we want a large size for the second block. And here we have some results. We can see that first we compare the saddle point solution with the stiffness matrix, so the leading block solution only. The second solution is the dashed line, the leading block solution is the continuous line. First of all, we have that in the first case, we cannot solve the leading block because it's singular, so we cannot do any comparison, but the saddle point system solve at all, it requires 16 iterations. Here we use a right preconditioner GMRS. In the second case, we have that the saddle point problem is slightly more difficult than the original leading block problem in the original stiffness matrix. Indeed, it requires, let's say, 15 iterations more. But the most interesting case is the last one, where we move from the 250 iterations for the original stiffness problem to less than 100 for the overall saddle point problem, that is or less larger twice, because the last case is the case with more fracture unknowns. And finally, we compare our approach with, let's say, the classical way to build a preconditioner for this kind of problems, to compute the sure complement in the original way using A-1. So the one that we saw, that we said sometimes can be used because A-1 is too heavy to be computed. Indeed, here we approximate, we replace A-1 with a factor Parkes approximate inverse. So we compare our approach, RACP, reverse augmented constant preconditioner, with the mixed constant preconditioner, whereas kernel, internal kernel, for the stiffness matrix, we use either an AMG or FSI, so same approximation used to compute the sure complement. In this case, we can see that the first case, the floating side, the one with the singular leading block, cannot even be by the other two approaches. While the other two cases, we have that the novel approach is much more convenient, both in terms of iteration and application costs. Here, the application cost is just, if you want, an indication, in the sense that it's the number of floating point operation required to apply the preconditioner with respect to the matrix vector product with the original matrix. So just a rough indication is that the RACP costs 4 times, more or less 4 times, with respect to the original saddle point matrix times a vector. Other cases, the costs are very different, but the overall number of iterations is higher. So it's a quite effective approach. Finally, we want, here we show some theoretical properties, so the mesh independence. We take a simple case, we refine it several times, and we can see that there are there's essentially no dependence on the mesh size. The convergence, the number of iterations are constant with respect to the refined parameter. And the strong scalability, we took a very large case. We are talking about 73 million of unknowns as prime variable and 10 million of unknowns as Lagrange multipliers. And we solve it with several number of cores and processes. just to show that essentially the number of iterations, the setup time and solve time more or less remains constant up to 255 cores. The same for the same, we run also a strong scalability study, simply using more processes, more resources, and we can see that the solution solve the setup and solution times are quite close to the ideal behavior. So, to conclude, we presented double preconditioner for saddle point matrices, the reverse augmented constant preconditioner, and it has it's based on optimal augmentation matrix, several bounds, eigenvalue bounds, even if not presented here for the limit on times, can be proved and are quite useful indication to build this augmentation matrix. The proposed preconditioner is able to effectively solve problems with a singular leading block, and when the leading block is non-singular, we have sometimes an improvement on the conditioning number with respect to the leading block itself. And finally, several results we proved the algorithmic weak scalability and the overall performances of our approach. Will be done in the future more extensive experimentation to other cases arising from other discretization, other approaches, the implementation in a fully simulator, and testing on different let's say on problem using Lagrange multipliers different from the contact problems. And that's all.
Thank you.
Thank you.
Questions? I have a curiosity rather than a question. It's about the Marconi 100. Is the one at Sineca, I guess.
Yeah. Yes. It's the
standard,
one of the best compute.
The best computer. Well, the one available at Sineca, I guess.
Yeah. It's from China.
Okay. So are there questions online? It's just impossible to check whether there are questions online. Okay, very good. Thank you. So if there are no further questions, we thank all the speakers of the session and have a lunch break.
Ci sono le cartelle organizzate per sessioni e quindi noi la mettiamo già là, apriamo già tutto il biglietto della sessione. Allora, vediamo un attimo, posso continuare. Quindi forse è andata in spam la mail di 2 giorni fa, perché noi abbiamo, no, noi abbiamo inviato una mail un paio di giorni fa con le indicazioni. Allora, vediamo, importanti, informazioni per i partecipanti. Ok, eccolo qua. Allora, vediamo. Fabio Marcucci, unici D, cerca i destinatari, quindi sarà finita nel spam. Però la rinvio. Ho fatto lo stesso con... Sì, sì, allora faccio inoltre. Perfetto, grazie. Grazie, va bene. Ecco, siamo già in riunione Zoom. Voglio vedere se sta... Allora, vediamo. Salve.
Volevo chiedervi, non si può fare la mattina con
Michele per esempio l'ha abbassata prima, secondo me si sta lontano. C'è il puntatore? Sì. Se serve? viaggiavamo su queste ferie e poi abbiamo fatto... Allora, sì, anche se l'animo dallo slide, solo per non fare. Quindi dopo aver parlato eventualmente... Va bene. A parte che c'è pure un microfono di però... Sì, l'unica raccomandazione è che parlare vicino al microfono, perché dalla sala e a casa si sente meglio se uno sta non troppo lontano.
Va bene. Ho visto. Volentieri. Grazie. Va bene, aspettiamo. Va bene. Velocemente. Benissimo.
Non ne ho bisogno. Ah, scusate. Ok. Okay, so welcome to this first afternoon session. I am very pleased to see a session about the intersection of linear algebra and Cauchy problems, numerical methods for differential equations. And the first speaker is Davide Palitta, who is a researcher at the University of Bologna after long travels. And he will speak about parallelization of backward differentiation formulas, joint work with Martin Geiger. I look forward.
Thank you, Nicola, for the introduction. And yeah, so I'm going to talk about a joint work with Martin Gander from Geneva, and actually we have some still preliminary results about the use of part of the YAG, that is a parallel in time framework, when we want to adopt BDF as time integrator. But let's start from our first from the continuous problem. So we have this evolutionary PDE where L is any linear differential operator involving all these space derivatives. And if we discretize this problem with an all-at-once approach, so meaning we discretize at the same time both in space and time, we end up with this linear system here. This is the Kronecker product. B is L times L, where L is the number of time steps, and so B represents the discrete time operator. K and M are n times n, so where n is the total number of degrees of freedom in space, so these are the stiffness and mass metrics, saying we're using a finite element method for this discretization in time. And U and F, these long vectors n times L, can be seen as the vectorized form of these matrices here, where, for instance, here, UI represent the approximation computed at time ti, while Fi will collect the source term and the boundary conditions at time ti. So the idea behind part of the YAG, that again is a quite peculiar framework for parallel in time algorithms, the idea behind this is quite straightforward. So basically, we just want to diagonalize the time operator B. And so the original problem is written in this form here. We perform a transformation based on the eigenvector matrix of B, here, getting U tilde and F tilde, and then we are left with solving this block diagonal linear system here. And since this is block diagonal, we can parallelize the solution of H blocks. And this is basically the parallel in time step that we have. Once we have U tilde, we transform back and we get the original solution U. So very, very easy, but of course everything here relies on the diagonalization of B. So what happens when we cannot compute the eigendecomposition of B? For instance, maybe we adopt a time integrator that leads to a B that is not diagonalizable, or maybe L is too large, so we cannot compute explicitly the eigendecomposition of B. So today we're going to focus on this scenario here because that's exactly what happens when we adopt BDFs as time integrator. So BDFs are a family of time integrators, backward differentiation formulas, and for an initial value problem like this, a BDF of order S can be written in this form here, where tau is the time step size, Ti is the ith time step, alpha, I, and beta are the coefficients defining the BDF of order S. They are known. You can find them in books, so very easy. And you can see here that the approximation at time Tn builds upon the approximation that we have computed at the previous S time steps. So BDFs are an implicit method. They work particularly well for stiff problems. They are stable for order S less or equal than 6, while it has been shown that they are not stable for S greater than 6. But today we're going to focus on S equal to 1. But before that, I want to show you the matrix B that we get for a BDF of order S. So we have 1s on the main diagonal, and on the sub-diagonals we have the coefficients alphas. So of course this matrix is not diagonalizable because this is basically a Jordan block. So again, as I said before, today we're going to focus on S equal to 1, and a BDF of order 1 is just backward Euler. And this is the matrix that we get, the matrix B that we get. So what people did to try to overcome the fact that this B is not diagonalizable, basically the strategies in the literature are divided into two groups. First, we try to transform B a little. For instance, here in these papers, Madej, Ronquist, but also Martin and others, instead of using a uniform time step size, they try to use a different time step size at each time step Tj, getting this B here. And this is now diagonalizable. But the problem here is that the eigenvector matrix of this B here has a huge condition number that increases very rapidly with L, the dimension. And so the solution process, the parallel in time process, solution process becomes very, very unstable. Another approach that is pretty recent by Liu and others is to try to use like hybrid time discretization methods. So for instance, here you have the second order formula for all the time steps but the last one. At the last time step, you go back to backward Euler. And for this matrix, everything is fine, but this approach is not very flexible because you need to use this discretization in time. Why we would like to have something that works well for, like, say, a class of time integrators. The second approach is to try to solve the all-at-once approach by an iterative method and confine the parallel in time step to the preconditioning step only. So we use, for instance, GMRAS here, and then we use as a preconditioner something of this form, where C is let's say, a diagonalizable approximation to B, so that P inverse can be computed in parallel. So Daniele Bertaccini worked on this quite broadly. I report here only one paper, because I think it's the most significant, and it opened the way to a set of papers on this subject. But more recently, also McDonald, Pestan, and Wathen work in the development of preconditioners of this form. And it's, for instance, in this paper by McDonald, Pestan, and Wathen, basically what they do relies on this relation here, where B for backward Euler can be written as this matrix C here, that is a circulant matrix, plus a rank 1 matrix. And what they do, basically, they drop the rank 1 term and use this C in the preconditioner. So also our strategy relies on this relation, but instead of dropping terms, we're going to use these to design a solver instead of a preconditioning operator. So here in what follows, I'm going to assume m equal to the identity. Let's say we're using finite differences, but also with m different from the identity, everything works the same. So again, C is a circular matrix, so it can be diagonalized by the fast Fourier transform. And this is our original problem, the all-at-once linear system. So we apply the fast Fourier transform on both sides, plugging also the expression of B, so C plus rank 1. So we end up with this problem here. U tilde and F tilde, now they are transformed U and F. And this is the linear system that we now want to solve. This term here, many of you are familiar with the Kronecker product properties, but this matrix here, P, is block diagonal, while this term here is low rank. Here I replace FE1, this vector, with the vector of all ones because of the first column of the discrete Fourier matrix is indeed a column of ones. So we apply the Sherman-Morrison-Woodbury formula, and we end up with this formulation here. Once we compute U tilde, we go back to U by a backward transformation. So the main feature here that we need to exploit are, for instance, that the vector F, again, is the vectorized form of this matrix. So we can easily apply the Fourier transformation from the right. P is block diagonal again, so we can compute P inverse times a vector in parallel very efficiently. But actually, we cannot compute P inverse times M because this would be the parallel solution of L linear systems n times. So that's too expensive because M has n columns. But we can exploit the Kronecker structure of M and N to compute expressions like this. So the main issue here in this formulation, in the Sherman-Morrison-Woodbury formula, is related to this core matrix here, identity plus n transpose P inverse n. So if pi's are the eigenvalues of our circular matrix C collected in the matrix pi, and gamma I, gamma L are the components of this vector here, we can write explicitly the formulation of this matrix here that is given here. So we have linear combination of these matrices here. So shifted version of K inverse. So quite involved. And we need to solve a linear system with this coefficient matrix. And what we suggest to do is to employ a Galerkin method for this linear system based on the polynomial Krylov subspace generated by K, so the stiffness matrix, and the right-hand-side B. So this machinery is very general, has always the same structure. We compute an orthonormal basis for our approximation subspace. We look for a solution XM of the form Vm times Ym, where Ym is computed by imposing a Galerkin condition. And it can be shown that imposing this condition is equivalent to solving this, again, quite involved projected linear system. So the expression of the coefficient matrix here is not easy, but let's see what we have here. So theta here is just the norm of the right-hand side B. Mi is the inverse of this matrix here, where Tm is the projection of the stiffness matrix onto the computed subspace. Tm plus 1m is a scalar coming from the Arnoldi procedure. And H here are vectors of this form. So the solution of a linear system with this shifted version of the stiffness matrix, where the right-hand side is the m plus 1 basis vector of our Krylov subspace. So this means that this Hi, again, can be computed in parallel. So at each iteration of our Galerkin method, if we want to compute Ym, and we want to compute also the residual norm, we need, again, to perform a parallel in time loop. Okay? So summing up all the steps in our Sherman-Morrison-Woodbury formula, this is basically the overall algorithm that we have. So we start with a parallel in time loop. Then we define the right-hand side of our, let's say, inner linear system. We use a Galerkin method to compute Xm, another parallel in time loop, and then at the end of the process, we retrieve the original solution U by this relation here. So this means that we have 1, 2 plus m, so 2 plus m parallel in time loops for getting our solution, where m is the number of iterations we need to achieve a prescribed accuracy in the Galerkin method. So this is the most computational expensive part of our routine, but this can be decreased a little if we compute ym in the Galerkin method, and so we compute the residual norm every other d iteration. So we construct our subspace performing d iterations. Building the subspace is very cheap. It's a polynomial subspace. We just need matrix vector multiplication with k. After d iterations, we compute ym, performing a parallel in time loop, compute the residual norm. If this is small enough, we are happy, we're done. Otherwise, we perform other d iterations and so forth. Some numerical results. So we have a time-dependent convection diffusion equation here. You see the details of this equation here. We have this viscosity parameter. The convection vector is given here. These are the boundary conditions. And actually, we obtained the stiffness matrix by the IFS package. So we didn't design any routine for computing this K. And these are some results. So we have this all-at-once linear system, and we use as a comparator GMRAS for solving this linear system that is preconditioned by this operator here. This is basically McDonald, Pestana, and Wathen strategy. So we drop this rank 1 term in B, in this fraction of B, and we use only C in the preconditioner. So inverting this preconditioner can be carried out in parallel with a parallel in time approach. We set the same threshold between GMRAS and the Galerkin method, our inner Galerkin method. And here we report as a comparison measure the number of parallel in time loops that we need to perform in both methods. So for our method, we have, again, m plus 2 parallel in time loops, while for GMRAS, we have p plus 1, where p is the number of GMRAS iteration, because we need to apply the preconditioner at each iteration, plus also at the end of the iterative process to retrieve the final solution. So we have p plus 1. And here we have different number of degrees of freedom in space and in time. And you can see here that we need to perform much fewer parallel in time loops with respect to what is done in GMRAS, while the distance between the two computed solutions remains quite small. So to conclude, we have developed a new framework for paradiag when we adopt BDFs as a time integrator. So we try to overcome this issue of about the non-diagonalizability of our time integrator B. And it turns out that this approach is actually quite competitive with respect to state-of-the-art approaches. I showed you the details for backward Euler because actually we don't have the detail for BDF of order S greater than 1 yet. But actually we can apply the same exact procedure. What happens is that the JL, so the coefficient matrix of our inner problem, now is a S times S block. So our Galerkin method needs to take into account this structure. And also we need to have a broader numerical testing and also compare our method with other state-of-the-art techniques. And with this, I'm done. Thank you. Not really. So
by a stage, let's say.
In the, for instance, for Runge Kuta, you would have, instead of a identity matrix here in the all-at-once approach, you would have, like, let's say, B1, B2. But as long as you have this kind of structure where you have circulant plus low rank in both B1 and B2, and this happens also for Runge-Kutta. You can apply the same kind of approach. Of course, you need, like, technical details need to be adjusted, but I think the framework can...
And in principle, you control the step size by error control. So tau in the process is a variable, changes or not?
Not,
the step size, the time step size.
Not here, because we don't perform a time marching scheme. So here we fix tau a priori.
And then you do...
yeah, exactly.
And assume that for the error, this choice of tau is not good, you repeat?
Yeah, potentially you could go for something smaller.
Assume that tau has to be adjusted. Then you do some iterations. I wonder, just a question. Because usually the choice of tau is delicate, well, for me.
Yeah, I see your point. The thing is that this kind of like adaptive strategy is usually done in, like, again, time marching scheme.
So you need to have some a priori information about the
Yeah, because we solved, like, the whole problem in one time. So I think at that point, if you realize that your tau is too large,
you should refine by decreasing.
Yeah, but I think
then you lose everything. Even if
you have to
is
start back from scratch, I would say.
I see.
Yeah.
Okay. Thanks again.
Thank you.
Next speaker is Stefano Maset, professor at the University of Trieste. We did a PhD together, so we know since a long time. And he will speak about relative error today in ordinary differential equation, more than absolute ones.
Sì. Okay. Good afternoon to everyone, and thank you to Nicola for the presentation. And I go to speak about the propagation of a relative error in linear binary differential equation. In particular, we are interested in long-time behavior. And so we consider a linear differential equation. 2 years ago, in the same meeting, I presented the case for A normal. After 2 years, I presented the case for A general. And we are interested to analyze the perturbation in the initial value, y0. And we are interested in T large. Where are the news? We know that what happens when we perturb the initial value. In particular, if we have an eigenvalue with a positive real part, we have an explosion of the initial perturbation. On the other hand, all the eigenvalues are in the left-hand side. The initial perturbation is exponentially dampened. But the news here is that we are going to consider error measured by relative error rather than absolute error. And if we take this new point of view, the conclusion that we can give with the relative error are completely different with respect to the absolute error. Here we are considering perturbation in the initial value, and in the next talk by Asma Farouk, the same problem, for the same problem, there are considered perturbation in the matrix A. Here we use as a relative error a norm-wise relative error. It is also possible to consider a component-wise relative error, but here we consider the norm-wise, but I can say you more or less the conclusions are the same when we consider a component-wise relative error. So these are the main characters in our story. We have the relative error epsilon in the initial value, and then we have the relative error delta t in the solution at time t. And of course, the big question is, what is the relation between epsilon and delta t? Here we have a pictorial representation of what we are doing. In practice, for each time t, we are using in a state space picture like this two-dimensional case, we are using as a unit length the size of the solution. So this is the situation at the beginning where epsilon is the error at the beginning, and then this is the solution when the time is t. Once again, the unit length is the size of yt. And so here the error is delta t. And now we are ready to introduce the condition numbers. What are the condition numbers? Are the factor with which we can pass from the initial error epsilon to the error at the time t. And so we perturb in the top equation, we perturb the initial value by using a fixed direction of perturbation, z0 hat. Then we introduce y0 hat is the normalized initial value. And then we have the exact direction, delta t equal to k epsilon. And this first condition number k can be called, it gives exactly the relation between epsilon and delta t can be called condition number with direction of perturbation. And it is given by the formula on the right. On the other hand, okay, it is useful, but from the practical point of view, I don't know if it is useful indeed. And so we consider the worst case for the perturbation. And so we have our second condition number. It is the maximum when we move the perturbation on the unit ball, because the perturbation, the direction of perturbation is a unit vector. And then we have this second condition number. Indeed, we have a third condition number, and when we consider the worst case for the initial value, and in this case, what we obtain is the classical condition number of the exponential matrix. But this last condition number, worst case for perturbation and worst case for initial value, it is not interesting. Why? Because it describes a situation that is not generic for the initial value. So we have an explosion, exponential explosion of the initial error epsilon, but this happens in a non-generic situation for y0. And so it is not interesting. And for this reason, from now on, we consider only the first two that are the more interesting, and we study the asymptotic behavior. And in order to do this, we need to partition the spectrum, and the spectrum is partitioned by decreasing real part. So we start from the rightmost real part, then the next rightmost, and so on, goes down to the leftmost real part. And so these real parts of the eigenvalues are R1, R2, RQ in decreasing order. And so this is the spectrum partitioned. Then another tool is we need a formula for the matrix exponential where the role of the time t is explicitly defined. And for this reason, we use the formula in the top. This is a formula for a generic function of matrix, and it is based on the Jordan canonical form of the matrix A. And I remark that I use the Jordan canonical form only for analyzing, not for computation. And here, this formula involves mi, the index of the eigenvalue lambda I. Mi is the maximum size of the block of the eigenvalue lambda I. And then we have matrices, PIL, are suitable matrices that here we don't define, but they are constructed starting from generalized eigenvectors that are in the Jordan canonical form of A. And in particular, I can say that Pi0 is the projection of the eigenspace of lambda I. If we apply this particular formula to the matrix exponential case, and we take into account the previous the partition of the spectrum by decreasing real part, we obtain the formula that you can see there in the middle, where we have from J to 1 to Q the different real parts, then L to 0 to capital Lj. This is an index of the size of the blocks relevant to eigenvalues in lambda I. Lambda j, I remind you, lambda j is the eigenvalue in the jth real part. And finally, we have these matrices Q, J, L that depends on T, and they are fundamental for our asymptotic analysis. They are given by the formula in the bottom. Here we use the following notations. Ft asymptotically equivalent to Gt means that the relative error between f and t goes to 0 when t goes to infinite. And since we are also interested about the onset of the asymptotic behavior, we also consider this other notion. Ft is approximately gt with precision epsilon, and it means that the relative error is not larger than epsilon. And these are the theorem that introduce the asymptotic condition numbers. And in a generic situation for y0 and the initial perturbation, and this is the reason for, this is the basic assumption that excludes the case that I mentioned, two pessimistic cases that I mentioned before. In this generic situation for y0 and the directional perturbation, the two condition number, the condition number depending on the perturbation, the condition number independent of the perturbation, the worst case for the perturbation, they have asymptotic version. They are k infinity in both, where k infinity are given in the formula just in the middle, and you can see they are involved the matrices Q1, L1, as applied to perturbation, as applied to normalized initial value in both cases. And I remind the definition of Q1, L1 there. So what are involved here? Of course, they are involved the rightmost eigenvalues and the maximum size of the blocks of the rightmost eigenvalues. And here we can conclude with the important fact that here the situation is completely different with respect to the absolute value, because as a function of t, these asymptotic condition numbers are bounded and away from 0. So it means that in the generic situation, we don't have exponential explosion, and we don't have exponentially, that the solution, the perturbation are exponentially damped. So they remain there. They don't go to infinite, they don't go to 0. What about the onset of the asymptotic behavior? We can say the first two things that are in the top. We have approximations of the condition number to their asymptotic version with the precision that is written on the right. And epsilon are errors, and they are given by these complicated formulas. But I want to remark that in that formula, we have a function of t that are going to 0 when t goes to infinite, because we have a negative exponential and negative power of polynomials. And so this error goes to 0 when t goes to plus infinite. And so we can control when there is we can say something about when we have the onset of the asymptotic behavior. Here we consider the case, the previous one was the case for any matrices. For any matrix. Here we consider the case, the generic case for a real matrix. So we suppose that A is real, and we assume the following generic situation where for any real part, the eigenvalues with this real part are given by a unique simple real eigenvalue, or otherwise by a unique pair of simple complex conjugate eigenvalues. And so we have the spectrum we can see just in the middle. I remark that if you try with, in MATLAB, A equal to rand n, and A equal to rand normal n, you obtain spectra like this. And here, in order to deal with this case, we introduce Vj, that is an eigenvector of lambda j, a Wj that is a left eigenvector of lambda j. So Vj is a column vector, a Wj is, on the other hand, a row vector. And so then we introduce these two normalized, right eigenvector and the left eigenvector, and then we introduce this important number, fj. We will see because it is important. And this theorem considers the case where the rightmost eigenvalues are given by a simple real eigenvalue. In this case, the two asymptotic condition numbers are constant, independent of t. And it means that if we look to the graph of the condition number, we see that this graph has an horizontal asymptote. What about the onset of the asymptotic behavior? Observe that we have negative exponential against this ratio. So, in practice, the onset is determined in which manner the negative exponential can dump this ratio. On the other hand, in case we have lambda 1 constituted by a unique complex conjugate pair of simple eigenvalue, these are the two asymptotic condition numbers, so we have a constant part plus another part that depends on t, and these parts, depending on t, are periodic function of t. So it corresponds to an oscillation. And these are two lower bound and upper bound of this oscillation. Observe that here it is involved this number V1, that is the modulus of this complex number. Observe that V1, for this case, is a complex vector, and here we are doing the transpose of this complex vector times this complex vector. We only transpose without conjugation, and so this is a complex number, and we take the absolute value. It is between 0 and 1. So we can call these two factors oscillating factors, and the constant value are the oscillating scale factors. And this is when we have the onset of the asymptotic behavior. Here, with respect to the previous one, the exponential faced with this ratio, but also the square root of 1 minus V1. And so I skip the numerical test, and I want to speak about non-normal matrices. In case of normal matrices, V1 is 0, and also this number Fj are equal to 1. So immediately we have the onset of the asymptotic behavior. With non-normal matrices, V1 is arbitrarily close to 1, because remind that V1 is between 0 and 1, and the number Fj can be arbitrarily large. And so the question is, what is the impact of an non-normality on the asymptotic condition numbers? So when lambda 1 is constituted by the real eigenvalue, we have no impact on the asymptotic condition number, so the asymptote, because V1 is a unit vector. And what about the impact on the onset of asymptotic behavior? And here we have the problem that this ratio, Fj over F1, can be very large. But this is not automatic for an eigennormality, because with an eigennormality, what we have is Fj large. But nothing is known about the ratios. What happens when the lambda j is constituted by the complex conjugate pair? In this case, we have to take into account the case where V1 is close to 1. In this case, we can have possible wide oscillations, because remind that these are the two bounds for the oscillating factors, and we have in numerator square root of 1 minus V1. And also we have an impact on the onset of the asymptotic behavior, because we have a larger ratio, but also we have the square root of 1 minus V1 at the denominator. Have time for show you 2 minutes. Okay, so I show you some numerical test. Here I take a matrix from the MATLAB gallery test. In particular, this is the matrix LESP n with n equal to 10. We have 10 distinct real eigenvalues. And here we use the Euclidean norm. In this case, we have the horizontal asymptote. In blue, the blue line is the condition number, and the red line is the asymptotic condition number. This is for an initial value, this is for another initial value. This is another test where we take this matrix. In this case, we have parterre of dimension n equal to 10. We have 5 pairs of eigenvalues, conjugate pairs, and here we use the infinite norm, and in this case we can see the oscillation. This in the yellow is the oscillation scale factor, and this is multiplied by an oscillation, and this is the result is the product. We see that asymptotically they coincide. We have not a smooth curve because we are using infinity norm. This is another initial value, and this is the case for A when is highly non-normal, so we take this one, where this is the Hilbert matrix of order 8, and this is the situation for initial value another one, and on the other hand, this is a case where V1 is very close to 1, and here we can see the wide oscillation. Okay, thank you for your attention. Yes, because it is related to what happens before the asymptotic. Yes, yes, but you have to invent another notion of pseudospectra, relative pseudospectra.
Hi, good afternoon, everyone, and it's a pleasure to be here. Maybe take away facial mask. So, thanks, Nicola, for the kind introduction. And yes, so as Nicola remembered, I did my PhD in Sweden, in Gothenburg, and my PhD was about geometric integration of non-Hamiltonian and Hamiltonian systems, and in particular applications to this integrator to fluid dynamics. And then when I moved 1.5 years ago in Pisa with Michele Benzi, he was interested in the more sort of numerical aspects, and in particular those that are related with the numerical linear algebra. So, in fact, what we will see today is a study in a particular geometric integrator that I developed during my PhD, and some sort of optimization of how to implement it and solve it numerically. So the title is about cubic matrix equations. So in literature, we don't find several of these examples. Actually, most of the literature stops at quadratic matrix equations. So this might be interesting also because of this aspect, part of the applications in geometric integration of ODEs. So in fact, the starting problem that I studied, and sort of the main application of the studies in this work, is the geometric integration of isospectral flows. Isospectral flows are particular ODEs on matrices, on matrix spaces. For those that are not familiar, typical isospectral flows are on structure called Lie algebras, or matrix Lie algebras. For example, the orthogonal matrices or unitary matrices. Sorry, skewer meeting, of course, the Lie algebra of the orthogonal group and the unitary group. So in this case, I just keep the general sort of notion of isospectral flow, where we start from any possible complex or real matrix. But then the vector field, which I call it L, is a linear operator on matrices. And it could be, for example, a bracket of matrices and so on, so you can define the linear operator that you like on matrices. And the bracket that you see on the right-hand side is the usual commutator. And the peculiar aspect of these flows is that the spectrum of the state variable y is time invariant. And more interesting to applications in physics is that when the operator L is self-adjoint, for example, with respect to the Frobenius inner product, then we can find an Hamiltonian structure to this problem. And in fact, we have conservation of the Hamiltonian you see in the bottom of the slide. And so in this case, these systems are called Lie-Poisson systems, for those that know this field. And so as a numerical analyst in geometric integration, the key point is to retain most of, or possibly all the first integrals of our system in a discrete time integration. So one of the simplest algorithms that I developed during my PhD that comes from the symplectic Runge-Kutta methods up to some algebraic manipulation is this one. And as you see, the first line, so the state variable is yn, and we have first to solve the first line, which requires the solution with respect to xn, and this, since L is a linear operator, then this is a cubic equation in X, cubic matrix equation in X. And then to move forward in the next time step for Y, then it's enough just to update the left-hand side of the second equation. And you see that the difference is only in the sign appearing in the terms in the parentheses. So this scheme is second order in time, and this is quite easy to see because it comes from the midpoint rule. The spectrum of Y is exactly preserved during the discrete evolution of the flow, and the Hamiltonian of the system, if present, is conserved up to order h to the power square, where h is the time step. Yes. So then we will focus on the cubic equation that was the first step of our numerical integrator. So x is the unknown, and y is the given term in the right-hand side. So we have this theorem of existence and uniqueness of the solution for such an equation in some neighborhood of y for h small enough. And in particular, if this equation takes place in SUN, so here SUN is the space of skew Hermitian matrices with a zero trace, which will be one of the most important spaces in applications. And I will tell you why later. So we can find that this neighborhood exists for any h which is bounded by the term in the bottom. So the proof of this theorem that I will not give here because of time restrictions is merely a combination of the Peano existence theorem for ODEs, and then one can work for the uniqueness using, for example, the fixed point, the Banach-Cacciopoli fixed point theorem, and also get this bound in the same fashion. So this result and the fact that we are using fixed point iteration immediately gives us a possible numerical scheme to solve this equation. In fact, one can just manipulate the left-hand side of the cubic equation and transform this equation in the iterative, in a fixed point sort of problem. And then we have that we can write our integration, or sort of our iteration, sorry, in this form. So the left-hand side is the unknown variable, and then the right-hand side is the sort of the function depending on xk, which is, again, cubic. The convergence is guaranteed because of the theorem for h sufficiently small, taking as an initial guess y. And the complexity is just given by the matrix multiplication, because in all our applications we assume that the evaluation of L on xk is the fast part of the algorithm. So we never assume that the evaluation of L is the most expensive part, which could be up to n to the power 4, but in many applications this is not the case. And in particular, when we work in SUN, for example, to evaluate the right-hand side, we only need 2 matrices multiplication. Okay, another scheme that it's possible to adapt for this problem is considering another fixed point problem. So instead of manipulate the left-hand side as we did for the previous scheme, we can just keep the cubic problem as it was, and then we sort of take one of the x as an unknown and give the other 2 x as given. And then we find this sort of linear iteration, linear in the sense that we have to solve a linear matrix equation, which is the second equation, and then update the variable that I call pk. Again, it's possible to see that this scheme converges similarly to the theorem, similarly thanks to the theorem that we had before. The complexity is similar, and we solved this linear matrix equation using LU factorization of the 2 factors on the left and the right of xk plus 1. And then, of course, another possible approach to solve this cubic matrix equation is inexact Newton iteration. Inexact because we define G as this function moving everything on one side of the equation. And then we have to sort of consider the Jacobian of G, of course, which is made of these 2 operators. And since then we need the inverse of this Jacobian, then we have to choose an approximation of its inverse. So we have up to second order in H, we have 4 possible choices. So there is the exact first order expansion, and then on the other side of the accuracy, we have the exact second order expansion, and in between we have sort of some possible choices. So we either keep one of the 2 second order operators. And apparently, our numerical experiments show that the best choice is the second one, because B1 square is actually usually quite small, and it doesn't influence very much the convergence of the inexact Newton iteration, still being expensive to be evaluated. So we don't gain anything of retaining B1 square. And the first order approximation is not enough accurate to guarantee good convergence property of the inexact Newton iteration. And again, we have the same complexity of the fixed point problems. So let's try these algorithms to see which one performs the best on some problems. So the main test problem that I have in mind is the following. So this is also part of my PhD thesis. So basically half of it, which is related to fluid dynamics, and in particular to the integration of Euler equations into the for 2D ideal fluids. So here in particular, when our fluid takes place on orientable surface, compact, for example, the sphere or the torus are the classical examples, then the Euler equations for the vorticity, which is the scalar field that you see here, indicated by omega. So this equation admits a very nice spatial discretization. So we have this semi-discretized in space ODE on SUN. So here I remember SUN is the space of n times n skew Hermitian matrices with 0 trace. So now our matrix W represents a discrete vorticity. This discretization is similar to a spectral method, but unlike to the spectral truncations, this sort of gives a system which retains most of the conservation laws of the original Euler equations. And in fact, it's a very interesting model in itself, a fluid in itself as a fluid model. And so here, our operator L is the inverse of the discrete Laplacian that I denoted with delta n, which, for example, on the sphere has a very nice three-diagonal structure. So the evaluation of the Laplace inverse on W with LU factorization, sparse LU factorization is very fast and requires only, the evaluation requires n square operations. And LU factorization, of course, can be done only once. So we apply our numerical scheme to this ODE, and then we try to solve the related cubic matrix equation with the three different algorithms I showed you before. And apparently for this problem, the fixed point schemes perform better than the Newton scheme, especially when the dimension n becomes large. So we really have to work with n quite large for this problem in order to get spatial accuracy for the Euler equation, because the convergence of this model in spaces like of the order 1 to the n power square. We keep the time step fixed h 0.5, and we normalize the initial data. And we compare the number of iterations in 10 different runs with different initial initial data, and the CPU time run on my laptop, which is not particular, like it's not high performance computing. It's just computation that you can do on your personal computers. And so the simplest scheme, which is the first explicit fixed point scheme, performs the best in this case. But here I want to show another application, which is the Heisenberg spin chain. And these equations arise from the spatial discretization of the Landau-Lifshitz-Gilbert Hamiltonian PDE, which maps the curve, so this sigma curve, which is a closed simple curve in S2. And then you see how the PDE is written, considering S2 embedded in R3 with the cross product. So discretizing in space, the Laplace operator on the right-hand side with the finite difference, we get the following system on SU2 to the power n. So it's a direct sum or direct product of these algebras, which are isomorphic to R3, so you can think R3 to the power n if you want. And this is a chain because the last and the first term of the discretization are the same. It's a closed curve. And so here we have sort of a different equation from the previous one. In particular, the operator is quite different from the one we had before. And also it's a direct product of algebras and not a full large matrix SUN as we had before. And actually our algorithms have sort of a surprise outcome. In particular, the first explicit fixed point and the Newton iteration are not do not perform well when n increases. In particular, their performance is really dependent on the size, so on the number of particles, spin particles we have in this case. And we see that actually the algorithm that performs the best is the implicit, the linear scheme, which is actually requires to solve a linear matrix equation. Still is based on the fixed point problem, but it's a different fixed point problem from the explicit one. And even if we don't have a sort of a mathematical proof of this, we expect that the higher order terms in H influence the convergence of these schemes. And in particular, the inexact Newton method also does not show very good properties for large H. If we reduce H, for example, to 0.1, all the schemes converge. So it really depends on the fact that if you want to keep H large, then you have to sort of consider that probably a method that requires some sort of some solution of linear problems, in this case matrix linear problems, might perform well. So you sort of gain what you lose in having to evaluate the LU factorization of your factors. Oh, yes. Yeah, that was the implicit. Yes. It's a typo, yes. Thank you. And to conclude the talk, if I have 1 minute more. So it's possible to devise another scheme which preserve all the structure we have shown so far. So, for example, our scheme were natural because they evolved in SUN, so they were natural for applications. And another is, instead of keeping x as the unknown variable, is to define p, which is L applied to x, as the unknown. And this sort of generates a quadratic iteration, which requires the solution of a Riccati equation, so a CARE equation in P. But the problem here is that in our applications, we don't have any sort of knowledge on the spectrum of P. So actually, we have non-uniqueness problems, non-uniqueness issues here in the solution of this scheme, which would be or could be applicable if we had some sort of problem that has a prescribed spectrum for P. But at the moment, I didn't find any real problem to apply this scheme, which would be nice also to see how this converges or this works compared to the others. And also in that case to prove maybe existence and uniqueness of the solution. And so to conclude, we have seen just brief introduction to the geometric integration of conservative PDEs and semi-discretized PDEs. These methods are very important for retaining physical properties, which, by the way, are essential in long-time integration of these equations, and that's why we really want to keep our time step large. Both iterations based on the fixed point and in exact Newton work well. Still, for large H, which is the main interest for applications, the fixed point iteration works better. In particular, the implicit one is more stable also for quite a large L. And I thank you for the attention.
Thank you very much for the very interesting talk. This time for a very quick question. There is one. If not, we thank you again.
Thank you.
The next talk is online. So you the part 2 that Stefano announced in his talk. So it's about relative error propagation, but perturbing the matrix A. And the speaker is Asma Farouk.
Hi, can you hear me?
Yeah.
So should I share my screen now?
Yeah, you can start sharing.
Okay. Yeah, you can start.
Hi, good afternoon, everyone. And thanks for the introduction. Before I start, I would like to pay my gratitude to organizing committee for providing this great opportunity to present my work. I'm going to talk about how perturbations propagate along the solutions of linear ordinary differential equations. It's a relative error analysis. And this work, as my PhD project, is jointly done with Professor Stefano Mazzet. Here is the outline of my presentation. In first part of the presentation, I will introduce you with 3 condition numbers, namely condition number with direction of perturbation, condition number independent of specific direction of perturbation, and the third condition number is condition number not only independent of specific direction of perturbation, but also independent of specific data. Then I'll confine my attention to analyze these condition numbers for normal matrices. Long-term behavior of these condition numbers is important part of our study. So I'll give the asymptotic behavior of these condition numbers. To testify our analysis, a few numerical tests is also part of our presentation, my presentation. So let's get started with perturbation analysis of ordinary differential equations when it is the coefficient matrix that perturbs. So for this, we consider following ordinary differential equation and suppose that the coefficient matrix A undergoes some perturbation, and after being perturbed, it takes the value A tilde. A perturbation in the coefficient matrix A also results in perturbing the solution of the equation. The solution of the equation is originally given by this equation, and after being perturbed, it takes the form y tilde t. Here, epsilon gives the relative error in the coefficient matrix A, and where the norm is a generic norm on Rn cross n, and xy t gives the relative error in the solution of the equation. Now, our main focus is to investigate how epsilon and xy t are related to each other. So in other words, we want to investigate how perturbation in the coefficient matrix A affects the solution of the equation. For this, we first specified perturbed matrix A by the following equation. In this equation, matrix B is the specific direction of perturbation with the unit norm. We first define our condition number with direction of perturbation. This is the condition. This condition number is defined as following limiting value. And for the problem under consideration, this condition number is given by this quantity. Here, in this equation, this quantity is the fracture derivative of matrix A in direction of B, and y0 is the unit vector which is given below. We define our second condition number as worst case of the condition number with direction of perturbation, and this condition number is for the problem under consideration. This condition number takes the following form. Here, this quantity is a linear operator, and this is the solution of the equation. Our third condition number, which is condition number independent of specific data y0, it is defined as a supremum of the condition number with specific data. Here, I would like to point out an important thing, that this kind of analysis has attained very less attention in literature. To best of our knowledge, there are only 2 papers in literature, one by Edwin Dedman and another one by Nicholas Haigam on this topic. But both these paper gives as a computational aspect of the condition numbers. On the other hand, our study is more on theoretical aspects of the condition numbers. For example, we have considered the initial data y0 in our study, and also the long-term behavior of these condition numbers is a very important part of our study. So let's analyze these condition numbers for normal matrices. From now on, matrix A is a normal matrix, And for the rest of analysis, we use a two norm. And to emphasize on two norm, we denote previously defined condition number with a subscript 2. Back to normality of matrix A, we decompose matrix A by following spectral decomposition. Here, lambda I are the eigenvalues of the matrix A. We have p distinct eigenvalues of the matrix A, and pi is the orthogonal projection on eigenspace of a corresponding eigenvalue lambda I. Next equality is result of orthogonality of projection matrix pi. This function G is an analytic function defined on matrix A, and by orthogonality of matrix P, we can give this very useful equality. Then we partition the spectrum of matrix A. The spectrum of matrix A is denoted by lambda, and we partition this spectrum into subsets, lambda 1, lambda 2, and so on, lambda q. In each subset, we have made this partition by decreasing real parts. So in lambda 1, we have all those eigenvalues with a maximum real part, and that real part is given by is denoted by R1. In lambda 2, we have all those eigenvalues with the second largest real part, and that real part is given by R2, and so on. In lambda q, we have all eigenvalues with the minimum real part. Following diagram also describes the situation of this partition. This partition enables us to give following orthogonal projection Qj. This orthogonal projection is sum of projections on eigenspaces of all those eigenvalues that lie in same subset of the spectrum. We also define this function C for some eigenvalue lambda I in some subset lambda j, and lambda k is eigenvalue from the spectrum of the matrix. Now we can give our first theorem, which is about the condition number independent of direction of perturbation. In this, but before the theorem, let me introduce you with the notation J star. This notation J star is the minimum index such that this quantity Qj y0 does not vanish. And theorem first states the lower bound for the condition number as the maximum of this quantity, and a maximum is on lambda I any eigenvalue from the spectrum, and lambda k lie in the union of the subsets lambda j, where this j starts with the j star to q, and this function d is given by already defined function c, provided that lambda k is a real eigenvalue, and it is given by sum of function c and its conjugate, provided that lambda k is a complex eigenvalue. Upper bound for this condition number is given by next inequality. We can observe that in non-generic situation, by non-generic situation I mean j star greater than 1. In this situation, we can observe exponential growth of the condition number. In generic situation, that is j star equals to 1, upper and lower bound for the condition number takes the following form. And in this generic situation, we can observe linear growth of the condition number. Our theorem 2 is about two interesting situations. The first one is when our initial data lie in rightmost eigenspace, that is, if it satisfies the following equation, then condition number independent of specific direction of perturbation is exactly equal to its lower bound, which is given in its generic situation. Second situation is when q equals to 1. Q equals to 1 corresponds to the situation when all eigenvalues lie in same subset of the spectrum, in the first subset of the spectrum. So it means all eigenvalues have same real part, and this is the situation which can be attained in by skew symmetric matrices. In this case of the skew symmetric matrices, once again the condition number is exactly equal to its lower bound. Third theorem gives upper and lower bound for the condition number independent of specific data. First, it states the lower bound as the maximum of this quantity. Here, lambda I is eigenvalue from the spectrum, and lambda k is the eigenvalue which lie in the last subset. So it has the minimum real part. And this function d is already defined. We can, from both of these bounds, once again, we can observe exponential growth of the condition number for q greater than 1. So here is asymptotic analysis of the condition number. Before the asymptotic analysis, let me introduce you with a few notations. The first notation, J star, I already introduced. It is the minimum index such that this quantity qjy0 does not vanish. And J double star is the minimum index such that this quantity for some k does not vanish. F of t asymptotically equivalent to g of t stands for following limiting value. We have a similar notation here. This constant C infinity is given by this ratio for some eigenvalue lambda I in lambda j, and lambda k lies in some subset lambda L, where j is less than L, and d infinity is given by C infinity provided that lambda k is a real eigenvalue, and it is given by sum of C infinity and its conjugate provided that lambda k is a complex eigenvalue. Here is our first asymptotic behavior of the condition number independent of direction of perturbation. So theorem 4 first states the generic situation. In a generic situation, this condition number independent of specific data asymptotically goes to this quantity. And for non-generic situation, that is J star greater than 1, we have asymptotic upper and asymptotic lower bounds. Asymptotic lower bound is for gives the maximum of this quantity for lambda I lies in the first subset of the spectrum, and lambda k lies in the union of subsets lambda j, where j starts with j star to q. We can observe that in non-generic situation, this condition number grows exponentially. We also have following relation of the condition number. Our last theorem gives the asymptotic behavior of the condition number independent of specific data. We once again have upper and lower bound for the condition numbers, and here the maximum is on eigenvalue lambda I, which lie in the first subset of the spectrum, and lambda k lies in the last subset of the spectrum. So we have exponential growth of these of this condition number with increasing t. Okay, and now a few numerical tests. Our first example, we have constructed to testify our theorem 2, which is about, let me show you once again. here, which is about a special situation of skew symmetric matrices. So in example 1, we consider a 2x2 skew symmetric matrix for left plot and a 4x4 skew symmetric matrix for the right plot, and we plotted maximum of this quantity in 10,000 random selections of matrix B. These red points are the maximum of this quantity in each random selections of matrix B. And we can observe that these red points are very close to this blue line, where this blue line is has a constant value 1. So it verifies our theorem 2 for skew symmetric matrices. In our example 2, to testify theorem 4, the generic situation of theorem 4, which is here, we chose our initial value y0 in a way to have it in rightmost eigenspace, so to have the situation j star equals to 1. We considered 2x2 symmetric matrix for the left plot and 4x4 symmetric matrix for the right plot. And we plotted maximum of this quantity in 10,000 random selections of matrix B. And once again, we can observe that these red points are asymptotically going to this blue line, which has constant value 1, and it also verifies our theorem 4. So, thank you. It concludes my presentation.
Thank you very much. Are there questions from the audience? If not, we thank you again.
Thank you.
Okay, so the last speaker of this session is Mattia Manucci, PhD student at Gran Sasso Institute, and he will speak about initial value problems for partial differential equations by contour integral methods and the connected linear algebra issues in these methods.
No, lo uso qua. Oh. Ok, va bene. Okay, thanks for the introduction, and moreover, thanks to the organizer for the effort of organizing in presence this conference in this period. So, I will speak about the first part of my research for the PhD that concern pseudospectral roaming contour integral methods for convection diffusion equations. And is a joint work, is a work started originally by Nicola Guglielmi and Giancarlo Lino from GSSI L'Aquila and Professor Maria Lopez Fernandez from University of Malaga. So this is the type of problem we want to solve, that is a time-dependent partial differential equation, where A is a second-order linear differential operator, and F is the term containing the source forces. We assume to have a suitable discretization in space, and this leads to the ordinary differential system of equation, where this time capital A is the matrix associated to the discretization of the differential operator KRBA, and B is the vector containing the source forces and also possible boundary conditions. So now the question is, we want to solve this problem, but we are interested in the solution only at a given time t. So how we do this? Well, typically there are employed time steps methods, but these methods can be expensive if is required high accuracy that is related to having a small step size, or if we need, or if the computation has to be done for a large t.
So an alternative approach consists in using the Laplace transform, and employing the properties of the Laplace transform, one can see that the Laplace transform of the solution at the point z is given by the solution of a linear system, where the matrix is zi minus a, and the known term is given by the initial condition, U0, plus the Laplace transform of the vector b, evaluated always in the point z. And then, of course, we want to go back in the time domain, and therefore we apply the inverse Laplace transform. And under suitable hypothesis, what can be shown is that this is given by an integration along a contour gamma, which keeps all the singularity of the integrand function on this left, and goes to plus and minus infinity on the imaginary axis, and stays, asymptotically stays on the left part of the complex plane. So let's say all the formulation of contour integral method is related on the approximation of this integral. And the first step is to construct a parametrization from R to the car gamma, in such a way that we can perform the integration on R. And to do this, let's say one can propose several kind of profile for gamma, because the geometry here of gamma is not given. Only the properties that have to be, I mentioned before, have to be satisfied. So for example, Guglielmi, Lopez, Fernandez, and Nino worked on this profile, the elliptic profile, joined with two half lines. And say part of my work consists in extending the methodology developed for this profile to the parabolic profile and the parabolic profile, which were already known in literature. Okay, so after we have our parametrization, choosing one of these profiles, we need to truncate the integral, because we cannot perform integration over infinite length integral. So we determine a parameter c in order to truncate the integral, and in such a way that the neglected part of the integral is smaller than the accuracy we want to reach with our method. And let's say the idea why this is possible is because, okay, the integral is going on the left part of the complex plane, therefore the exponential is going to have a negative real part, and let's say it will make at some point enough small the integrand function. Then we apply a quadrature rule. For instance, let's take a simple trapezoidal quadrature rule, and what can be shown is that the error between the solution at a given time t and our approximation is given by three major components. So starting from the right, the first component is due, I call it the component due to the noise. Okay, this is related to the fact that when we evaluate the integrand on the quadrature points, we need to solve linear systems. Therefore, there will be small perturbation due to the use of finite machine precision. And okay, even if the system is well conditioned, then we have the exponential there on the integrand function. Therefore, if we are in the right part of the complex plane and the exponential is big, small error in the solution of the linear system will be strongly amplified. Therefore, the integration profile has to be placed in such a way that we can control this part of the error. And then the second component I already mentioned is due to the truncation of the integral, and also this we can control. And finally, we have the component due to the use of the quadrature rule. And the nice property is that even if it's a simple trapezoidal quadrature rule, the rate of convergence is exponential with respect to the number of nodes. Okay, so here I highlighted also the constant t. This because this constant also can be very large if we don't place the integration profile in a suitable way. And now we are going to see why. So the methods work in this way. Before placing the integration contour, we place two other profiles of the same geometries. The first one is gamma left or gamma plus here. And we do this in order to control the norm of the resolvent of the matrix zi minus a, multiplied by the exponential to the real part of the complex point where we evaluate the resolvent times t. And this we need to control because otherwise that constant t can be very large, and therefore we may need a lot of solution linear systems, so a lot of nodes to make the error smaller than the accuracy we require. Then we place the profile gamma right in order to bound the exponential on the right part of the complex plane. And finally, in the middle, there is space to place the integration profile. And this integration profile is chosen in such a way that the number of nodes required to reach the accuracy we prescribe is minimized. Okay, so let's say here it's already clear that the norm of the resolvent plays an important role in placing the integration profile. And let's say this is related to the concept of epsilon pseudospectrum, which is the set of all the points of the complex plane for which the norm of the resolvent is greater than 1 over epsilon. So this set is well known if the matrix is normal, because it will be just a circle with center and eigenvalue of the matrix A of ray epsilon. But if the matrix is not normal, as in our application, this set can have a widely behavior. And therefore, we need some computation in order to determine the boundary of this set. And okay, these computations are expensive because these are the evaluation of that norm is related to the solution of eigenvalue problem, since 1 over the norm of the resolvent is equal to the smallest singular value of the matrix zeta minus A. Therefore, we need to employ some strategies. So in the literature, there have been proposed some methods. For example, the use of the software egg tool, which can be applied to very general cases, but in general it can be very expensive. Or the contour tracing methods, but there can be a problem with disconnected components. And then the approximation of the pseudospectral abscissa, but there are difficulties with the conditioned eigenvalue problem. We worked in developing these strategies that consist in, let's say, section the complex plane in vertical lines. And then we fix, for a fixed value of the real part of the complex point, we try to move the imaginary part. And we move this imaginary part in such a way that that quantity, that is basically the evaluation of the weighted epsilon pseudospectrum, is close to our target epsilon. And we employ the Newton method to do this, exploiting the derivative formulas for the singular values. So, to summarize the content, we set the initial data, that is the matrix A, the vector B, and the initial solution, U0. And then we fix the time where we want to compute the solution and the target accuracy we want to reach. We compute the curve gamma left, based on the pseudospectral computation. We compute then the integration profile, minimizing the number of quadrature nodes to reach the target accuracy. We compute the truncation parameter, and we apply the quadrature formula. The advantages of this approach also in relation to approaches existing in literature are that we don't need any a priori knowledge about the resolvent norm of A. The profile of integration does not depend on the number of node n, and also the method is stable with respect to the number of node n. The method can be extended to deal with time intervals, and these, let's say, without real increase in the computational cost. Also, the main effort, that is the solution of the linear system on the quadrature point, can be parallelized, and also is designed to work in such a way that the user gives the target accuracy that wants to reach, and the method returns a solution with the target accuracy, and if it's not possible, it tells to you. So these are a couple of numerical examples. This will be a numerical example arising from finance model. This because finance is a contest where one is interested in a solution only at a finite time t, and not on the dynamics of the solution from 0 to capital T. The first model is the Black-Scholes equation. And this is a one-dimensional advection diffusion reaction equation for which the Black-Scholes also won the Nobel Prize for economics. And okay, these are the results for different value of the target accuracies, and for all the three types of profile, the elliptic, the parabolic, and the hyperbolic one. So here the horizontal dot line represents the target accuracy we want to reach. And we can see that in all the presented pictures, the method is able to reach the target accuracy for all the types of profiles. And let's say the highlighted dots are the estimated number of quadrature points to reach the target accuracy.
And we can see that it's not exactly the minimum value, but is an estimate close to that value. And we are quite satisfied of this. We can also see that there are no remarkable difference on the behavior of the three types of geometrical profiles. And that, of course, the convergence is exponential until they reach the plateau, which is given by the fact that we are truncating the integral. Okay, the second example is the Aston equation. This time is two-dimensional, and is basically an extension in two dimension of the Black-Scholes model, Black-Scholes. Indeed, if you keep constant the variable b, you go back to the Black-Scholes equation. Here the results are shown for only for the hyperbolic profile, but the same results hold for the elliptic and the parabolic one. And let's say for this time for a time window, 2 times window, 0.11 and 5.510. So and again we can see that the method goes under the target accuracy, that is always the horizontal line there, dot horizontal line. And it goes under a target accuracy for all the value of t in the time window. While the vertical line here is again the estimated number of nodes required to reach the target accuracy. And okay, again, it's not exactly the minimum value, but it is an estimate close to it. So these are the references. In particular, I would highlight that all the codes developed for these methods are available in GitHub. And thanks for your attention. Thank you very much, Matthias, for the very nice talk. Do you have any questions, remarks? Yeah. Can you explain the method for organize the matrix A on function of time? So I didn't listen. Matrix. Can you come here, Mario? Go.
Yeah, I was curious if the method can be extended in the case of your matrix A being time dependent.
No, I think, okay. I think like this, no, because of course then you have to take the Laplace transform of the matrix A multiplied by U, and that this leads to, let's say, kind of non-linearities. So it should be investigated. I'm not aware, let's say, of. I know that there are some examples are studied when, for example, you have a sum of matrices, and the coefficients multiplying the matrices are time dependent. I know that there are some freezing methods, but yeah, I think in that case something can be done. I read something on this, but I never worked on this kind of numerical example, let's say. If you freeze, what you freeze, then it's not natural, but then it has a range. So then you can say, So the general case is complex, but maybe these cases can be treated. Thank you, Mario. Actually, a very interesting question. Any other? If not, we thanks again, Mattia. Vieni qua. We have the coffee break now. Mattia. Voglio presentare un po'.
Sì, adesso sì, tra la mattina e poi l'abbiamo... pure stamattina abbiamo fatto così, sulla pranzo l'abbiamo lasciata.
Bella la grafica, carino.
Con la pausa che c'è. Eppure oggi col lancio ci ha aiutato, perché poi sui su YouTube rimane sempre.
sta basso. No, non lo so, in realtà no, penso che venga da Lombardia, Como. Sì, un'altra forse. Poi non... Sì, però ancora non c'è.
Mancano 5 minuti. Vabbè, però mancano ancora 5 minuti. Vado a chiedere a Daniela. No, stanno 6 minuti, secondo me aspettiamo qualche minuto. No, l'abbiamo visto.
Probabilmente
Lasciamo la sala. Lasciamo la sala.
Sì, lascio in quella
Lasciamo la sala.
tanto. Poi ci dobbiamo ricordare che però quando finisce il talk.
Sì, la dobbiamo rimettere.
Comunque il microfono resta attivo, quindi nel senso il gelato sì, quindi quando magari se uno vuole parlare poi automaticamente va nell'audio dispositivo. Possiamo intervenire sia via chat sia via audio senza problemi.
Silvia, Marco, c'è qualcuno?
Switch telecamera.
Attende.
Così facciamo. Allora, ho reso co-host tutti e tre gli speaker online, se mi potete confermare che per voi è tutto ok.
Sì, perfetto.
Okay. Perfetto. Penso che, Silvia, penso che tu possa anche iniziare a condividere lo schermo, anche comunque iniziamo fra 2 o 3 minuti, ok?
Sì, 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 grazie.
Ciao Silvia.
Ciao a tutti.
Ciao Silvia.
Ciao a tutti. Allora.
Quando siamo vicini ai 20 minuti, il chair potrebbe segnalare che siete vicini alla fine del talk, ok?
O via audio o io scrivo via chat o il chair tramite microfono, in modo che...
Perfetto.
Allora io qua...
Le slide le vedete che si muovono? Sì.
Sì, confermo. Tutto
Perfetto.
ok. Magari va un po' forse lento il refresh rate, ma non è niente, non è un problema. Si vedono muovere comunque.
Bene, bene.
Solo lei, solo speaker, perfetto. No, aspetta. Ok, aspetta, fammi cambiare la telecamera. Ok. Sì, penso momentaneamente. No, penso che dopo si attiverà. Io ho affiancato la tua immagine alle slide, quindi se poi vuoi tenere la telecamera accesa durante il talk, così la gente dovrebbe riuscire a vederti mentre parli. Questo giusto come avviso generale.
Sì, sì, perfetto.
Va bene, adesso vado e lascio spazio alla chat.
Ok. Buon pomeriggio. Parliamo in inglese? Allora, the first speaker of this session is Silvia Gazzola from University of Bath. The title of her talk is Regularization by Inexact Krylov Methods.
Right, so I hope you can hear me well, and thank you very much for giving me the opportunity of presenting my work here. And this is a recent work of mine done in collaboration with my former PhD student, Malena Sabaté-Landman. She's now a postdoc at the University of Cambridge. And yeah, I want to tell you a bit about, some new inexact Krylov methods and how they can be employed for regularization, and in particular with applications to the problem of blind deblurring. So I will start just with setting a bit the stage and the notations. So essentially, we want to solve linear. To start with, really linear least square problems that are typically larger scale, and we can think of these as modeling some discrete impulse problems. In fact, we can think of A as, say, an available condition matrix that models the forward process that acts on some, say, quantity of interest X that we want to recover. And the vector B are typically collected data that are available but are corrupted, right, as we see in this model here. And just to give an example, I want to illustrate image deblurring. Okay, so in this case, the matrix A models the blurring process, okay, modeled by this essentially convolution with this pointer spread function. X is the sharp image we would like to recover and restore, starting from data that look a bit corrupted like this, right? And here I just want to report the size of this simple test problem, just to put emphasis that on the fact that we are typically considering large scale computations when doing inverse problems in imaging. And actually, I want also to present the formulation of a generalization of this problem that would be image, well, sometimes semi-blind deblurring, right, or blind deblurring. So this is a simple generalization of the test problem I presented before, okay? And essentially, we should think of the matrix A not to be completely known, right? So the matrix A will depend on typically a small number of parameters y, okay? So in the case of image deblurring, we can think of these as the parameters that model the blur, right? So in this particular test case, the blur is Gaussian, right? So y are the 3 parameters that define the Gaussian. And apart from this, the problem really reads like the one before, okay? I want to recover a sharp image x, but with the added difficulty that I also have some unknown parameters y in here, right? So essentially this is still a least square problem, but now it's non-linear, although it has a particular structure, right? Because it's a separable non-linear inverse problem. So linear in x and non-linear in x and y jointly, right? Okay, so what are the typical methods used to solve these kind of problems? And going back to say just the linear formulation, okay? We can, there are 2 approaches, both of them are really based on nice numerical linear algebra techniques. So the first one is early termination of the iterations, right? So typically one takes a Krylov method like LSQR, CGLS, GMRS, and applies it to solve the linear least square problem, but terminates early to avoid, say, the error entering in the data, right, entering too much the reconstruction process. The other approach is to consider some variational regularization approach, like Tikhonov method, like the one that is stated here, right? But in the case of larger scale problems, essentially what we do in practice in computations is to combine this variational approach with a projection method, okay, typically a Krylov method. And we can either, well, there are a couple of ways to do this. I don't want to go into the details, but in the following, in the presentation, I will say that when we adopt this approach, okay, this second big bullet point, we will do some hybrid approach, right? And one nice thing of these hybrid approaches is that typically you may change kind of the regularization parameter lambda, this parameter here, which is crucial for obtaining good reconstructions. You can change it along the iterations, and you have a good theoretical framework for this because essentially the Krylov subspaces are shift invariant. Okay, the subspaces for the approximation of the solution X. And also, since I mentioned also the generalization to separable nonlinear inverse problems, which by the way is a kind of the realistic situation, right? So in practice, when kind of tackling the blurring problem, I cannot really assume a complete knowledge of all the parameters that build up the blur, right? So anyway, these to handle separable nonlinear inverse problems, we will consider this variable projection method that essentially consists in a first step. So at each iteration, there is a first step that implicitly eliminates the linear variable here, right? And then the nonlinear problems obtained is solved using, for instance, a Gauss-Newton method. Okay? So this is a bit like the preliminary stage, introduction to the problems. And what I'm doing next, right, I will first introduce some new inexact Krylov methods that can be used for regularization, starting really from regularization for just linear least square problems. I introduce hybrid variants of them that can be used together with the Tikhonov formulation. And then I will explain how we can adopt these solvers to work in a kind of setting where I want to solve a separable nonlinear inverse problem. Okay, so the next slides, I'm warning you, they are quite dense of formulas. I don't want to go into the details, right? I put all the details there, although to kind of look at them from an high level, right? And then hopefully to highlight differences and similarities between what would be the exact solver and the inexact solver, right? So in particular, I focus on Golub-Kahn diagonalization, bidiagonalization. So I can express these either in terms of, say, vectorial form at each iteration or as incomplete factorizations, right? This is well known. In the inexact case, I can essentially do the same, but it's more messy because all these red quantities, they denote inexact quantities and errors, right? So instead of simply having multiplications of A and A transpose, okay, at each iteration, I have multiplications with inexact versions of A and A transpose that are actually iteration dependent, right? So in particular, if we look at the end of this slide, I mean, while in the exact case, the links with symmetrical enlancers are well known and quite clean, right? So the same is not true in the inexact case, okay? Although I can always write, I mean, for instance, compact factorization that looks still quite nice, okay, and gives me an idea of how the problem eventually will get projected. Right, so once the factorizations, like a building block Golub-Kahn is settled, and by the way, here we took inspiration from other, say, similar work, okay, that are used, that are cited here, and they are used mainly in the framework of well-posed problems. We were interested in devising linear solvers, right, with in mind really ill-posed discrete inverse problems, right? So once we have these factorizations at our disposal, we can go ahead and define a version with Golub-Kahn bidiagonalization. It is well known, LSQR is a linear solver based on it, right? And can be reformulated in a bunch of equivalent ways. And essentially, on paper, right, formally, the same exact relations build up what we call inexact LSQR, right? So formally, these formulations are very, very similar, okay? But of course, in the inexact case, we cannot enjoy all the properties, all the nice properties of the exact case, okay? So, for instance, even if, like the projective problem I'm going to solve eventually looks like this, actually, we cannot enjoy anymore the optimality properties of LSQR, okay? So, for instance, the minimization of the residual at each iteration. And similarly, okay, while in the exact case, I can go ahead and establish equivalencies with CGLS, well, in the inexact case, okay, what I call inexact CGLS, which is really obtained with formulas that are very, very similar to the exact case, is not equivalent to inexact LSQR anymore, right? So these would be two new different solvers, right? And once we do this, just for the least square problem, the next extension, thinking of regularization, is how to use these solvers in a hybrid way, right? So how to combine these solvers and Tikhonov regularization. And here I instead want to report essentially what would be inexact LSQR and the hybrid version, okay? Or inexact CGLS and hybrid version. And hopefully you can see that in the case of LSQR, hybrid LSQR, we end up solving, like, I also have some equivalent formulations, damped or regularized least square problem. And in the case of hybrid CGLS, we have some resemblance again with the normal equations here and here, projective normal equations associated to Tikhonov regularization, right? Okay, so just, of course, one should be careful in setting the regularization parameters in these settings, right? But again, we can prove theoretically that under some conditions, okay, we can guarantee a complete freedom in the choice of the regularization parameter, even varying as the iteration proceed. Okay, then just slide to warn you that, well, these solvers are not always meaningful, right? So I cannot really plug in a kind of arbitrary amount of inexactness. And of course, we know these very well. It has been analyzed in the case of the solution of well-posed problems. We should look at similar bounds. Actually, here they are in the case of, say, solvers, these solvers used for ill-posed problems, but we are typically a bit more relaxed than in the well-posed case, okay, essentially because of these reasons, sorry. Okay, so I don't necessarily want to have a small residual, right? So, or better, a small residual for ill-posed problems is not a guarantee of a small error, right? And especially when I use these in the framework of Tikhonov regularization, right? I cannot really expect a small residual because I'm solving a regularized problem, and I'm going to skip these to keep on time, right? But just looking at these without any details, right? These estimates that follow are just kind of bounds that link, say, the what we can call the exact residual, okay, and the inexact residual that is obtained through the inexact projection process, okay, and that kind of estimate how far away they are and give bounds on the errors that one can commit at each iteration to guarantee that exactly these residuals are not too far away, right? And again, these all estimates are more delicate in the well-posed case, so we're kind of lucky when doing ill-posed problems in this sense. Okay, and just to give you an idea of the bounds, okay, so let's focus, for instance, on the green lines, okay. These bounds are quite permissive, okay, and especially they become more and more permissive as the iterations proceed, okay, in the just for inexact LSQR and hybrid inexact LSQR, okay, with a fixed regularization parameter. Okay, and finally, okay, back to the blind deconvolution problem. This is again a formulation, okay, of these separable nonlinear least square problem, right? And here is formally a possible reduction, right? So eliminating in a way implicitly the linear variable and considering a Gauss-Newton step to deal with the nonlinear parameters. This is formally what one typically obtains. Again, I don't want to go into the details. I just want to mention that, well, when doing Gauss-Newton, right, so it could be quite delicate to compute the Jacobian, but for image the blurring problem, we actually have a nice analytical expression for it that we can exploit. And right, here I want to present an algorithm that is kind of regarded, sorry, I'm running out of time maybe. Okay, yeah, I'm going to wrap up essentially presenting what was the algorithm, okay, that kind of regarded the state-of-the-art algorithm that, as I was saying before, kind of performs to get rid of the linear variable, performs a bunch of inner iterations, right, that are here, and before updating really the blurring parameters. What we propose to do is to actually get rid of one layer of these iterations, right? And so what we do, we want essentially to use an inexact Krylov method to approximate the linear variable, okay, the image, while also advancing with approximation of the blurring parameters, right? So this is eventually an inexact solver because the blurring parameters that define the blurring function and the matrix A, okay, the coefficient matrix, they actually vary at each iteration. And okay, of course, we should keep an eye on the accuracy, right? So, and not exceed the prescribed error bounds. Okay, so it may actually be necessary to restart. I'm skipping this. I just want to show, maybe I have a couple of examples, okay? So this one is an image deblurring, okay, of the satellite image. You can see the results here, right? I just want to say that, well, algorithm 4.1, the blue line is what you obtain with the classical method, okay, keeping iterating with inner-outer iterations, and the red line is the performance of the new algorithm, right? So by introducing these inexact methods, Krylov methods within nonlinear, separable nonlinear discrete problems, we can gain a lot in terms of computational time. And I have another one, okay, similar one, still image deblurring, but I'm not going too much into the details because I think I'm out of time. And right, so this is just a brief summary, okay, and some other possible research directions. And if you're interested, just feel free to contact me, or we have a paper about this that recently appeared in SciMax. So thank you very much for your attention.
Questions, remarks? Okay. Over here. Okay. Silvia, I don't know if you can see me. Just a curiosity. I'm not sure that I understood correctly your methodology, but it seems to me that having your regularization, the Tikhonov of 1 plays an important role in working with your method. And have you tried to use a different regularization? Different one, maybe L1 norm regularization or other types of regularizers? And can you say something about that?
Yeah, this is actually a very good question. Thanks, Daniela, right? If I saw correctly, yeah. Yeah, it's a very good question. At the moment, I mean, I think potentially it's possible to extend it. At the moment, we have something that just works with the 2 norm squared and really standard Tikhonov regularization. I think there are a couple of ways to go to extend these, and could be, well, with a general regularization matrix, one may consider standard form transformation. And I believe that with the 1 norm, I mean, one way of extending these would be to consider iteratively weighted least squares solved in some. I mean, there are many recent efficient methods to handle that as well. So I wouldn't know. I mean, I wouldn't know about plugging in some of those proximal gradient algorithms, or like more sophisticated optimization, but for sure keeping in the domain of the 2 norm regularization would be possible, I think. It's a very good question.
Okay. Thanks a lot, Silvia.
Thanks.
Okay. Let's thank the speaker again. Sorry.
Thanks.
The next speaker is Antonella Fallini, Università di Bari. The title of the talk is A Novel Matrix Factorization Algorithm for the Analysis of Hyperspectral Images.
Yes, so I hope you can see my slide. Okay. So thank you very much for the introduction, and thank you for giving me the chance to speak in this very nice and interesting workshop. So this is a joint work with Professor Francesca Mazzia, and it is done within this POM project, Research and Innovation. And I will talk about a matrix factorization algorithm in the context of hyperspectral images. So what is an hyperspectral image? You can think of it as a 3-way tensor where on the third mode, you have what is called the spectral signature of every pixel. This means that you have a collection of, just think of it as colors, stored in 100 of narrow, equally spaced bands. And that's why you have an abundance of information, and you would like to be able to neglect the redundancies and to keep what is important. So usually, what it is done is to vectorize this tensor and to see it as a matrix, and then to apply some matrix factorization algorithm to reduce the dimensionality of the problem. So you have to think of it as along this direction, you will have the pixels, and along this other direction, you will have this spectral signature. So we talk about every row as every row vector as a spectral vector in this sense. And we are going to use a matrix factorization algorithm based on the Stewart-QLP decomposition. So here I will go quite quickly, but just to summarize a bit, what is this decomposition about? So let's say you have a rectangular matrix, and we are always assuming the number of rows bigger than the number of columns. The first step is to perform a pivoted QR decomposition. So you will get a permutation matrix, pi 0, an orthogonal matrix Q, and an upper triangular matrix R. On the second step, you can perform QR factorization again, but on the transpose of the matrix R. This I put inside parentheses pivoted because in this case it's not necessary. And let's say if you collect together the first and the second step, you will end up with something that looks like that. So Q and P are orthogonal matrices, L is lower triangular. And why this decomposition is attractive? Because the Q and P matrices represent a very good approximation of the singular vectors, and the diagonal entries of the matrix L represent a good approximation of the singular values. This is a well-known result, okay? So this is known. And let's say that this decomposition is also attractive because you could do it iteratively. Let's say that you know a priori how many singular values you would like to approximate. Then you can construct iteratively this Stewart-QLP decomposition, and so you can greatly reduce the computational cost. So I'm going to present you now the algorithm that we developed. And let's say that what we are interested to do is to compute an approximation, of course, of the original matrix. But the important thing is that we are not going to know in advance how many singular values we would like to retain. We are just providing some tolerance. So we will have an input matrix A, and in our case, this is always a full matrix. And we will produce matrices U, V, S such that the following holds. And in particular, the second norm of the relative error will be bounded by the tolerance that we are going to decide. So we fix this initial tolerance, and we give as initialization a maximal number of singular values, let's say, that should be computed. Then we perform the thin QR factorization, so you get this expression, and then we perform the LQ factorization on the matrix R. So at this stage, you get this kind of expression. Now, how we do proceed? We take, let's say, we extract the diagonal elements of the matrix L in order to construct the matrix S. So these diagonal elements will be an approximation of the singular values within the given tolerance. So here I put just a very rough overview of the algorithm. Let's say that what is important, I'm going to, I hope, highlight through all the notes. So let's say at the beginning, you don't know how many singular values you need to compute. So this, it will be initialized as the number of columns because we are working with rectangular matrices. So let's say in the worst case, you need to compute exactly n, so as the number of columns singular values approximation. Then you can start from the top and from the bottom of this matrix L and compute the exact SVD. But the size of these small subblocks is going to be given by this parameter here. And as you can see, in the worst case, this SVD's cost is linear in n. And the size of these subblocks is diminishing, okay? As much as we are approaching the center of the matrix, this size is getting reduced. I have to say that for our application, we are mostly interested in recovering the most important singular values, so the heaviest one, which means the biggest. But this algorithm could be used also to compute the smallest singular values. Since we are not performing the pivot QR at the beginning, of course, we need to check at every iteration the magnitude of the diagonal elements. Because you need them to be sorted in descending order. And of course, we respect still to the given tolerance. So at the end, the output, the important output is this parameter, Ks. And of course, the matrix is U and B that contains the approximation of the singular vectors. I know this was very quick, but I don't have much time. I can answer all the questions later on. So let's say that you could also optimize even more this strategy if you could perform long shots by diagonalization at the beginning. And you could do also other things. But the important matter is to keep in mind that in order to approximate the biggest singular values, you need to set up a quite high value for the tolerance. So this tolerance shouldn't be small, otherwise you're going to compute a lot of singular values. And so let's have a look a bit at some example. So this is a very general matrix, which is of the type of matrices that we are dealing with. So here you see the number of pixels, so the magnitude of these matrices, and this is the number of bands. So in this case, I set up this tolerance 10 to the minus 2. And what we are looking at here is on the horizontal axis, you see the approximated singular values. On the vertical axis, you see the number of iterations. The blue blocks are the biggest singular values. The yellow blocks are the smallest. So the first 4 biggest singular values in this example were approximated with 3 iterations. And in total, you have 7 biggest singular values approximated in 4 iterations. You can ask what happens if I'm going to require more accuracy. So I need to set up a smaller tolerance. Of course, you're going to compute more singular values, all of them approximated with respect to the set tolerance, and so on. So in this case, for instance, if I set the tolerance 10 to the minus 4, I can compute all the singular values. You see this because at the end, the 2 blocks, it will become just 1 block, and that's why you get this overlapping. So in this case, you are computing all the singular values already, still approximated with this tolerance. You could also set up a smaller tolerance in case you may be interested in really recovering very good accuracy, so you could still use this algorithm. But as I said at the beginning, I'm going to work with full matrices where we are interested mostly in the most important singular values, which are the biggest ones. Okay, so now let's see how do we apply this decomposition in the setting of what is called change detection. What is change detection? So let's say you have 2 hyperspectral images of the same area collected at 2 different time instants. For instance, this one and this one. And the ideal output, so what you would like to produce, is a binary map, something in black and white, where the white pixels are the changed areas, and in this case, the black pixels are what did not change. So in this case, you're looking at some agricultural area in the Hermiston city of the Oregon province in the United States. And so we provide as input this true, and we would like to have as output this guy here. How we do proceed? So first you have this tensor, you vectorize it as a matrix. Then we apply the algorithm to produce these matrices U, S, and D. And then we would like to express every image in terms of some basis times some coefficients. Some basis, W, they should account for the spatial distribution of your pixels, and H, so the coefficient matrix, also called a mixture matrix, that should give you the spectral information. How we compute the W? By using, let's say, these first KS columns of the matrix U and a KS size block of the matrix S. And the mixture matrix H will be given by the matrix B. Okay, then we can select one of these two images. For instance, here I chose the first one, and we are going to project the first one by using the coefficients, so the mixture matrix used for the second picture. In this way, we can compute, let's see it with abusing a bit the language, let's see this as another basis, but we are going to work in a different space. So it's just allow me to call this as another basis. After that, we are going to compute the difference between the W1 we compute at the beginning and this new one. This difference is not a standard difference. I'm going to tell you how we need to do this. And at the end, of course, we would like to extract, as I said, what is white, so the changed areas, and what is black, so what did not change. The difference, what is it? You can apply some standard classical function, like the Euclidean distance between these spectral vectors, or also this SEM, which is the angle between two spectral vectors, and so on. Or you can also use some new distances, functions that we introduced recently. Yeah, so I will just show you some results. Since in this case, we know what is the ideal output that we should produce, we can also measure how good we did perform. And we are using two indicators. One is this overall accuracy, and one is this kappa coefficient, which is less biased. It's a bit more robust with respect to the overall accuracy. So for this example, I set up the tolerance 10 to the minus 2. We used 7, let's say, of the biggest singular values. And so you see what we get. So the best result is given by this guy here. So we get overall accuracy 0.9856, and it means that the more you're close to 1, the better it is. And also for the kappa coefficient, the more you're close to 1, the better it is. Now the question could be, what happens if I take less than 7 components? If I don't trust what the algorithm says? For instance, if I select only 2 components, this guy that was the best one, now it's one of the worst. And also other functions give you poor results compared to before. We could also increase. So let's say that some of them already hit their best, but not all of them. Some are still missing of the important information. And the same question can be asked, what if I use more than 7 components? So the thing is that we don't know what happens in this case at the 8th approximation, diagonal approximation, because we don't have the control. So far we are controlling what's happening up to the 7th, which are the singular values approximated within the given tolerance. The 8th one could be also one of the smallest. We don't know at this stage. And so exactly in this case, we see that this accuracy is reduced. So mostly we are probably injecting just some small noise. So we should trust what we compute before. Here's just some comparison with other methods. So the first one is a method still produced by our group based on the non-negative matrix factorization. The second one is an improvement of the previous one. And then there are other competitors still on the same data set for which we knew this kappa coefficient, which is less biased than this overall accuracy. Okay, so just to conclude, so we are proposing a change detection algorithm in hyperspectral images that is based on matrix factorization, which is the mostly iterative QLP decomposition. We need to use some error function to measure some differences, and this approach is fully automatic in the selection of the number of singular values that we need to approximate, although we need to give an input tolerance, and is rather competitive compared to the state-of-the-art methods. Of course, this I didn't mention anything, but then the output should be post-processed, which means usually you apply some morphological transformation to remove some spurious noise. And somehow you can still try to use some supervised learning approach to improve even more the final accuracy. These are all things that could be done later on, let's say. Okay, so with this I conclude. I hope I was on time, and thank you very much for your attention.
Thank you for the nice talk. Have you remarks, comments? I have a question. About the error measure, does it work even if the background is not the most expensive part of the image?
Could you repeat, please? Because
If the background is not the most expensive. Say if the background is not the most extensive part of the image, does it work the error measure?
So you mean
you use sparse matrices and sparse algorithms?
Well, we don't have sparse matrices. That's the point, unfortunately. The matrices are all full, always. There is no sparse partners anywhere. Okay. Because this is the input. The input is a full matrix. You should be able to detect what is changed from what is not changed.
No, I understood this. Okay.
Okay.
I just, the number singular, small singular values is not important.
No, not for this application, let's say. Okay. Yes.
Okay. Thank you.
Thank you.
Other questions? Okay, let's thank the speaker again.
Thank you.
The next speaker is Antonio Ciccone, Università dell'Aquila. The title of the talk is Inverse Problems in Signal Processing, a Numerical Linear Algebra Perspective. Antonio?
Thanks a lot. Before beginning, I have a problem sharing my screen. Okay, now I can, sorry. Okay. So, can you see my screen, right?
Go ahead, please.
Oh, okay, thanks a lot. Okay, thanks a lot to the organizer for giving me this chance to present our work. It's really a pity not being able to be there in person. Unfortunately, you know, the period is what it is, but it's anyway a great chance for me to present it online. So thanks a lot. So I'm going to talk today about recent results I produced together with my collaborators, Giovanni Barbarino from Aalto University and Ao-Min Zhou from Georgia Tech. And in particular, the talk, in this talk, I'm going to revise recent advances in the development of nonlinear techniques for the decomposition of non-stationary signals. And in particular, I'm going to talk about iterative filtering and beyond iterative filtering, in particular the resample iterative filtering. So the main problem that we are trying to solve is given a signal, a real-life signal, and in particular 1D in this particular case, our goal is to solve the inverse problem of identifying which components are contained in this function. So we want to decompose it into simple oscillatory components, and ideally we do not want to use any a priori knowledge. there are really many possible applications, and economy, medicine, engineering, and so on and so forth. And the problem is that when we deal with strongly stationary components, classical techniques, they really cannot help understanding what's contained in a given signal. So let me start quickly revising what is iterative filtering, and then we can go move on the recently developed methods. So first of all, what we mean by simple oscillatory components. So Wang, the author of empirical multi-composition, 20 years ago, proposed an informal definition which is still in place. The idea is having a signal containing oscillatory components, which are basically functions which are symmetric with respect to the horizontal axis, and such that, so then the zero crossing, the number of zero crossing match the number of minima and maxima, at most up to 1, with difference up to 1, and these curves, they should be symmetric in some sense. So it was suggesting to have like envelopes connecting minima and envelopes connecting maxima to be symmetric. So we can think about, practically speaking, to a generalization of what sinusoidal curves are. So we can think about sinusoidal curves which are non-stationary in amplitude and frequency, or we can think about functions which are no more smooth, but just simply continuous. Those are the simple oscillatory components we want to extract. Now, the next question is how to extract them from a signal. One way is by optimization, and the idea is basically choose a priori basis, and then given this choice, we can, by optimization, identify the sparsest representation based on that basis. There are many techniques that have been developed in the recent years. The problem with these approaches is always that we need to make a priori a selection of a basis when for many signals we do not know exactly what is contained in them. So the other approach is by iteration, and among these techniques there is the pioneering empirical multi-composition and its variants like ensemble, noise assisted, and then there is iterative filtering, fast version that we're going to revise today, and then the adaptive local iterative filtering, stable adaptive local iterative filtering, and resample one, that we are going to see today. The open problem in this field is the stability and convergence of these techniques, except for iterative filtering, for which we developed in recent years complete theory. Okay, so what is iterative filtering? It's a really simple algorithm. The idea is, given a signal, we compute the moving average of it by simply convolving the original signal with a filter or window in order to, in some sense, remove the high frequencies. So we do a convolution with a signal S with a filter W, and the idea is that the size of this filter is chosen adaptively with the signal itself. So that's why a linear operator, which is the convolution, can become actually a nonlinear, can produce a nonlinear approach, which is the iterative filtering. So the idea is that the interval of integration minus LL here is defined based on the signal under stat. And this makes the method nonlinear. What is a filter? It could be any function which is even, non-negative, and compactly supported. And clearly we want it to be of area equal to 1. So then we can use it as the elements of this function can be used as weights of our convolution. We developed a few years ago what are called Fokker-Planck filters. They have the nice property of being smooth on C infinity and to be still compactly supported. But many other kind of filters can be adopted for decomposing using iterative filtering. Now, here I just show a couple of examples. Here we have naked eyes. We see that there are high frequency oscillation, low frequency ones, and the trend. And if we run the algorithm I just described, we can produce easily a really nice decomposition. There are some issues at the boundaries. This is been easily fixable. I left them here just to highlight that boundaries can create troubles. We have been working in this direction. There are many ways of easily solving this problem. And in this second example, I just want to highlight the stability and robustness of this approach with respect to noise. So if I take a signal which contains just two components, if I perturb it with a little bit of noise, I produce a new decomposition which highlight the presence of new frequencies due to the noise plus the original components that we had in the signal. If I further perturb the signal, here we have a 3 dB signal to noise ratio. It's still possible for the algorithm to reconstruct the two components. They're going to be slightly perturbed due to the noise, which is a white noise, so it's affecting all frequencies, but the algorithm is still able to identify the original two. Okay, and a real-life example, it's tsunami. It's an old example we always show, but give you really the flavor of how powerful these approaches are in general. So we have the water level measured offshore nearby Hawaii Islands when a tsunami coming from Japan arrives, and we see that the water level abruptly starts changing pretty quickly. I mean, those are hours. Clearly, if we enlarge, it's not that fast, the solution. If we run the iterative filtering, we can decompose the original signal into several components, highlighting the non-stationarities due to the tsunami. And the regular or almost stationary components, they highlight instead classical patterns, cycles that are well known in the field. Okay, what about fast iterative filtering? So in 2020, we published a paper where we showed that leveraging on the property of the matrices that we use in the convolution and using also the assuming periodicity at the boundaries is always possible to rewrite the algorithm using the Fourier transform, which is a little bit surprising considering that all these kind of techniques, they have been developed with the goal of fixing the limitation of Fourier transform. But, fast Fourier transform is a great way to speed up calculation of matrix vector multiplication. And in this case, where we deal with tablets matrices, we are using the FFT at its best. And so it's possible to accelerate roughly 100 times the original algorithm, which was already pretty fast compared to empirical mode decomposition or equivalent methods. Okay, all this said, the problem is that iterative filtering that we have been studying so far is limited. In which sense? If we take strongly non-stationary signals, then iterative filtering has an hard time separating components as we would like to. We can think, for instance, to this example, we started with two components which are non-stationary, and we observe that the first component starts from high frequency to middle frequency and then goes back to high frequency, whereas the second component starts from an average middle frequency, which is close to the frequency we have here, and then goes to low frequency. So if we look at the plot of instantaneous frequency versus time, we observe that the two curves representing instantaneous frequency, they are always, for each instant of time, well separated, but overall, their ranges, they overlap. So this one goes from 4 to roughly 8. The other one goes from 1 to 6. So there is this overlap. And this is where iterative filtering has troubles, because the algorithm is basically trying to capture components which are quasi-stationary in frequency and amplitude modulated. So if we add together the two components I just showed you, we obtain this signal, and if we pass it to iterative filtering, that's the decomposition we can get. Well, what this represents is simply a splitting of the original signal into several pieces. And I let you observe that basically, if we recombine these parts here together, we re-obtain the first component we were trying to extract. Whereas these pieces that I'm showing with my mouse, they represent the second component. So iterative filtering is not producing anything fake, it's simply splitting the components, not in an ideal fashion. So how to fix it? The idea we had in 2016 was that of simply allowing the algorithm to adapt the filter size or shape over time or over space. So then the idea is, instead of dealing with a convolution, we simply allow the function W to change its support point by point. This simple change in the algorithm allows us to actually separate the two components of the previous example properly. Now, one way of adapting the shape of the filter is, for instance, the easiest way is to by linearly scaling the original filter W proportionally to some, if we have a knowledge of what is the frequency we want to capture. Okay? So here, for instance, in the previous signal, we can, just studying the relative distances between extrema, we can have the blue curve you see here, which is an approximation of an average relative distance between extrema. And we can use the blue curve to guide the adaptive local iterative filtering. That's how we call the algorithm alive. And alive, if we guide it in this way, it can separate in these two components the original signal. So if we zoom in, we see there is still a little bit of wiggling, but the separation is pretty remarkable. Now, the problem is, from an algorithmic point of view, the algorithm seems to work, but numerically, or better, theoretically, how to guarantee the convergence of this approach? We studied for many years the problem. Recently, together with Carlo Garroni and Stefano Serra Capizzano, we published a paper where we were trying to understand how to guarantee the convergence. And we discovered that using the GLT theory, it was possible to construct the symbol associated with the alive matrices. And using this result, we were able to provide necessary condition sufficient condition that guarantees the necessary condition of the convergence. What I mean by that? Clearly, the symbol to guarantee convergence should be in between 0 and 2. And thanks to the knowledge on the symbol, we discover that the filter we want to use in the alive algorithm should be built as convolution of a filter with itself. If we do that, this is a sufficient condition that guarantees that this necessary condition is satisfied. Unfortunately, this was just a necessary condition for the convergence. So we conjecture at that time that this condition was also sufficient to guarantee convergence. But we couldn't do much more than that. Recently, with Giovanni Barbarino, we dig a little more in this conjecture, publishing a paper on the topic. But the main question was still open. So how to guarantee convergence of the life? Until with Giovanni, we had the idea of stabilizing adaptive local iterative filtering. The idea is simply taking the W matrix associated with alive and basically multiplying by itself using transposition. And if we do that, the new operator we have as the same kernel as the previous matrix, the eigenvalues now are all positive, and this is sufficient to guarantee the convergence of the method. The problem is that the method becomes way slower. Okay? So because the iterations becomes more involved because we have to do this transposition, plus due to this operation, the eigenvalues, they becomes closer to 0, which makes the algorithm to converge more slowly to to the solution. Okay, so it was a nice fix, but it was not the ideal way of doing it, because the other problem is there is no way to accelerate this calculation. And that's where we came with the idea of a completely new approach, which is probably super simple, but super powerful. That's what we call resample iterative filtering. The idea, it's really simple. The idea is we have a signal, so with a live, we take the signal and we apply filters that have to adapt point by point. So they start with a big filter and big support, and then to go a small support, following the behavior of the instantaneous frequency that we see in these components. But what if we resample the signal? So this signal here can be resampled in a way that the highest frequency component becomes stationary. If we do that, then we can apply fast iterative filtering to extract the stationary components. Then we can remove it, and we can end up extracting the moving average we wanted. And that's exactly what we do with the resample iterative filtering. So given the signal, we build the curve, the resampling curve. Then we basically apply fast iterative filtering on the resampled signal. We extract the moving average, and then we resample back. So basically is fast iterative filtering with two interpolations, so two resamplings that can be done outside the iterations. This approach is flexible as alive, is fast because we work with fast iterative filtering, so we can leverage on the FFT, and is always convergent. Okay. So and just mention quickly, we also we compare alive in the linear fashion, so when we scale linearly the filter, and we discovered that linear alive, it's basically kind of first order approximation of resample iterative filtering. And these two algorithms are always different, except when the resample iterative filtering and alive use a constant filter length. So we got the theorem that, to show this result. I just show you a couple of examples. Here is an artificial one. We take several components, stationary, their frequency are varying over time. Again, we have an overlap on the frequency ranges. And with alive, with all three methods, alive, stabilized, alive, and RIF, we can decompose, but the computational time is definitely smaller with resample iterative filtering, and the error is clearly smaller. Okay, and that's a real life example, bat sound. So that's the sound emitted by the bat. And that's how the time frequency representation looks like. So we have three main chirps. So there are three components with varying frequency over time. With fast resample iterative filtering, we can easily separate the three components where the original iterative filtering couldn't get anything. Okay. So what is next? There are many open problems. For sure, boundaries, we have to work a little more in this direction for this resample iterative filtering. We never dig into studying how much the filter selection is going to influence the decompositions we produce. We can work on a multi-dimensional and multivariate extension of this technique. We are working on making the algorithm automatic on the resampling part, because for the moment it's manually selected. And comparisons with other techniques is still open field of research. And there are other secondary things, but I guess I better stop here. So thanks a lot for the attention.
Okay, thank you. Just a quick question. This time, just for a quick question. Okay. If not, let's thank the speaker again.
Excellent.
Okay, next speaker is Carmen Scalone, Università dell'Aquila. The title of the talk is On the Approximation of Low-Rank Rightmost Eigenpair of a Class of Matrix Linear Operations.
Okay, thank you very much for the introduction and for this possibility to present my research. This talk is inspired by a joint work with Nicola Guglielmi from the Sasso Science Institute in L'Aquila and Daniel Kressner from École Polytechnique Fédérale de Lausanne. So let me start from, okay, we consider a real matrix-valued linear operator, and essentially we are interested in the eigenpairs of such kind of operator. Not in the whole spectrum, but in the rightmost eigenpairs of the operator. Making the a priori hypothesis on the eigenmatrices to have fastly decaying singular values. So this hypothesis is is suggested by some applications, as I will show you in the last part of the talk. And essentially, we exploit this hypothesis searching for approximate eigenmatrices in a low rank setting, taking all the advantages of this choice in terms of reduction of the cost of the dimension of the initial problem. So this is the setting, essentially. And I show you now a matrix ODE, which is an important tool, which is constructed starting by an operator A. And it is an important tool for our analysis because it is possible to prove some properties showing that this matrix ODE is deeply connected to our problem. So to be more precise, this ODE has a norm conservation property. I mean, if we start with an initial value, which is of norm 1, we remain with the solution, of norm 1. So about the equilibria, if we consider a matrix of norm 1, which is the set of the norm 1 equilibria of the operator coincide with the set of the eigenmatrices of A. And supposing that our operator has a unique real rightmost eigenvalue, call this eigenvalue lambda 1. Lambda 1 is real, and supposed to have a matrix of unit norm, which is an eigenmatrix associated to a simple eigenvalue, a simple real eigenvalue of the operator. By virtue of the previous property, this is an equilibrium of the system, and this equilibrium is stable if and only if the associated eigenvalue is lambda 1, is the rightmost one. So, the main property is about the asymptotic behavior of the system. Again, if we suppose to have a unique, simple real rightmost eigenvalue, and suppose that B1 is the associated eigenmatrix, just suppose it, so it is a stable equilibrium of the system, just assuming generically that the initial condition x0 is not, there's no Frobenius orthogonality between x0 and B1, so the solution of the matrix ODE converges for t going to infinity to the equilibrium. So it is clear that this matrix ODE is deeply connected to our problem, but we still to introduce the low rank approximation. And we mean with low rank approximation, essentially we fix a priori a value R of the rank, which is in general much less than the dimension of the problem, and consider we aim to find solution of the system which are constrained in the manifold MR, the manifold of all the matrices of fixed rank R. We follow the approach of Koch and Lubick, the dynamical rank approximation, which follow essentially the following criteria. We aim to minimize the Frobenius distance between x dot and f of x, where f is the right-hand side of the equation. And the minimization is with respect to all the matrices which are tangent to the point x to the manifold MR. So is respect to the tangent space, which has the vector structure. So the solution is the orthogonal projection of the right-hand side onto the tangent space. And about the orthogonal projection, it is available in the work by Koch and Lubick, the analytical expression of such projection by considering the rank R decomposition of the matrix X as USB transpose, which is similar to the R-reduced SVD apart from the form of S, which is not required to be diagonally, just non-singular. So essentially, we can project our matrix ODE onto the tangent space. In this way, we ensure that the solution lives in the manifold MR. So, and we can write the system, the projected system, as essentially with respect with the factors of such rank R decomposition. In our specific case, is just replacing Z by the right-hand side of the matrix ODE. And in this case, we have again the norm preservation. But about the other properties, it is much more difficult to give a description of the equilibria, and also the asymptotic behavior is more complicated to determine in this case. So we proceed numerically, employing the projector splitting integrator by Lubick and Gauzelets. And in this case, this is a first order method, and we have the advantage for which essentially the error bound is independent by small singular values. Because another possibility is to solve the system of the factors, but in such by a standard numerical integrator. But the problem is the presence of the inverse of S in the system of the factors, because we may have problems of stability when S is nearly singular. And when S is nearly singular, when the starting rank is over-approximated, but we fix the rank a priori, so it is not possible in general to prevent an over-approximation of the rank. So the choice of the projector splitting integrator is better also in terms of stability. And about numerical results, let me show you some examples. In this case, the operator is constructed essentially discretizing by standard finite differences a partial differential equation. And I show you the eigenvalue, the rightmost eigenvalue lambda 1. And if we consider the exact solution of the whole problem without Lorentz approximation, I show you the leading 5 singular values. So you can understand that it makes sense to consider a Lorentz approximation because the singular values are decaying. So for instance, we can consider an approximation in M3, in M4, and I show you the computational results in essentially in this case, fixing R equal to 3 and rank equal to 4. To conclude, I show you a comparison with another method. In this case, we have a symmetric operator. This is a very particular situation in which essentially also the theoretical part is much more studied and well understood, because the matrix ODEs unprojected and projected, essentially along the solutions of such ODEs, the Rayleigh quotient of the operator are increasing. These are gradient system for the Rayleigh quotient. So, and in this case, we can compare our approach with the ALS method, which is based on finding the extremal eigenvalue, optimizing the Rayleigh quotient, and expressing the solution as UV transpose, a Rancard decomposition of type UV transpose, and optimizing alternately each factor. And we find that for different values of the rank, our approach seems to outperform ALS, the alternative least square method, in terms of accuracy and in timing. So I think I can conclude now. This is the essential geography. Thank you very much.
Thank you. Question? Remark?
So if I understand correctly, you're choosing the rank at the beginning. Do you think it would be possible to choose a target accuracy instead and adjust the rank as you go and try to achieve the target accuracy for the eigenpairs or something like that?
Yes. In general, you start with a guess of rank, you update, proceed, and find the best approximation possible. In this case, sometimes we consider some step of the Euler method. We do the SVD to understand the situation of singular values and consider and fix the rank.
Okay, so you basically enlarge the manifold as you go. If I
Yes.
understand correctly. Okay. Thank you.
Mark. Other questions? Okay. Let's thank the speaker again. So the next speaker is the last of the session, is Tommaso Bevilacqua, Università di Milano. The title is BDDC Preconditioners for Virtual Element Discretization of the Stokes Equations.
Ah, sì, dai, uso questo. Thank you for the introduction today, and thank you to the organizer for having organized this beautiful event. So today I will talk about a work I joined with Simone Scacchi, also from University of Milan, and we study preconditioner, balancing domain decomposition by constraint preconditioner for a divergence-free virtual element discretization of the Stokes equation. So today we will see firstly the two-dimensional cases, so we recall just for a moment the Stokes problem. We will see the virtual element method, the domain decomposition technique, and the preconditioner, and we show some numerical results. And to conclude, we just see some preliminary results that we have obtained for the three-dimensional case. So we start considering an omega subset of R2, and we consider the Stokes problem, the steady Stokes problem, with homogeneous Dirichlet boundary condition. So our objective, our goal is to find the couple velocity and pressure that satisfy this equation. So the continuous space for the velocity is the space H01 square, and for the pressure is the space L20 with the usual norms. We assume also that f is a linear functional in h-1 square, and that nu, for simplicity in our codes and from now, is a uniformly positive constant, but it can be any L-infinity uniformly positive function. So we define the bilinear form A, the continuous bilinear form A, that is the grad form, and B, the divergence form, and we obtain the standard variational formulation that we know as unique solution. So we are now ready to introduce the virtual element method. This family of methods has been introduced in the last few years, and could be seen as an evolution of the finite element methods applied to a mesh where the geometry of the elements could be arbitrary. The peculiarity of these methods is the fact that they require the integration of only polynomial function anyway, even if the mesh is quite irregular. And also, their name, virtual, is given by the fact that you don't have to know explicitly a function on these elements, but you have to know only some keys information like some pointwise evaluation or some moments. So we introduce now a tessellation of a mesh, and we define the diameter of each element and the sup of this diameter, and we need to introduce some space of function. The space of the polynomials of degree minus or equal than k, and with bk on the partial k, the space of function that are continuous on the boundary of each element and that are polynomial on each edge of each element. And in this way, we can follow an article of Beirao and introduce the classical local space for the velocity that is made by function that lives in h1 square that are polynomial, so on the boundary of each element, and that has the Laplacian that is a polynomial of degree k minus 2 square. While for the space for the pressure, we consider the polynomial of degree k minus 1. Anyway, in our work, we use a different approach because we use a different approach that has been introduced in the last few years, and we need to define another space of function that is the gradient of the polynomial of degree k plus 1. In this way, we obtain a local space of the velocity that is quite similar to the previous one because it's made by functions that are polynomial, again on the boundary, but the function has different property. We can say most important is the fact that in this case we require that the velocity have the divergence that is a polynomial of degree k minus 1. In this way, we have that the space of the divergence of the velocity is included into the space of the pressure, and this leads to an exactly divergence-free discrete velocity. We have to handle this function, and to do so, we need to introduce some suitable degrees of freedom. And for the velocity space in particular, we take 4 subsets. The first one is the evaluation at the vertices of the velocity at each polygon, the evaluation into k-1 distinct points for every edge that are given from a quadrature rule. It can be any quadrature rule, but we use the Gauss-Lobato. Some moments of the velocity onto the space or of the gk-2 orthogonal, and the moments of the divergence of the velocity up to degree k-1. While for the space of the pressure, we can consider the moment up to degree k-1. With this recipe, we are able to introduce the discrete bilinear form, and
the discrete bilinear form for the divergence bilinear form, so the bilinear form B, is chosen using the continuous one, because we can directly compute these contributes using the degrees of freedom that we have just introduced. Also, we are able to compute directly from the degrees of freedom the continuous bilinear form A when we test a virtual function against the polynomial, because we can integrate by parts and using some suitable decomposition of the polynomial space, and we can recover this two information from the degrees of freedom that we have seen before. The problem came out when we have to compute the bilinear form A for two virtual functions, and in this case we are not able to compute exactly it, and so we need to approximate. We do so using this technique and defining the bilinear form discrete in this way, using two contributes. The first one consists in compute the continuous bilinear form tested on a suitable projection of the virtual function on the space of the polynomial. And this can be computed exactly because we can compute exactly this term. And this is the consistency part. The second one is called a stabilization term, that is a bilinear form that has to scale like the bilinear form A. With this discrete bilinear form, we have a theorem that guarantees us the unique solution of the discrete problem. It gives us an estimation of the error. The peculiarity of these methods is the fact that the velocity has an error that is not affected by the pressure. And we can say that in this case, we can in some sense consider a reduced space for the pressure, and so consider a lot of less degrees of freedom and obtain anyway a good approximation for the velocity. So when we have introduced the discrete bilinear form, we came out with a linear system, and so we can introduce the domain decomposition technique. So we subdivide our domain into some subdomains, like we can see in figure, and so we need to introduce the composition of the space for the velocity and the pressure. The velocity is obtained as a direct sum of a space VE that is made by functions that are defined on each subdomain, and a space V gamma that is made by functions that are defined on the interface of the subdomains. While the space for the pressure is obtained as a direct sum of a space of functions that are defined on each subdomain and has a mean and null on each subdomain, and a space Q0 that is made by functions that are constant on each subdomain. With this decomposition, we obtain a linear system of this form, and we can eliminate the interior variables using a Schur complement, and came out with the so-called saddle global interface problem. That is the problem that we want to speed up with a suitable preconditioner. So to introduce the BDDC preconditioner, we need to define a partially assembled interface velocity space, and we split this space into two subsets. The first one that is so-called the primal space, made by a function that have nodal values in common for all the subdomain, and this made a continuous space, and a space V delta that is so-called the dual space, that is the discontinuous one. So a function that lives in this space as general continuous values on the primal space and discontinuous values on the dual space, on the dual nodes. So introducing a suitable restriction and scaling operators, we obtain that the preconditioner make this system symmetric and positive definite, and so we can use a preconditioned conjugate gradient method to solve it. But this happens only if we satisfy two assumptions. The second assumption is related to the stability of an average operator that is required and that have the function to restore the continuity onto the dual nodes. And this has been proved for the virtual MM methods in an article by Bertoluzza, Pennacchio, and Daniele Prada in the 2017. And to satisfy this assumption is sufficient choose as a primary constraint only the vertices of each subdomain. While to satisfy the first assumption, that is so-called the no-net flux condition, you have to introduce a further constraint, and so you have to require that the integral of the normal component of the velocity across the interface is continuous. And in this way, we have a theorem that guarantees us the fact that the problem is symmetric and positive definite, and gives us an estimation on the eigenvalues of this problem. So we can now see some numerical results for the two-dimensional case. We considered the classical square 0,1 times 0,1 with the homogeneous Dirichlet boundary condition. And we test our code in MATLAB, so we have a serial code, and so we are interested only in the iteration count and, where possible, the conditioning number. So we show here some results for the square meshes, and we highlighted in blue the iteration count that are in some sense related to the weak scaling. So we fix a local problem size and we increase the number of subdomain. And in red, we highlighted the number of related to the strong scaling. That means that we fix the global problem and we solve it with an increasing number of subdomain. We see that solving the saddle point problem with GMRS implied the fact that the number of iteration grows very rapidly. But this not happen when we solve, for example, with the BDDC using only the vertices as the primary constraint. In fact, we have that the number of iteration is really low, but we are not able in this case to give an estimate of the eigenvalues, because in this case the problem is not symmetric and positive definite. This happens instead when we introduce the extra constraint for each edge of the interface. And so in this case, we see also that the fact that the number of iteration is lower, and also we have that the conditioning number respects what we have seen in the theorem before. This happens also for other kind of mesh. For example, the Voronoi mesh, we have the same behavior. In this case, we have an higher conditioning number due to the fact that the mesh in this case is quite irregular. Also, enlarging the coarse space, so introducing an extra edge, an extra constraint for each edge. So we have two basis functions for each edge of each interface. We see that the iteration count and the conditioning number is lower again. And this is a good result, because we can see that enlarging a little bit the coarse space give us a better velocity. So to conclude, here we report also some plots related to an optimality test. So we fix on the left the number of processors, so 4 times 4, so 16 processors. And we see that increasing the number of DOPs implies that the conditioning number has the logarithmic growth that we have seen in the theory. And on the right, we see some plots of the weak scaling. So to conclude, we say that now we are working with Simone Scacchi, Franco Dassi, and Stefano Zampini of a three-dimensional extension, giving also a parallel implementation. And so we are using the Vem++ library written by Franco and the PETSI library, where Stefano implemented the BDDC for the finite element methods. And we test, our test was performed on the Linux cluster of the University of Milan, Indaco. And here we report only the some preliminary test with the cube meshes using the BDDC preconditioner with a variant of the scaling function. We use the deluxe scaling, and we had the possibility to use an adaptive coarse space, so we can choose the number of the primal degrees of freedom that we use to solve the coarse problem. We report here the result for, in some sense, an optimality test respect to the mesh refinement for the k equals to 2. Okay. For k equals 2 and 3 with 32 processors, and we see that the richer coarse space has a very good behavior because the conditioning number, the number of iteration, stay bounded, increasing the degrees of freedom, while the coarse space that is more poor, so as a number of primal degrees of freedom that is quite low, has a worse behavior, because we can see that the number of iteration grows a little bit and also the conditioning number. And this happens also when we fix the number of elements for the mesh and we increase the polynomial degree. And to conclude, we show some results related to the strong scalability. So we fix the global problem and we solve it with an increasing number of processors. We see that the parallel speed up is quite good for the moment. We know that we have a few processors, but the work is in progress, so we will provide some tests with an higher number of processors. And we recall that this parallel speed up is computed dividing the time of the CPU computation with 4 processors divided by the time of the computation with the P processor. And it seems that for the assembling time is quite good, and also is really good when we look at the solution of the coarse problem. To conclude, we see that we compare also the BDDC with other direct solver, the PARDs and the MUMPs, and we see that we have a good advantage, especially in the time of the solution for the global saddle point problem. So, thank you for your attention.
Okay, thank you for the nice presentation.
So this is, you presented this for the Stokes problem.
Yeah.
Can it be extended to Navier-Stokes, for instance?
Yes. For the moment, we are studying the Stokes problem, but we are interested in the extending for the Navier-Stokes. We have there are also some papers related that show the behavior of this preconditioner for the virtual element methods on the mixed problem, the Laplacian seen as a mixed problem, and is our current work. So we will extend after that, after this. Yes.
Thank you.
Let's thank the speaker. Oh, do you have other questions? Sorry. Okay. Let's thank the speaker again. Volevo ringraziare gli organizzatori per questa magnifica 2 giorni e passo la parola a Daniele.
Allora, grazie Silvia. I don't know if I must speak English o devo parlare italiano. We have been speaking English all the time, so I can speak English. I have just a couple of announcements. Tomorrow morning we are starting at 8:50, 10 to 9. Okay, so we will see each other tomorrow. And also we are going to take a picture of all the participants. Probably it will be just before the coffee break in this room. We can stay here. And I also want to thank everybody for coming here to Naples. And in particular, I want to thank 3 people that gave us a strong support. One of them has already left because she had to go back home, but two of them are here, and they are, please come. Rosanna and Monica, please stand up and come. Rosanna Campagna from the University of Campania Vanvitelli and Monica Praiola from the University of Naples, and also the other one is Serena Crisci from the University Vanvitelli too, and they gave us a strong support. They took care of the registration, they welcomed people, so they played a very important role in the overall organization of this meeting. So thanks again. And thank you to everybody, thank you to the speakers, thank you to the participants, and see you tomorrow. Have a nice evening. Goodbye. Ora noi? No, I've already said that. The second was remembering me about the picture, but I have already said that tomorrow morning we will take this picture just before having the coffee break. Thank you. No, ma magari ce la facciamo qua la foto prima di...